This is good. Yeah.
Yeah. The recording bot. Taking samples. So exactly the local
There's like
So you're showing the wrong screen. You're showing your screen instead of the big one.
Oh, really? Oh,
Yeah.
Thanks for
Yeah.
How is it? Which one is showing? Oh, really? Oh,
Share the whole screen or something.
oh no.
Now, but then that one is wrong.
Yeah. Sorry. Maybe we can keep going.
Yeah.
That's the
There's a thing at the top. Right? You can click swap. Let's swap. There you go.
yeah. Thanks.
Yeah. Where is it working? It's
I don't
there.
think. Yeah.
So
Shall we?
this screen you share.
Shall we start going?
You can just duplicate
Yeah.
your speaker notes. Please use my show. Actually, I'm not sure. Should we try this?
Yeah, both of them gonna be like this.
Is that
Oh,
okay?
yeah, oh, yeah, yeah, yeah. That's good.
Yeah, is it good now? Yeah.
All right, thanks. All right, yeah, let's get started. Yeah, thank you everyone for coming to, sorry. Yes. Yeah, thank you everyone for coming to our workshop on the robot safety and the uncertainty from the intangible specifications. And yeah, I'm happy to co-organize this workshop with the Vikas and Pio and Iwe, Nicole, and Dimitra. And we also have an option for attending Zoom. So like, yeah, would be good to check as well. And we have a website where you can scan this QR code to see the website. All right, so the workshop scope is generally safety, but let me introduce a state-of-the-art robot safety, which, for example, consider mobile robot in an environment with obstacle to avoid the collision to navigate through as an example. And there are a couple of techniques there. Sorry. From the control theory to ensure the safety. One is the control barrier function to ensure the safety by imposing a linear constraint in terms of the control input. And we also have the reachability analysis to care about the worst case scenario and solve the Hamilton-Jacobi PDE to obtain the optimal control for ensuring the safety, also caring the worst case scenario. And we also have a model predictive control, the MPC, as a technique to ensure the state constraint over a finite time horizon, where we can impose the both safety and the state and input constraints. And those state-of-the-art methods generally very advantageous in terms of guaranteing the safety in a formal way. However, we need the explicit formulation to describe such a safety constraint. For example, if we use the CDF, we need to know the control barrier function itself, and to use the reachability analysis, we need to know the function about the state constraint as a mathematical description as well. And the question and the challenge we are interested, as we see in the workshop title, is that some safety constraints are intangible, which cannot be described by the mathematical or analytical expression, and we need to infer the safety constraint from data and demonstration. And we also sometimes need to describe by the natural language as a safety condition. And another challenge is that in practice, the robot model and environment models are uncertain. So the question is how to quantify the uncertainty and how to define the safety under such a stochastic scenario. Also, when we implement this whole the architecture in practice, we need to care about how the accuracy of the perception is and how to estimate the environment and the safety corresponding to that from the raw sensors, and how to reason about the semantics to care about the constraint with respect to the semantic information as well. So as one example, learning safety from demonstrations have been recently studied a lot. And the recent one tries to train the certificate for the safety through the obtained data. And that kind of certificate running can be done for a given data points, also separating the safe data and unsafe data, and train the CBF to minimize the loss function with respect to the constraint and condition about the CBF, also associated with the QP the formulation. Another interesting direction is to run the robot objective from physical human interaction. So the safety constraint can be trained through the interaction with humans, where the human interaction can be informative in that scenario. And there is growing work on the natural language with logic to describe the safety, such as incorporating the signal temporal logic to describe the condition in terms of negation and or operator, as well as the globally and eventually and until operator to describe a condition in terms of temporal logic. And there is growing work on describing the safe control based on the STL constraint. And another interesting direction is to use this the STL and the quantified uncertainty about the future prediction by the method so-called the conformal prediction, where the uncertainty quantification can be done for any general probability density function by the sorting the data points, and we can guarantee the probabilistic constraint about the safety or some constraint about the obtained the information. Also, in terms of the perception uncertainty and semantics, there is growing work in terms of general the computer vision and perception, but to use those information for the safe control, we need to exactly construct the environment, and there is a growing work on identifying the map environment through the perception, and also identifying the semantic information throughout this state-of-the-art perception methods. And we also see the trends on the perception for 3D rendering, such as the NAF or the Gaussian strutting. But the question is, when we use these state-of-the-art methods for the safety critical scenario, we need to know some sort of the guarantee in terms of the accuracy and robustness and uncertainty measure for those perception techniques. That's what we are interested in. And yeah, motivated with these technical aspects, we are very much excited to have a special lineup of the speakers from several institutions and industry as well. Where we will see those exciting talks later on. And yeah, here is the schedule of today's workshop. And we have the 7 invited talks and 1 PhD talk throughout this schedule. And in the afternoon, we have a poster session from the accepted papers regarding the topic of the safety under uncertainty, especially in terms of the intangible specification as a topic of this workshop. So yeah, I would appreciate everyone to attend and like ask questions and for those throughout poster session. And we have in total the 12 posters where the papers are uploaded in our website. So please check them out. So this concludes the opening remark. And shall we? Let me first give an introduction of the first speaker for now. And so the first speaker is the Andrea Baici. She's the assistant professor from the Carnegie Mellon University, especially in the Robotics Institute, where she leads the interactive and trustworthy robotics lab, and broadly works at the intersection of robotics, machine learning, control theory, and human AI interaction. And she obtained her PhD from UC Berkeley in 2022. And she's a recipient of many awards, including NSF Career Award and Google Research Scholar Award, and the Rising Stars, and honorable mention of the TRO Best Paper, and NSF Graduate Research Fellowship, and so on. So let me please turn to the Andrea. Is there? I have the document. Michelle?
Yeah, I'm sure I know. Does it look good?
Yeah.
Amazing.
Let me.
Are you ready for me to start?
Just a moment, please. Make host. Yeah, if she's cannot really share, then it's good.
I did.
Yeah. Good.
Fantastic.
Thanks.
All right, thank you so much for that lovely introduction. It is so nice to see all of you here. I know it's early, but I'm going to try to keep it exciting. We are at workshops, so we're going to talk about some frontiers. But let's start out with some motivation, even though I know I don't need to motivate all of you. You are all roboticists with high probability. It's a really good time to be a roboticist. For the first time, robots are actually kind of doing stuff. Like when I started my PhD 10 years ago, I did not expect that I could take a fully autonomous Waymo ride today in San Francisco. Actually, how many of you have done this? How many of you have taken a fully autonomous ride? Raise your hand. Okay, right? This is way higher than I've ever seen before. And if you haven't, book a ticket today, go to San Francisco and try it out. It is super, super, super cool. But one thing that's really exciting is it's not just navigation. I remember when I started as a PhD student, my advisor told me, get the robot to do just simple pick and place. We had a robot manipulator. And it was so hard to get the robot to grab anything. Now, my PhD students, in about a week, thanks to these modern models, can actually get robots to do something useful, some kind of useful pick and place task in a week. So it's a really, really good time to be a roboticist. At the same time, it is precisely these increased capabilities and widespread deployment that have gotten people a little bit more concerned about safety these days. And these people are not just technical experts. In fact, regulators, policymakers are really worried about these things. You can see on the right-hand side, the executive order from the prior Biden administration about this. Companies have entire safety teams now. This is starting to become a serious thing because if you want to deploy your system at scale, it's got to be reliable. The challenge, which I'm sure because many of you are here for this intangible workshop, you are familiar with the fact that if you are deploying robots at scale out in the unstructured world, what it means to be safe is really, really nuanced. It's not obvious. Now, I like to start with the following example. Let's start with a seemingly simple specification of safety, which is collision avoidance. I'm sure all of us here would agree on this spec. I also would contend that this is a straightforward specification to measure. If I tell you the positions of the vehicles, I can measure L2 distance between them or their penetration. I can tell you if they're in collision. But what I like about this example, this is our favorite example to pick on, it's Tesla Autopilot. It's on the Bay Bridge, and the autopilot decides to do a hard brake. Okay? This hard braking maneuver in the middle of the highway causes a multi-car pileup. I was in the Bay Area during this time. I was trying to go to San Francisco. It ruined my day. Thankfully, no one was hurt. But what I like about this example is we often think, okay, well, to avoid collisions, just stop. Okay, stopping happened here, and safety was violated. And that's because even if the safety spec is simple, safe decision-making is very hard and extremely context-dependent. But the thing that we're interested in this workshop maybe goes even further. Safety is more than just collision avoidance. Consider on the right-hand side this fantastic work from Professor Adi Majumdar's group and Google, where they had this large language model-based task planner telling the robot how to execute some behaviors to accomplish a user's goal. And what I love about this example is that here they're arguing, rightfully so, that a safe autonomous system should be one that asks for help when it's uncertain. So here there are two generations that the LLM proposes for the task. They are both almost equally likely. It is probably good to be like, what did you actually want? Rather than just, flipping a coin and picking the best. But what I also like about this example is it highlights another type of safety concern. And that's that robots should understand that it's just fundamentally unsafe to put metal in microwaves. That can lead to unsafe outcomes. Finally, I like this example too. This is a Roomba that has literally broken free into the open world. I don't know how it escaped. But when faced with this pool environment, this poor Roomba does not understand the consequences of getting too close, and it ends up taking a little swim. All right. So this has got me personally very interested in what does it mean to generalize safety. All of these behaviors we saw these robots do are super, intuitive to us. I know not to brake on the highway. I know to walk slower at the edge of a pool. But codifying this, mathematically injecting it into reasoning is really, really, really hard. Now, I started thinking about this from the perspective of my prior background and grounding in robust control theory. This type of safety over the past few decades has steadily been making progress. This is a non-exhaustive list of some works. They're just pretty videos that I thought would be nice to highlight here. And specifically over the past several decades, these kinds of models have been scaling up to more and more complicated systems, more complicated settings. And in this kind of formulation, safety means constraint satisfaction. Now, what I like about this mathematical framework is it's grounded in dynamic game theory. And what this really means is that it really formally models feedback loops, tight feedback loops between the autonomous system and the environment. Another thing I particularly like about this framework is that it really tightly couples the detection of an unsafe event with mitigation strategies. What should the robot do to prevent something bad from happening? The challenge, though, is that for the longest time, this very general mathematical framework has been limited to hand-designed state space representations, hand-designed representations of failure. And this is really, really painful. I'm not going to do another poll. Many of you, if you've worked with tools like CBFs or reachability or even constrained NDP, know that it is really, really hard to get this to work. You have to sit there and be an expert to write down the correct state space representation, get a high-fidelity dynamics model, then Even if you have all that done, you have to actually write a constraint function. This can be arbitrarily hard. You know, we talked about how collisions are like not too hard, but they're actually pretty hard to encode in a collision checker. Collision checkers are not easy to implement. Okay, so this always requires a really, really highly trained expert in the loop to get this to work at all. And this is going to work in one particular setting for one particular safety specification for one particular kind of state. Okay, on the other hand, simultaneously, generative modelings as a paradigm have been growing in parallel. And these models have been able to learn really interesting, complex patterns about the physical world. My first introduction to them was actually through trajectory forecasting, because in trajectory forecasting, you have no idea what the internal state of a person is. You have to consume a lot of data to understand their intent, their latent state, and essentially figure out how that might evolve their future behavior. But I'm sure all of you have interacted with these models in other forms like, Gemini, Claude, things like that. So as I mentioned, what is the pro of this paradigm? It's these latent representations. The fact that I don't have to handwrite what is going on in your brain. I can try to infer this from a lot of data. And this is really, really nice for extremely complicated modeling problems. Another thing that's nice about these paradigms is that they're quite intuitively informed by non-expert feedback. How many of you have given a thumbs up or a thumbs down to ChatGPT? Raise your hand. Or you've compared outputs. There we go. Okay. I'm not saying you guys aren't experts in understanding ChatGPT. Maybe you are. I definitely don't understand all of the internals of ChatGPT, but I can still get it to do what I want. Okay. The problem with these paradigms, though, is that oftentimes when we talk about safety, we typically think about something like anomaly detection or uncertainty quantification. And these are really, really important parts of safety, but they're typically decoupled from mitigation strategies. So the robot knows that it doesn't know, but it doesn't know what to do. So a nice example of this, there's this interesting work from Professor Marco Pavoni's group on the use of large language models as kind of open world semantic anomaly detectors. I think it's a really nice case study in the potential of these models to really scale this kind of reasoning. And here's an example. If you see this Tesla Cybertruck with this light post on the back, the LLM can tell you that's pretty weird. But what should you do? Should you pull aside the road? Should you do a hard brake? It's not always clear. And so my hypothesis that my group has been really pushing on is how can we systematically unite these two paradigms to really get the best of both worlds? Perhaps if we take careful steps, we can unite the best of the robust control literature with the power of these generative models. And I don't have time to go into everyone's work. I'm just going to flash some work right up here. One of the works I want to specifically highlight on the top right here, this is a paper we have here at ICRA. I see the student who led that in the back over here, Leo. You should go to his poster. You should talk to him because this is very related to the introduction, which was all about how we can use natural language as a nice way for non-experts to specify safety constraints. So you should definitely check that out later in the ICRA program. All right, but for today, I want to talk about the following three works. We're going to talk a little bit about foundations, just establish the same language about what I mean when I say safety. And then we're going to talk about two frontiers. One is the recent work that we're presenting at RSS, and another one is a hot off the press archive paper, because I know that's what we all want to talk about. All right, let's get into it. So let's first establish some common language about what we mean when we say safety. And for this, I want to start with a simple motivational example from some of my old work. So here's a robot. It's navigating an environment. It's using a vision-based planner. So actually those RGB images you see on the lower right-hand side is what it's using for decision making. And here, this base planner that the robot is using to make decisions generally is pretty good. It's exploring, but sometimes it's overly optimistic. So for example, it decides to cut a corner a little too sharp, causing the failure, which in this case is collisions. Now, most of the time, this base planner is good. I want to use it because it helps me explore this environment, but I want to somehow minimally modify the generations or the output from this base planner to keep it safe. And here's where our first idea from control system safety can come into play. Safety filters are a policy agnostic mechanism that you can wrap around any base policy. And what it's going to do is it's going to monitor the output of that base policy, and it's going to modify the output actions so that the current action generations do not result in future failure or future constraint violation. Okay, the big trick with safety filters is how do you synthesize them? How do you construct it? And so let's go through a few of the ingredients that I think we need to generate these safety filters. That says the 4 ingredients for safety. All right, we're going to start out. We know it, we love it. We need a state space. In something simple like this Dubin's car, in this ground vehicle, we can use a Dubin's car-like model. Maybe you have positions, orientations, velocities. Next, you need a dynamics model. In general, this can be continuous or discrete. It can be written down by hand, or it can be a call to a high-fidelity simulator. And note here that the state evolves via 2 inputs in general. One is the robot's action. In this case, is denoted by U. And then in the robust control language, you oftentimes have an extra input D here, which is a way in which you can model uncertainty and ensure robustness to uncertainty. And so this is oftentimes called like an opponent model or an adversary or a disturbance, and it can model a variety of different things that you might be uncertain about, an explicit adversary or just unmodeled parameters like friction. All right, last but certainly not least, we need to represent failure. And here, if I know exactly the geometry of the environment, I'm good to go. My failure set is just going to be any states that are obstacles. All right, with these ingredients, we can cook up a safety filter. And the specific tooling I'm going to use to compute a safety filter is Hamilton-Jacobi reachability. Okay, so this is a safety filter synthesis technique. And essentially the key idea is that failure set, remember it was just a subset of our state space. We say, if my robot is ever inside of the obstacles, I am doomed. That's a SAT problem, a satisfaction problem. And reachability intuitively is going to convert that satisfaction problem into an optimal control problem. That conversion lets us use a lot of modern fancy optimal control tools to do the construction of the safety filter. And the first step in reachability is we're going to encode essentially the distance, the failure set, the distance of the failure set via this margin function L here. And essentially, this is just a sign distance function. It's telling us how close are we to failure. If it's negative, I'm inside of the failure set already. If it's positive, I'm good. If it's 0, I'm right on the boundary. Think of this as essentially like a cost function in an optimal control problem. Now we want to know, for any initial state of the system, does there exist an action the robot can take so it steers clear of failure? And if you're solving the robust version of this, this must be true even under the optimal adversary's perturbation to your trajectory. Now, formally, this is a safety critical game whose value is defined here. I am not going to go into the details of this equation. It has a really beautiful long history. If you want to talk more about this, please come find me after. I can give you resources, or we can just talk math. But the intuitive thing for those of you who are seeing this for the first time here is that this value function is going to remember. It's going to remember the closest that the robot, the system, ever got to failure, despite its best efforts to stay away from failure. And the sign of this function is super important. If the value function says negative, then this means that despite the best efforts of the robot, there was nothing it could do to stay away from failure. Because we remembered that the closest we got to failure was negative. Negative is inside of the failure set. Now, thanks to decades of progress, we can solve this safety game via a variety of tools. So in low-dimensional state spaces, we can solve it with high-fidelity grid-based PDE solvers, for example. In higher dimensions, there's exciting work on using reinforcement learning or adversarial reinforcement learning, as well as self-supervised learning techniques to do this solution. And here I'm just showing you one such solve happening in real time. And you see here the value function growing. I'm going to play that one more time as it's being computed backwards in time, essentially by dynamic programming. Think of it. All right, once we run our solver, we extract 2 really important quantities. All right, so the first quantity is a safety policy. This is a best effort strategy for the robot to stay away from failure. So it's a feedback policy. You plug in any state you want, it tells you what to do to stay away from failure. You can also get a safe set. Sometimes we call this a monitor. Essentially, it tells you if the robot is doomed. And you can see this boundary that has kind of pulled back from the failure set is precisely what is so interesting about these optimal control problems, these safety problems, because there's a non-trivial gap, because the robot has dynamics, which means that if it gets too close to the obstacle, it cannot help but end up colliding with it. And the monitor tells you precisely the moment of no return. Now, here's a little visual. So these are, I'm showing you a slice of this value function. It's high dimensional, it's like 4-dimensional, but I'm showing you a slice of it for a particular orientation for a particular velocity. And you see that intuitively in this low dimensional example, the safety controller makes a lot of sense. It's basically pushing you away from the failures. But the beauty, by the way, the important thing about using these kinds of tools is that these safety controllers and the safety monitor are not intuitive in general to construct. You want them to be computed because it's very hard to hypothesize them, especially hypothesize ones that are tight, that are maximal in their safety. And we'll return back to this later. Finally, last but not least, here's a really simple safety filtering scheme you can implement. As long as you're solidly inside of that safe set, you can apply whatever you want. This is called control invariance. You use your favorite base policy, use your neural network, use whatever you want, teleoperate. As soon as you get near the boundary, which is the last point at which there exists a safe control, you have to override the base policy and execute the safety policy instead. There are many, many other ways to implement safety filters. For example, control barrier functions are really beautiful ways of blending a nominal control with safety control. If you want to check it out, there's really nice surveys down here where you can read more about advanced safety filtering techniques, but this is the simplest you could possibly implement. All right, here we see our safety filter wrapped around that vision-based policy we saw before. On the right-hand side, you see that red boundary here, which is the safe set, updating and changing over time, because actually here we're recomputing it online from new sensor measurements, new SLAM maps, basically, as my robot is exploring the environment. And so we're essentially going back and forth between filtering and updating based on new sensor hits. And you see that overall, we can prevent the robot from taking those overly aggressive maneuvers to end up hitting those obstacles. All right, now we are all on the same page with some foundations. When when I say safety, you kind of know what I mean. But if you really read a lot of this literature, what you're going to realize is that under the hood, the majority of the safety representations are all collision avoidance. Okay, this is a very non-exhaustive list. I'm picking on mostly myself and my friends, but there are many, 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 many people, many other papers you can definitely look at here. But these are just snapshots from some of my papers on the left and in the center. The failure set ends up looking like distance between two agents is less than some threshold. Distance between the robot and the obstacles is smaller than some threshold. Distance between the robot's head and the ground is smaller than some threshold. And these are very important safety representations. But the kinds of safety representations I'm really curious about these days is more than just collision avoidance. It's safety problems like this. It's spilling, it's breaking, it's tearing. Now, a fair question to ask here is, what's holding us back? Why is it hard to do safety for these kinds of problems? And here's where I like to return back to our ingredients. By the way, for the rest of this talk, I'm going to kind of ignore the disturbance. We can talk about that later as well. But for now, let's just focus on the other ingredients. And to understand what's holding us back, let's take a closer look at a canonical example we're going to return to. Here's a robot, and it's picking up a bag of Skittles. Now, I know Skittles are not safety critical. They're just an example, okay, of spilling, tearing, breaking that more generally might be legitimately kind of life-threatening or safety critical. And here the robot, for some reason, has decided to pick up the Skittles bag from the wrong end. And when it pulls up, that failure happens of all the Skittles spilling all over the table. Now, I'm not going to do this exercise with you. If I was giving a lecture, maybe would actually, you know what? We have a little time. Okay, let's do a little exercise. If you had to design a state space for this problem, what would you put in your state? Raise your hand. I will call on you. I want to hear how you design the state space. I know it's early for a quiz, but you guys can do it. Oh yeah. Let's start in the. Okay, Nikolai, go ahead.
All the Skittles.
All the Skittles. Amazing. Love that. Next.
Since you said my answer, I'm gonna go for the image.
You're advanced. We'll get that. We'll get to that. Let's think about like first principle state. Yeah.
Some notion of position, because I'm guessing gravity will play a role.
Yep.
Position, velocity, acceleration.
Love it. Yeah.
Orientation of the Skittle.
Amazing. Yeah. Yes.
Yeah, like similar, like upright.
Amazing. I think there was someone over here as well. No?
I was mentioning right.
Okay. Anyone new? Yeah.
The opening of the skill bag.
Opening the skill bag is good. I don't know why I just got kicked off the Zoom. That's okay. I'm back. Loading it up. There we go. Okay, good. By the way, when I gave this talk in the robotics seminar, a faculty was like, what about the color of the Skittles? Do you need the color? And technically you might, right? Like if the constraint is never spill red Skittles because they're my favorite, you got to have color in the state space to represent that failure set. So it gets arbitrarily complex, right? Okay, so now given the state space representation we all designed together, what are the dynamics? Who's going to give you the dynamics model here? Okay, some of you might be mechanical engineers or aerospace. There's a keyword I'm looking for here. Some of you might know about.
Finite element.
That's what I'm talking about. Yeah, so you could do something like finite element analysis, right? Maybe if you're representing the bag as a mesh, you can maybe kind of think about all those particles moving, you know, that's what you could try to do. And the thing is, that's very fair. And I think it's worth thinking about. There are a lot of representations of robotics that do that. But as we can all kind of tell, it's getting complicated, right? It's getting very, very hard to scale. And last but not least, you know, we talked about what is the failure set. This is where some nuance comes into play as well, based on the end user and the end capability, right? For example, the failure set can be, you know, some volume of Skittles are on the table. The failure could be any red Skittles on the table. It can get arbitrarily nuanced, and it's very hard to measure because the Skittles are partially observable. They're in the bag most of the time, and only when they actually are on the table do you know that you failed, and that's too late. It's too late once you see the Skittles. All right, so hopefully I've convinced you why this is not trivial. And the question now is, how do we do this? How do we go beyond collision avoidance? And maybe, I think we had some smart audience members here. What we really need to start thinking about is we need to start reasoning about safety maybe beyond hand design representations of state and dynamics, because it's really, really, really hard to do this at scale. And that's precisely what we hypothesize in this next work. We're going to take a really big leap here and start doing this unification together. Okay. So even though we don't know how to write down our state or our failure set by hand, it might seem like all hope is lost, but there's one nice thing, which is that failure is observable. We're assuming this, that failure is observable from high dimensional observations. If I show you Skittles on the table, you can tell me that is a failure. The trick now is that you have to learn to predict if the robot's actions are going to cause this, because again, if the Skittles are already on the table, you're already doomed. And this is where we start taking inspiration from generative models. The key idea of this work was, well, let's do safe control directly inside the latent space learned by generative world models, which are essentially just generalized dynamics models. And so before we had a setup like this, now we have a setup like this. You might say to me, that looks the same, just with the Z. Technically, at a mathematical level, it is. In practice, it's very different. All right, this is what our problem looked like before. You know it and you love it now. This is what our problem looks like now. State is going to be an encoding of some high dimensional observations. So we now have a latent state Z. It's an uninterpretable vector in Rn. Failure is just going to become a classification problem. I don't have to now train a complex collision checking function. I need to train a classifier. And my dynamics model is now my world model. And let's start here and briefly talk about how you construct these. So world models are trained from the following type of data set. You get observations. In the examples I'm going to show you, we're going to use a third-person camera, a wrist camera, and the robot's proprioception. And this is paired with action labels and the next observation you got to see. This does not have to be optimal data. It can be random. In fact, I'll show you the data composition later. The majority of the data we use is random. And essentially what you're doing is, for those of you who come from control background, you're posing and solving a sys-ID problem, a system identification problem. So essentially what you're going to do is you're going to take those observations, you're going to encode them into some lower dimensional representation, this latent state Z, and then you're going to learn a dynamics function in the latent space. It's just transitioning how will Z evolve to some ZT plus 1 given ZT and AT. And because you know the true observations you see next, you can train this with a variety of mechanisms. For example, teacher forcing, image reconstruction. There's many, many ways you can train this. I am not innovating on this for the record. These are two really nice works you should check out. We are building on really nice work from the model-based RL community and the generative modeling community. The top paper is an older paper. Maybe you've heard of it, called Dreamer. The bottom paper is a very new paper called Dino World Models, which essentially uses some pre-trained vision encoder priors to bootstrap the world model training. That's what we use in hardware. It's very, very helpful there. All right, now that we have a world model, what we're going to do is our safety specification problem just becomes a classification problem. This is nice because I can show you a data set. You can tell me left is safe, right is in failure. Okay, we train the classifier. Our loss is going to make sure that we're kind of assigning the right sign to everything. And this is just essentially lifting that safety specification we had before, but now it's all happening in the latent space. All right. It's at safety analysis time. We're going to do everything now in the world model, but the equations will look quite similar. So now we have some latent failure set. It's going to be these imagined failures of the Skittles. So I can essentially do all of my control in the world model. I don't have to do any new interactions or rollouts in the environment. I ask my optimization problem, if I started seeing these observations and I was moving around in my latent space, what is the closest I'd ever get to failure? And that's exactly what we're just solving, just the latent space version of our reachability objective. And the beauty here is that if we actually were to solve this problem, this is the latent space version of the Hamilton-Jacobi-Bellman equation, we would automatically construct this latent unsafe set, which would discover these interesting scenarios. Like if I start out with my Skittles really high up like this, there's nothing I can do. Those Skittles are coming out. They're doomed to fall. So it's going to identify these situations for me, all from just the high dimensional observations. All right. Ultimately, we're going to do the same kind of synthesis procedure. We get those same two quantities out, the safety monitor, the safety policy. At deployment time, this is the setting again. We encode the image observations. Now we can roll out whatever task policy we want. If we're getting too close to danger, so our safety filter knows that if you keep doing this, you're going to be doomed, we override and we use our safety controller instead. All right, let's see how this actually works in hardware. So this is the setup from before, just a reminder, here are the cameras. And now what I'm going to show you is we're going to be shielding a teleoperator. So if my student is teleoperating here with no safety filter, he can easily just grab the bag in the incorrect way and cause that spill. Now we're going to go through our safety filter synthesis procedure. Here's the data set we used for world model training. It's 80% random trajectories my student just sampled from a Gaussian and executed those kinds of actions, 10% explicit safe demos, 10% explicit unsafe demos. We then do our safety computation offline in the world model to construct our latent unsafe set. And here is what comes out. So if my student grabs the bag from the top, by the way, the safety filter is running in the background now, but he's fully doing the task on his own because it's safe. Next, he's going to try to grab the bag by the bottom and shake. And every time that green boundary pops up, it means the safety filter is correcting him. Here, it's actually slowing him down. But it still lets him mostly do the task. But now if he grabs from the bottom and pulls up super hard, it's going to block his entire command. It's going to say, you cannot pull up. And here's an uncut version of this. You can see the safety value function over time. You can also see the raw image observations we're passing in on the upper right-hand side. And you see that this is quite a smooth interaction between the robot and the teleoperator, where only these last resort moments are corrected. If you're ever in Pittsburgh, come talk to me. You can do the demo. It's really, really fun. All right, let's keep going. I'll show you some maybe out of distribution tests we did. We bought a bunch of Skittles we could find. We tried them all out. Turns out the system generalizes to other colors of Skittles as well, even though it wasn't trained on them. It was only trained on the red ones and to background changes. This is not perfect though. So here's some dirty laundry. Observability challenges are definitely difficult. Here we rotated the Skittles bag upside down. Neither the wrist camera nor the third-person camera can see that the bag is opened. Of course, it doesn't filter. And on the right-hand side, we changed up the dynamics. We put an M&M's bag here instead. I have a great appreciation now for a lot of different candy bag stiffnesses. This is also peanut M&M's, which are heavier, and the dynamics totally break down and the filter breaks down too. One last key challenge I want to quickly mention is you also cannot safeguard what you cannot predict. And the problem is that world models in the real world are going to have like finite data coverage. So for example, think of this Dubin's card here again. There's two failure sets, the gray and the purple region. If your data coverage never shows your robot entering into that purple region, the world model can be very unreliable. For example, if you ask the world model to predict what will happen if this robot moves forward, you can see the prediction on the right-hand side, some crazy teleportation happens. So you can't really rely on this anymore. And this is true in a lot of real world scenarios. For example, in the game of Jenga here, there's so many ways the Jenga tower can fall that you will never see it is really, really hard to perfectly predict every single way the Jenga blocks can fall. And so, of course, you're going to have this kind of hallucination problem. And so if we go back to our latent safety problem, what you can do is you can say, well, in reality, I'm only getting some partial coverage of the failure set. I know some failures, but there are many things I don't know. There's many things I just don't understand, like what would happen if I left this data manifold that I've learned on. And so what we've been doing recently is using the epistemic uncertainty of our world model as a proxy for unseen failures, essentially keeping it always in distribution. And it's more conservative than it needs to be all the time, but it helps us protect against these uncertain imaginations we just saw. And so you can do the same kind of safe control synthesis with the union of known and unknown failure representations and keep yourself in this region now. And this really helps you with those kinds of examples like I showed you with Jenga here. So here the robot gets corrected. This is the teleoperator again. And here the robot's going to grab these cubes, and the cubes will fall off if you keep pulling out. The robot has never seen the cubes fall down, but the safety controller still says something weird is about to happen. I don't understand. Stop that. If you want to check out more of this, this is our very recent paper we just put up on arXiv, and you can check out more details. I want to say a quick thank you to all of my students and my sponsors, and that's my time. Thank you guys so much. Sorry, I went a little over.
Thank you, Andrea, for the exciting talk. Is there any question from the audience?
I have one. Thank you. It's very interesting topic for work here. I wonder how you train your model here. Like, do you do a lot of signal collection and did you human label all the failure? Like,
right now, all the failures are human labeled, yeah. But we have some other work where we can actually use a vision language model. We can align it in the latent space, and it can be a critic.
I see. Thank you.
Which is a more scalable approach.
That was a great one. Just to clarify, so for the imagine the videos that you're showing those sort of things with things like Dino and the world model, so that just do video generation.
We tried both recurrent state space models like Dreamer that have the reconstruction objective and Dino, which has no reconstruction. Yeah, we tried both in hardware and in sim.
But for the imagine videos, it's just trained with a world model and then just generate the videos as you do the hardware.
Yeah, the videos, for example, in the Dino example, because there's no decoder, when you actually do the imagination, we have to train a decoder and then just visualize it after the fact for the interpretability. I don't know who was first. You're the boss. No, you're the boss. You get to choose.
Yeah, and can you come to the mic actually, because there's a Zoom audience as well. So.
Yeah, it's a big audience, right? Thanks, Andrea, for the really nice talk. I really enjoyed that. So I have a question about so we're going into a latent space, which is something lower dimensional, right? So have you thought about if you can get actual safety guarantees for the underlying original system, because we're always going into a lower dimensional space. If we do the analysis there, the trajectory may correspond to multiple trajectories in the original space. Do you have any thoughts on that?
I think it's a really, really good question. Unfortunately, I don't have anything intelligent to say yet, but I think it's the right question to ask. Yeah, so if you want to talk more, we should. Yeah, I think that's an awesome question.
I have a maybe somewhat related question. So in the latent space, I was thinking, you mentioned because you have examples, you might not have a perfect description of the unsafe set. Do you encounter cases where you specifically observe some non-physical behaviors, but they could be related to either safe or unsafe situations, just because the unsafe set is not described really well? I'm thinking of reinforcement learning and how it's really good at finding these kind of cases that exploit the cost function. I wonder if something similar can happen here.
Yeah, that's a great question. I don't have any nice example off the top of my head for you. Maybe we could do a little bit more hard mining to figure out if those kind of edge cases are happening. There's many learned components here, right? So one is your failure classifier needs to be reliable. If your failure classifier is a little unreliable, it can start giving you wrong signal about your imagination, even with a perfect world model. Then there's an additional problem where, like, even if you have your perfect failure classifier, but your world model hallucinates, you can get the wrong signal too. So I would not be surprised if there's weird interplays between those two models that might be imperfect on their own, that together do something similar like this. In practice, we haven't found a lot of that yet, but we're just at the beginning. So we're trying to stress test a little bit more and understand exactly what you need.
Yeah. I wonder if you mentioned the adversarial
Mhm.
training, but I wonder if that would.
Yeah, we're thinking a lot about that extension. Exactly. Yeah. I think the trick is that it's really hard to know how to pose adversarialness in high dimensions. Yeah. So we're thinking about that. If you want to talk more, I'm happy to as well. Yeah.
Yeah, that's what so I was just wondering, did I get it correctly? So we are using safety filter to block those unsafe actions. Can we also predict what would be the safe action in this space?
Yeah, so it's not just blocking. When we override the teleoperator, we're not just saying you cannot act, we're actually overriding it with the safe action. So sometimes the safe action is to stop, sometimes the safe action is to slow down. And that's what you see when the student was shaking the bag. It's not stopping him, it's just slowing him down. And so it's because the safety filter co-optimizes the safe policy and the safe monitor. Oh.
Yeah. Please go ahead.
Great talk, Andrea. Thank you so much for keeping us excited and awake this early in the morning. So I was wondering how your models like distinguish between like costs, which are generally considered like softer, and constraints that are harder. So I can imagine that there might be some forms of behavior, however undesirable, that are still kind of tolerable and acceptable, and others like the robots, for instance, entering the pool that are just a hard no. So I was wondering how the model can distinguish between the two.
Yeah, I mean, I think this is an engineering question. It's a designer question for us, which is like, what do we think are hard constraints versus soft constraints? And I think that this is a key difference between, for example, AI safety as it's instantiated in a lot of large language models, where typically you talk about something like alignment, which is precisely a soft penalty, versus safety critical control, which is very focused on constraint satisfaction. I think we still have more to do to figure out how to, like, what is the right kind of problem to model with each. My philosophy on when you choose which one is on how hard it is to undo. So why do we say dropping into the pool is a hard constraint or colliding is a hard constraint? It's really hard to undo that. Similarly, like if I tear a bag, it's never going to be the same. It's very hard to undo. If I spill a certain chemical on the table and it stains my table, it's really hard to undo. But some things are easier to undo, and maybe those are things that you can start talking a little bit more in the alignment language and in the preference space. That's kind of my philosophy right now.
Cool. Thank you.
Yeah.
Yeah, great.
Thanks for the great talk. So one thing I really liked about your work is that you went in a crazy high-dimensional space compared to all the previous work on safety. I mean, you went from dimension 16 to 100 or something.
It's 512 now, yeah.
And so I really liked your last slide on this idea of using uncertainty, because you're going to have uncertainty
huge
in
uncertainty.
such a high-dimensional space.
Yes.
So that I think that's a very nice idea and a critical component of your framework. I was just curious about how do you get this uncertainty estimation? Because typically neural networks don't give you that.
Agreed.
Are you using some generative models for getting the uncertainty?
Yeah, so I'll tell you a quick take on how we do it, but if you want to find me later, we can also talk more details. The take is the following. So you have a world model, and what you do is you train an ensemble, like a lightweight ensemble on top of this. And then what you do is when you look at the disagreement of the ensemble as your uncertainty measure, but we have a specific form of disagreement that lets us, as much as we can, disentangle aleatoric uncertainty from epistemic uncertainty, because the latent dynamics model fundamentally is stochastic, and we don't want to safeguard against stochastic transitions that are just inherent in the world, right? Only those that are uncertain. And so what we do is we use a higher order version of like Jensen-Shannon divergence to kind of disentangle these two. And then once we quantify the epistemic uncertainty this way, we have a small post hoc calibration procedure where what we do is we have a few held out in distribution trajectories that my model has learned to predict. And I'm going to use this along with a technique called conformal prediction to find a good threshold to discriminate in and out of distribution imaginations. And so essentially the guarantee we can give you when it comes to uncertainty quantification in the imagination is like a recall guarantee. Like with high probability, I can tell if I'm imagining things I have seen before. And then you can use the inverse of it as a proxy for the safety constraint. You don't get the guarantee technically on the complement, but it works in practice. Mm-hmm.
So thanks a lot. Very nice talk. I was wondering, can you handle different shades of failure?
For example, I got out one skittle, which is
Yeah,
bad, but not so bad, 2, 3, and well, the failure is all the skittles.
I love that question. Yeah, my student, when he was training this, he had to kind of fiddle a little bit with what the threshold is. I think it's still an open question. I think basically it comes down to how you shape your failure classifier and how you shape your value function. So what do I mean by this? In typical like first principles reachability, all the level sets of the value function are interpretable. And they're essentially giving you different amounts of like conservatism about how pessimistic you want to be. And you can take these slices. If my value function was well formed, then I could maybe do the same thing where different slices give me kind of these different levels of conservatism about how many skittles pop out. In practice, we don't find these nice level curves right now with our paradigms. That is because of some of the ways in which these models are shaped, some of the ways in which they're trained, and we have some work thinking about how to get them to be a little bit more regular so we can start taking these different slices and adjusting, okay, are we upset with just one skittle, 2 skittles, how many? But it's a frontier. Yeah. Yeah.
Hi, thank you for the great talk. So I had a more like general question. Like drawing like an analog to like the LLM space, like usually you have like really strong base model and like recent work that doing like some sort of like, you know, RL style stuff to have like really like interesting like the error recovery and like reasoning on top of the base model. So also like there are like really large like VLA kind of models recently like Pi0 and all that kind of stuff, which show like some sense of like very like, you know, big error recovery. So yeah, just like a more general question, do you think like there's like a way that we could do this by scaling these base policies and like get around this like world model training stuff and like
Okay, I love this question. If you want to hear me talk more about this question, you should come to my talk later today in the Human-Centered Robot Learning in the Era of Big Models workshop, where my talk title is What Can Robot Safety Learn from LLM Safety?
Okay.
So that might be intriguing to you, but let me give you the quick take here, which is I think that even if you look at, for example, LLMs as the best example of the kind of model everyone is trying to train with like Pi0, it's the same exact architecture, same exact training objective. Nothing is different there except the type of data and the consequences are kind of different. And there's, of course, certain quirks in embodiment versus not. But if you look at the history of LLMs, first, they were trying really hard to just get the base model to be interesting. And then what was the big advancement in GPT 3.5? It was alignment. It was like RLHF. It was guardrails. That's what started to like really pop up. And so if we believe that we're going to be successful in the same way in robotics, it's just a matter of time before we're returning back to these kinds of principles, but having to scale them up from these frontier models.
Yeah, thanks. Thank you.
Yeah, maybe, yeah.
Okay.
Yeah, let's send the Andrea.
Hi everyone, my name is Vikas Dhiman. I'm one of the organizers, and our next speaker is Li Zhang. So we invited contributing talks for recent PhD graduates or about to graduate PhDs. And Li Zhang is a PhD candidate in the Hong Kong Institute of Robotics and Thrust of Robotics and Autonomous Systems within the Systems Hub at the Hong Kong University of Science and Technology under the Guangzhou pilot scheme. Before that, he worked as a senior engineer at XAG. The associated trajectory replanning algorithm and safety backup policy have been used in over 50 countries and regions that he developed. Currently, he is a visiting scholar in the Robotics Institute at Carnegie Mellon University, working with Professor Cheng Li Liu. His research interests include robotics, autonomous vehicles, motion planning, and safe learning-based control. And I make him a co-host. And you should be able to share your screen already. Okay, so everyone can. Okay, so let's give applause and welcome to.
Yes, thanks for your kind introduction. Hello, everyone. I'm Lei Zheng. You can also call me Zach. Today, my talk is concerned with towards real-time safe optimization for autonomous vehicles under uncertainties. To begin with, let me briefly introduce myself. I'm currently a PhD candidate in HKUST, and I'm also a visiting scholar in CMU. And before my PhD study, I was working as a robotics engineer in a agricultural technology company focused on high-speed navigation and planning. And before I leave this company, the algorithms, specifically the navigation and decision-making algorithms I developed, have been utilized in over 50 countries and regions. So the mixed experience of industry and the research have really shaped my understanding for safety critical systems. So broadly speaking, my research is always focused on safety, from UAV to mobile robot, manufacturing, humanoid, and autonomous driving. Specifically, during my PhD study, I was working on intelligent transportation systems. Intelligent transportation systems, especially the autonomous driving, hold the promise of improved safety and convenience in our daily life. One of the core requirements is to safely and efficiently navigate to their destination with high task performance. However, it's a very difficult task, especially under dense and dynamic traffic. And the efficient navigation involves different requirements, such as task optimization and interaction. When it comes to the task, it must be accurate. And the optimization process should be fast enough to support real-time replanning, and the interaction has to account the motion uncertainties of surrounding agents. So, considering all of these factors, can we enhance the overall safety and enhance the travel efficiency is what I was focused on. Imagine that when you are driving in a very dense and dynamic traffic, there may be some uncertain behaviors of surrounding agents and will tend to a collision. And specifically during a partially observed environment, when you cannot accurately perceive the environment information, it may also tend to a collision. And one potential policy to address this is use a very conservative policy. As you can see in this left video, this vehicle will stop in this occluded intersection and wait all the surrounding vehicles to pass, and then it accelerates past this intersection. But this is too conservative, right? Can we strike a balance between safety and efficiency? Because we want to guarantee the overall travel efficiency. But it's a very difficult challenge. One of the core challenges behind this is the existing of uncertainties. There are mainly two types of uncertainties. The first one is what we call from the system level, like the imperfect system model, like the unknown parameters. Another one is from the environment, like the localization of the position and velocity of obstacles, and the change condition of the road, and the unknown intention of surrounding agents in dynamic traffic environment. So considering all of these challenges, during my past research, we have addressed this from different levels, from the robust probabilistic and use different approaches, combine control theory and machine learning. And during all of these works, we have to consider two factors. The first is what we call the feasibility, because you have to strike a balance between safety and efficiency, right? And you have to also account other constraints, as the kinematics, the control limits, and there are a lot of multi-objects to be traded off. How can you optimize your approach, your proposed problem very efficiently with solving feasibility guarantees? Another one is what we call the safety issue, because you have to account the possibility, like the safety conditions. And what we aim to do is to design very efficient policy that provide like robust safety, high efficiency, solving feasibility, and robustness to environment at the same time. And during my past PhD study, I was initially working on single trajectory optimization, focused on safety and real-time performance. And considering the decision-making and the trajectory optimization, we have extended the single trajectory optimization to parallel trajectory optimization. So why do we need to use parallel trajectory optimization? Because during autonomous driving tasks, there are always different
decision variables. Like you can keep in a current driving direction, or you can change your driving direction to a different line. So this motivates the parallel trajectory optimization. We further infuse the feasibility to the optimization and to further enhance the proposed approach to handle some like sudden obstacles and out of distribution scenarios. We extend to like a tree structured branch for parallel trajectory optimization. And finally, we focus on safe learning control to combine machine learning and control theory for safety recovery. And by doing so, we can design policy that offers high computational efficiency, safety guarantees, feasibility, and robustness at the same time. Well, let's dive into the technical details. Before we dive into the like mathematical details, let me show you the outline of today's presentation. In the first part, I will present barrier-enhanced safety planning for autonomous driving, and then we will focus on safety recovery. And finally, I will conclude my presentation. Well, let's turn our eyes to the first part, barrier-enhanced safety planning. We believe the motion of this vehicle is influenced by the following factors, such as its geometry and kinematics, the unknown intention of surrounding agents, and the traffic rules, like the road boundaries. So considering all of these factors, you can make different decisions and planning. Like you can perform like a lane change to the left-hand side or to your right-hand side, or maintaining your current driving direction. So this problem is very hard to be solved. Can we efficiently solve this problem? To further solve this problem, like this decision-making and planning problem, it can be further categorized into two sub-problems. The first problem is how can we efficiently generate parallel trajectories that is safe, feasible, and very efficiently. Another problem is how can we select the optimal trajectories from all of these candidate trajectories for the ego agent to execute. During the parallel trajectory generation, as I mentioned before, each local trajectory is not only feasible and safe, but it also represents a discrete decision variable. Like take the red trajectory, for example, it's not only a safe trajectory for the ego agent to execute, but it also represents like a decision maneuver, like turn left. So by doing so, we can simultaneously optimize the desired trajectories with decision variables to integrate decision-making and behavior planning. Well, let's consider this in more detail. Parallel trajectory generation. As we have mentioned before, we have to enhance the overall safety rate. A powerful tool, as just Andrea introduced before, is to use control barrier function, specifically the barrier function. So what is barrier function? Barrier function is kind of like an airflow function, but its stabilized region is not an equilibrium point. It's like a safe set designed by this function, hx. What properties the barrier function has? It means whenever your system is out of this safe region, it can asymptotically coverage to this safety region. And once your system is already in the safety region, it will always keep in the safety region for the environment. So with this safety barrier function taken into consideration, we can formulate the parallel trajectory optimization into a barrier-enhanced homotopy trajectory optimization problem with the consideration of kinematics, feasibility, and performance. But this problem typically is a nonlinear problem. It's very hard to be solved in real time. How can we deal with this? How can we enhance the overall solving efficiency? In some extreme conditions, it will involve like over 1,000 variables and constraints. A powerful tool is to use ADMM. What we have done is to leverage ADMM, over-relaxed ADMM, to do problem decomposition, and by doing so, it can decompose the original large problem into several sub-problems. Let's consider this in more detail. So over-relaxed ADMM can solve the original very large problem by decomposing it into several sub-problems. Take the safety variables, for example. During optimization, we can always only focus on one type of variables, like on the safety variables. And another variables is fixed. And by doing so, the original large problem can be solved by a series of very low-dimensional problems. And to ensure the feasibility during the solving process, we introduce slack variables. And whenever the acceleration and the velocity is out of your desired boundary, we can use projection to project the velocity and the acceleration into its desired boundary. And by doing so, we can enhance the overall feasibility. And one last question is, how can we ensure each sub-problem is convenient and converged? And we use few variables update to converge each problem. And by doing so, we can obtain a lot of local candidate trajectories for the ego vehicle. And another issue is, how can we determine the optimal trajectory for the ego vehicle to execute? With the consideration of the goal tracking accuracy, literal deviation from its target-driven direction, safety, driving comfort, and consistency, we can select the optimal trajectories for the ego vehicle to execute. Now, let's see how it actually works. This is for high-speed navigation tasks, and the red ego vehicle has to navigate through this dense traffic environment. And the relative speed between the ego vehicle and the obstacles is very high. So it can simultaneously optimize multiple candidate trajectories and select the optimal trajectory to execute. And by doing so, it can safely and efficiently navigate through such dense environments. And we have tested the proposed approaches in both static and dynamic environment. Use different data sets. And you can scan this QR code to get more information about this project. And during this whole process, we have an assumption that is the ego vehicle can accurately get the real-time position and velocity of surrounding agents. But this is not possible in every conditions, right? Especially when it comes to perception uncertainties. And in such conditions, you cannot accurately get the position and the velocity information of surrounding obstacles. How can we handle this issue? Because in such conditions, if you switch between local trajectories, especially for such a high-speed autonomous driving tasks, it will compromise your overall driving experience, right? Imagine that if you are currently driving in this direction, but your decision requires you to perform an abrupt non-change, it will compromise your overall driving experience. Another problem is if you switch between local trajectories, especially under perception uncertainties, it will cause a safety issue. So can we enhance the overall robustness to perception uncertainties? This motivates to the contingency parallel trajectory optimization approach, which offers highly computational efficiency, safety guarantees, and solving feasibility at the same time. How can we realize this? A good way to realize this robustness is use trajectory combination. As you can see, there may be obstacles that is misdetected or be occluded by other vehicles. But during optimization, we can simultaneously optimize several candidate trajectories. And all the trajectories will share the initial trajectory segment before a branch point. It means in a receding horizon planning manner, the next step is shared by all the local trajectories. And if you switch between trajectories, it will not cause like a safety issue. Because during other, like this red trajectory, we consider there may be a sudden appear obstacles. And by doing so, we can enhance the overall robustness by use consensus optimization. Let's consider this in a more specific example, a contingency events. So what is contingency? Contingency is a future events. This is possible, but cannot be predicted with certainty. Like if you navigate through an occluded intersection, there may be a sudden appear child or human drivers. And in such case, you cannot access the formal history trajectories of this child or this human drivers. And how can you enhance the overall safety under such contingency? A good example is navigate through a blind intersection or overtake a truck. Or sometimes when you are doing a racing task, the road condition is immobile. So considering such contingency events, how can you enhance the overall safety and efficiency? As we have mentioned before, we have mentioned before, you can use a very conservative behavior, like in this video. You can stop and wait all the obstacles to pass by, and there is maybe no contingent events in this case, and you pass by this occluded intersection, but it will compromise the overall efficiency rate. What we want to do is to strike a balance between safety and efficiency, because we do want to avoid over conservative driving behaviors. And how can we realize this? This involves two requirements. The first requirement is to account the potential contingency. A good example of this is to navigate through a occluded intersection. And in this case, you have to account the influence of occlusion to strike a balance between safety and efficiency. Another one is during dense and dynamic obstacle environment. This is interaction heavy environment. You have scale your algorithms to handle such dynamic interaction and to enhance the overall efficiency. Before we take this in more technical details, let me quickly recap existing approaches. To ensure safety under contingencies, as Andrea has introduced before, we can design like a safety filter or a safety backup policy, like fail-safe policy. And whenever it detects a potential failure, it can stop the vehicle, but this is too conservative. And to address this issue, you can adjust your heading angle to maximize your perception region. But during this whole process, it will compromise your motion consistency. Because when you navigate through a occluded intersection, a very experienced driver want to suddenly change its driving direction, right? It will adjust its speed along its current driving direction. And there are also some problems to handle this issue through partially observed MDP and contingency planning. But this process involves to account different constraints and it is extremely time consuming. So how can we handle this problem? A good approach, as I have introduced before, is use tree-structured parallel trajectory optimization. And in this case, we can simultaneously optimize two trajectories. One is for exploration, one is for safety fallback. But during execution, all the two trajectories will share the initial trajectory segment. It means when it executes the next control steps, it will consider all the possibilities of two trajectories. And we use reachability analysis to guide optimization for two trajectories. And by doing so, we can formulate it as a biconvex optimization problem with consideration of control effort, goal tracking accuracy, state constraints, kinematic constraints, safety, state, and control limits like the acceleration boundary and the jerk boundary. And the driving consistency value is we have introduced before. But this problem is very large, but it indeed have some good properties. Like if we fix on some variables, like fix on 6 CY, and we only focus on the theta, which is related to heading angle of these autonomous vehicles. And this whole problem will become very small size problem. And we can solve it very efficiently. By doing so, we can leverage consensus ADMM to do problem transformation and solving this problem very efficiently in a routing optimization way. And by doing so, we can achieve safe and efficient navigation for the Eagle vehicle. Let's show you a demo of how it really works. This is the Eagle vehicle navigates through an occluded intersection. There may be a sudden appear obstacles. And with the occlusion aware contingency planner, it can enhance the overall efficiency. But what will happen if we don't account the occlusion? As you can see in such scenarios, there are some obstacles that will suddenly appear and you cannot accurately detect. It will turn to a collision. And if you use a very conservative behavior, like very conservative nonlinear MPC behavior, it will wait and then pass by, and this will compromise the overall efficiency. And how it really works on some hardware experiments. And we have deployed it in an autonomous vehicle. This is an Eagle vehicle. And at the initial state, it cannot perceive the occluded obstacles, but there exist some dynamic obstacles. And it will always prepare for it. And after pass this intersection, it will accelerate. And another thing we have mentioned before is the scalability of these approaches to dense and dynamic traffic environment. So let's say how is the real-time performance. We have increased considered obstacles into the proposed approaches. As we can see, with the increase of obstacles, the maximum optimization time will not increase when the number of obstacles is surpassed like 5 obstacles. It means the proposed approaches can very efficiently and process only the relevant constraints during the overall optimization. And by doing so, it can simultaneously optimize over 1,000 variables and over 1,000 constraints simultaneously. But during autonomous driving tasks, it always like a structured road conditions. Can these approaches be extended to handle unstructured road conditions? The answer is yes. We have tested the proposed algorithms into occluded unstructured scenarios. And in this case, this eagle vehicle has to navigate through occluded environment, and there may be dynamic obstacles cannot be observed. How it really works? Let's see a simulation video first. And at the initial stage, it will simultaneously optimize several candidate trajectories. But all 3 trajectories will share the initial trajectory segment to enhance the overall efficiency. It means whenever trajectory you choose, and the transition is very smooth. And each trajectory can account different scenarios. Let me show you in more detail. And during the initial stage, as you can see, this green trajectories will consider there may not be obstacles, but this blue trajectory will account there may be a high-speed dynamic obstacles. And this red trajectory will account there may be low-speed obstacles. But during execution, as all the 3 trajectories will share the initial common trunk, it means the next step is shared by all the 3 trajectories. Whenever it switches between trajectories, it will be very smooth and will enhance the overall driving consistency. And once it has more accurate perception of environment, all these 3 trajectories will convert to 1 trajectory. This is kind of like a delay decision. But during optimization, the next step will consider all the desired object of potential contingent events. And let's see how it really works. This is a eagle vehicle. It can efficiently account the sudden appear obstacles and ensure safe navigation. And we have also tested the proposed approaches in high-speed driving tasks with the baseline comparison with different approaches. And with the proposed contingency parallel trajectory optimization, it can very efficiently navigate such dynamic traffic environments in different tasks. As you can see, the batch MPC without trajectory combination will switch between local trajectories and switch between different driving direction. And based on the proposed contingency BPHTO, it can always drive very safe and efficient with driving consistency. And when it comes to non-change tasks, and the overall driving is more smooth. And we also investigate the influence of different consensus steps during trajectory optimization. So far, we have talked about trajectory optimization to handle some contingency events. But one thing we really care about is safety recovery. Because in some cases, like when you encounter some very aggressive, like human drivers, it can cut in your current driving direction, your connected cruise control. And how can you recover your safety? And during high-speed driving, and you cannot accurately get the model of this vehicle. How can you take these uncertainties into consideration? This motivates to the safety recovery. We aim to recover the system from unsafe state, but unsafe doesn't mean a collision, to a safe state. As we have introduced before, the barrier function is a very powerful tool to enable the safety recovery. But when it comes to the model mismatch, like the uncertainties, how can we handle this? And how can we safely and efficiently recover safety? And this model mismatch is usually bounded and corresponding to some distributions. And this problem can be further categorized into two sub-problems. The first problem is how can you adapt to uncertainties? Some approaches like the end-to-end learning and deep learning are usually unexplainable and quite slow. How can you efficiently and fast adapt to the model uncertainties? Another sub-problem is once you adapt the obtain the uncertainty quantification, how can you recover safety? And to handle the first issue, we use incremental learning and Woodbury matrix identity to decrease the complexity of Gaussian process from ON3 to ON2. And by doing so, we can efficiently model the model uncertainties. And you can scan this QR code to get more information. And finally, we can use quantified uncertainties to design a stochastic controller to enable safety and efficiently recovery for the ego agent with fast computational efficiency, feasible solving guarantees, and uncertainty modeling at the same time. And we have tested it in a connected cruise control task. When the initial distance between the ego agent and the front vehicles is larger than its desired boundaries, it can asymptotically rapid coverage to this desired boundary. And the overall computational efficiency is very high, as you can see in this table. So basically, in today's presentation, I have introduced my PhD study from single trajectory optimization and the motivation of why we need to use peri-trajectory optimization. From no coordination batch structure to coordination branch structure, and finally we introduce safety recovery to design a computational efficiency, formal safety, feasibility, and robustness guarantee at the same time. And during my future work, one ongoing research project is account the influence between human, robot, and systems. Because currently, during a lot of motion planning tasks, you can always predict the motion of surrounding agents and plan a safe and feasible trajectories. But sometimes, actually, when it comes to dense traffic environment, when you have to interact with humans, and the motion of the ego vehicle will also influence the motion of surrounding agents. This is like a closed loop manner. How you account such influence? And the typical safety module cannot account such bi-directional influence. And in some cases, as we have mentioned before, in some contingency events, the agents might not behave as you modeled. How can you handle such scenario? And during interaction, interaction have scenarios with a lot of obstacles that may be computationally intensive. How can you handle this issue? Can we design a real-time interaction or real safety field to account for such interaction in a dense obstacle environment? This is one of my ongoing projects. Thank you all for your attention. And I'm currently looking for postdoc opportunities. If you are interested in my work, or if you think I'm a suitable candidate, you can feel free to reach me out. And in the afternoon, I have a post section, and then we can discuss in more detail. Thank you all of you guys.
Thank you, Lee. We have time for one question from the audience. Yeah, please.
Thanks for a great talk. So in the work that you presented, where you have the consensus part for the branching time, I see it's changing adaptively, or is it fixed?
Yeah, actually, this is a very important question.
Yeah, maybe the follow-up question: if it's adaptive, how do you find that branching time?
Yeah, currently during my research project, we fix like a branch point. Yeah.
Yeah, but technically, depending on the scenario, it has to be either changing in real time. So, do you have any idea how to do that?
Actually, in my ongoing research project, we investigate such mechanisms. We can use some scenario quantification. If you quantify a scenario that is highly uncertainties, and maybe you can increase your branch point. But in some cases, as I have introduced before, if you only increase your branch point, like the performance may not be good as you expected. Because in some cases, you have to always like investigate a suitable like branch point. But this is actually a very important thing to be done. Yeah.
Thank you. Let's thank the speaker.
Thank you.
Yeah, you can talk to him offline.
Yeah, yeah. You can discuss with me after.
Yes.
We'll have a coffee break.
Yeah,
now.
we have a
Resume
coffee.
at 11. All right. It's reward.
Are you on logged into Zoom?
Not yet.
Okay. Yeah, it's on the top of the link is on the top. Just click together. Okay, so you okay, I'll make you co-host and you can mute. So the audio is going to come through this computer and this mic.
Okay.
And so you can mute yourself and mute the speaker as well.
You should try to turn this camera.
One quick slide to my slides.
Does she need a connector or something? Okay. Okay. That's nice. Thank you. Where do you find it? See.
Thank you very much. Very nice.
Hi, everyone. Welcome back from the coffee break. So we'll continue our session. Our next speaker is Nechme Oze. Nechme Oze received her BS degree in electrical and electronics engineering from Boğaziçi University, Istanbul in 2004. Her MS degree in electrical engineering from Pennsylvania State University, and her PhD degree in electrical engineering from Northeastern University, Boston in 2010. Between 2010 and 2013, she was a control and dynamical system postdoctoral scholar at the Department of Computing and Mathematical Sciences at California Institute of Technology. She joined Electrical and Computer Science Department at the University of Michigan, Ann Arbor in fall 2013, where she is currently the Chen Luan Family Faculty Development Professor of ECE and an Associate Professor of EECS and Robotics. She is a part of the Michigan Controls Group and affiliated with the Michigan Institute for Data Science and Michigan Institute for Computational Discovery and Engineering. Let's welcome Nechme.
Thanks to organizers for organizing this nice workshop and timely workshop, and thanks for inviting me, and thanks for coming to the talk. So I'm going to talk about learning specifications in general, not temporal logic specifically, possibly from multimodal data from humans. And I don't want to motivate this because probably we all know in this room, we have all these autonomous systems. We want safety guarantees for the systems and some notion of test completion. So we don't want our robots to sit in there just for the sake of being safe. And I am coming from a formal methods background to some extent, and there are many different ways of doing formal methods for autonomous systems and robots. So you have verification, you build the system, you try to verify whether it's correct or not. You have synthesis where you try to specify what the system needs to do, and you try to make sure you synthesize a decision-making logic that satisfies your specification. You have falsification where you try to generate adversarial examples to poke and find the defects in your system. And there are various different types of falsification that combine synthesis and falsification as well. But the elephant in the room here is the specification. So no matter how you want to test your system, you really need a specification to test for correctness. And I will argue sometimes learning people go wrong about that. They start with learning, and like once they train everything, the objective comes afterward. They try to make up metrics and say, oh, in this metric, my system works well. In this metric, my system doesn't work well. But I think more principled way of doing this is like come up with the specification first, then do whatever learning design you want to do. Then in the end, you have something to test and verify against your design. So I will start with an example of adaptive cruise control because I worked on this a lot. And I will argue some of the things that maybe we are not doing right in educating engineers and robotics. So if you want to design a robot adaptive cruise control, again, you need two things. One is the mathematical model for your system. This is your vehicle dynamics. And if you go to grad school, even undergrad in mechanical engineering, you can find classes on dynamical systems, how to model these things. And like if you go to grad school, you will get, if you're in aerospace department, you will get a course on like aerospace dynamics. If you go to mechanical engineering, you will have courses on automotive dynamics. You can have a lot of courses to learn how to do the left part. But you also need a specification, formal or informal. And in most of our curricula, there is no way of teaching how to specify things so that you can verify and check in the end. So we decided to do some control synthesis for adaptive cruise control. And we spent some time modeling vehicles. We have a test facility at the University of Michigan. We got data from real vehicles. We developed our model. Then we needed to write a specification. And we said, okay, adaptive cruise control, how complicated this could be. And our first attempt at a specification, not formal, in natural language. If there is no car in front, go at a set speed given by the user. And if there's a car in front of your ego car, follow the lead. So this was our first attempt, and we tried to like write this in logic and everything. My question is, would this work? There's something fishy about this specification.
There will be sudden changes. There could be
changes, but your model can capture the changes to some extent. And the models we developed were hybrid models where like cars are coming in and going out and cutting in. So the model was pretty complicated, but there was still an issue with the specification.
Specify any distance.
So distance yeah, distance is not there, but in our actual specification we wrote there was a desired distance as well. That wasn't the biggest issue that we had.
Maybe because you say follow the lead car, you may exceed any speed limits.
Exactly. So what happened is that we synthesized the controller with this. It was correct with respect to the formal version of the specification. And this is the behavior we observed. A car cuts in, you start following. The guy in front of you exceeds the speed limit. Our car was like still following, going like, if it's going crazy, we are going crazy. So it's really tricky to write specifications. Actually, what we did in the end is like 3 people with PhDs sat for 2 weeks, try to figure out how to write the right specification for this thing. We went and read this ISO standards and SAE standards. And in the end, we wrote something like adaptive cruise control. Simplest, one of the simplest things you can do. If you want to write a formal specification, it might get really complicated. So this motivated me to think about like, is there an easier way of coming up with specifications? Because I think specifications are undervalued, and I am so happy that specification appears in the title of this workshop. And we thought, okay, maybe we can learn specifications instead of trying to come up with these specifications. Or we can start with a partial specification and complete it with some feedback from humans. It's very common in control that you go from data to models. But as I said, if you want to design a controller or decision maker, you need both model and the specification. And we said, okay, we want to maybe learn specifications. And learning specifications in these formalisms is useful because you can use them in control design. You can also use them for monitoring your system for correctness. And you can use them for anomaly detection. And you can generate safety filters for by using these specifications. And typically, once you have this specification, you can go and design a new controller in a new environment with this specification. So it also gives you some generalized approach. And the most common way of doing specification learning, or the closest thing, is maybe learning from demonstrations. And I will come back to that. So there's another thing that we asked ourselves, and I will use some of those in later parts of the talk. What is the type of feedback we want to get from humans? So here are the forms of feedback we thought about. One is demonstrations. You get the human do whatever task you want to do. And in the context of driving, maybe you want the person to drive on the highway. And this is good in the sense that you get really naturalistic behaviors out of it. But it might not fully cover preferences and humans' actual intent in the following sense. One thing we noticed, and this is also like captured in the literature, in the context of driving, if you are driving yourself versus if you are being driven by someone else, your preferences differ a lot. This happens a lot. Like I always argue with my boyfriend. He thinks I drive so aggressively. I think he drives so aggressively. But like whenever we are on the passenger seat, since we don't have control, maybe we are more cautious and we want to be less aggressive in our maneuvers. And this is what we would expect from an autonomous vehicle as well. If you are driving, if you have the control, you can tolerate a bit more aggression, but if you are on the passenger seat, you expect slightly different. So another form of feedback is asking questions. Maybe you can ask the user to describe their preferences about how they want to drive, if they are going on a highway, how they want to overtake. But this can be very informative for us as humans, but this is maybe not so easy to mathematically process. At least it wasn't easy up until 2-3 years ago, but maybe there's some hope to bring in some of this natural language feedback through the use of LLMs these days. And there's one other issue with asking questions is when you do a task like every day, you don't typically reflect on how you do it. So I don't really think about and articulate how I want to overtake a car. I just do it because I do it all the time. And maybe one kind of form is asking pairwise questions, A/B testing type thing, where you show the user two different behaviors and you ask which one they prefer. This turns out to be easy to process for humans. And it has been shown to cover different types of preferences. Of course, you need to do it scenario by scenario. And I will come back to these different forms of human feedback. But in the rest of the talk, I will try to answer 3 different questions. So the first question I will try to answer is, can we learn complex specifications from well-curated but small amount of data? So this is opposed to machine learning, where you have tons of data. I will try to motivate some instances where you cannot afford to have too much data, but maybe you can afford to have well-curated data. Can we learn complex multi-stage specifications in this sector? The second question I will try to answer is, can we again learn these complex multi-stage specifications with large amount of data coming from populations or methods? But since the data comes from a population, you have lots of stochasticity in the data. And how do you handle this stochasticity in learning specification? So that would be our second question. And the third question I am quite excited about, and I think that's the next frontier in safe learning, is how can we do safe personalization? Because as we saw in Andreas' talk, there are many different ways of being safe. So you can act in many different ways, but can still be safe. If a specific person has one preference among those safe options, how do we capture that preference? And how do we personalize our machines to needs of individuals? Because if we are only learning from the masses and populations, we are probably ignoring smaller groups that might not be reflected in your data sets. And we might not be developing the best possible machines out there. Okay, so these are the questions we will try to answer. Now I will start talking about individual ones. Any questions so far? Okay, first setting. Can we learn complex specifications from well-created small amount of data? And here I want to emphasize small amount of data and think about a setting like this. You are a small manufacturing company. You are maybe producing, I don't know, 1 million pieces at most a year. And you buy a robot arm to automate your manufacturing process. You cannot really afford generating 1 million demonstrations. That's the whole thing you are producing anyways. You can really demonstrate a few times if you want this process to be efficient. And if in the next cycle you are producing a slightly different piece, you want to be able to give a few more demonstrations and learn how to do that piece. So if we want a small manufacturing operator to adopt some automation, and if we want to help them specify their needs with demonstrations, we really need to figure out how to work with small number of demonstrations. And you can ask them to be precise and do their demonstrations well, because they can afford that. But you cannot ask them to say, oh, give me 1 million demonstrations. Okay, so this is the setting. And again, here after generalization, maybe they will change their robot arm and they still want to be able to produce the same piece. So those sorts of generalizations are important in this. Okay, so what is the de facto thing people do? It's learning from demonstration. So we all know specifying tasks by hand can be challenging. And maybe we can get some demonstrations and learn a policy that completes the same tasks in similar environments. And we can do inverse reinforcement learning or inverse optimal control to learn a reward instead of a specification to capture what we want to do. So typically in inverse reinforcement learning, the demonstrator solves an unconstrained optimization problem. So they solve a problem of this form, and we come up with some known features to represent this reward. And our goal is to see this demonstrated trajectories and to predict this parameterized reward functions parameters. Then once we learn this, we can maybe plan using this reward function, maybe in different environments as well. And this has been applied in interesting settings, and this has been shown to be successful. But what if we care about safety and what if we want to be more precise? So if you are doing inverse reinforcement learning, maybe you put some soft penalty for your hard constraints. But the problem with the soft penalty is that sometimes if you design your controller with the learned reward function, it might no longer satisfy your specification. It might start violating this soft constraint. Also, if you start mixing constraints with your optimizing objectives, it's difficult to write down your features because your features are mixing too many things and you lose interpretability. And it's also difficult to scale up to multi-stage tasks. And I will talk about multi-stage tasks quite a bit. Okay, so what can we do instead? So we thought maybe we can directly try to learn these hard constraints from demonstrations. And here's the mathematical problem that we will try to solve. So we assume this is the manufacturing company owner solves a demonstrator problem. They are minimizing some costs, subject to some safety constraints. These are known by the demonstrator, but unknown to us. And we are trying to figure out and put their specification into a mathematical form. And maybe there are also some known constraints that are known to them and known to us. These could be like your dynamics and this and that. And maybe these are some demonstrations that they gave us. In this case, I am carrying, my robot is carrying a heavy weight. There's some glassware down there, and they are trying to go over this glassware, and they are avoiding the regions where there's a risk of dropping the weight and breaking the glassware. As a learner, our problem is to find some parameters that describe the safe set. So in a sense, I am pushing this reward featureization thing to constraint featureization. I am trying to find these features that renders my trajectories that I observe or demonstrations that I observe optimal. Okay, so this is the problem we want to solve. And there are a few challenges here. So we need to distinguish between good trajectories from bad trajectories, but we don't want the human to demonstrate any bad trajectories. We don't want people to break stuff for the sake of learning something. So the main challenge is we only have good trajectories, but they are coming from a well-curated data set where the person optimized something. And the key insight here is that we can really use this optimality to our advantage to learn in this setting with very few amount of data. And the basic idea is you can invoke Crash-Tucker optimality conditions to define what it means for a demonstration to be optimal. A demonstration to be optimal, they should be feasible. So if my constraint set is the red one, this demonstration is an invalid demonstration, and this demonstration is a valid demonstration. They should satisfy stationary and complementary selectness conditions, meaning I am searching for this red ellipsoid. This ellipsoid should be such that if I move my trajectories a little bit, I am either violating my constraints or I am increasing my cost function. So my trajectories, in a sense, should capture my constraints tightly. And it turns out that once you impose these constraints in your learning, it dramatically reduces the set of valid constraints, and you can learn with very few examples. There's still some uncertainty in learning if you don't have sufficient number of examples. For example, if I have only one demonstration and if I know my constraints are these ellipsoids, all of these ellipsoids are valid, but using this optimization form, you can find a region where all your ellipsoids intersect, meaning that region has to be unsafe. And you can find a region that intersects with none of the ellipsoids, meaning that region will be safe. And this can be written by a simple optimization problem. And this optimization problem acts as a collision checker that you can use any planning algorithm. I'm going a little fast here. Here are some results. We implemented this in robotic arms. We implemented this with quadrotors. On the left, I am showing the demonstrations that we learned from. On the right, we are planning with these constraints in new environments. This was so far collision avoidance type thing, so avoid certain regions. Maybe it's the simplest thing. This can also be extended to multi-stage tasks. But if you want to have the multi-stage tasks, you need some different parameterization than parameterizing regions in your state space. You also need a discrete notion of staging of tasks. So in a sense, you are in a hybrid continuous discrete constraint space. So continuous part of the constraint captures these individual tasks, and discrete part of the specification captures the temporal aspect and ordering, sequential ordering of different things that you want to achieve. And to do this, what we did is we extend our earlier results to learn temporal logic constraints. where if you don't know temporal logic, here's a quick description of temporal logic. You have some temporal operators that describes temporal staging of your different tasks. And you have some continuous atomic propositions that gives information about the geometry of your state space. And it turns out that this can be easily incorporated into our earlier learning framework, where in the low-level part, we are trying to learn the structure of this logic formula. And in the low-level part, we are trying to learn the propositions. And I won't go into details, but all of this you can write down as a mixed integer linear program. Again, we implemented in some multi-stage robotics tasks, where in a VR environment, the task is this long thing, maybe a waiter robot trying to deliver certain things to certain people. It's grasping a soup, placing in a small box, delivering to the blue region, grasping cheeses, placing in the large box. And I think it's not delivering that one. And in the VR environment, we got 3-4 demonstrations for that. And we can just put it in a totally new environment, same test specification on a real robot, and you can synthesize controllers doing this. So the key insight here is that if you have a small number of well-curated demonstrations, you can learn the specifications and you can use that specification in new environments. Any questions so far? If not, I will move on to the second question. Yes.
About scalability, you said it's a mixed integer linear program, so does it scale with the number of demonstrations?
It doesn't scale that well with the number of demonstrations, but you don't want too many demonstrations in this setting anyway.
Yeah, but for each new demonstrations, you have a set of integers.
So if you want to scale with number of demonstrations, that's the next question I will try to answer. Again,
theoretically, the constraints are point-wise or trajectory-wise?
It could be both. So it could be in the temporal logic case, you have a time varying point-wise constraint, which is what I think you mean trajectory-wise.
So,
yeah.
So you assume that the trajectories that you have are easy.
They are optimal. Yeah, assuming they are optimal. That's what I mean by well curated or close to optimal. There could be some optimality gap that we can handle. But we are assuming they are close to optimal in terms of either path length or time. Okay, so again, it doesn't scale well with too many trajectories, but it's a setting where we don't want too many trajectories anyway. So the next setting is I still want to learn complex specifications, but now with large amount of data. And this data is coming from a population, and the data is stochastic. Either the environment generating the data is stochastic, or since I am collecting data from a large population, the preferences or objectives of this population is multimodal. So even though an individual might be very deterministic, if I see two individuals and if I combine their data, it creates some stochasticity. And I want to be able to handle this stochasticity in my learning. So this is again related to inverse reinforcement learning, but for this more complex multi-stage test. And one of the motivations that we started looking for this was designing better environments for certain tests for learning intent. And this was through a discussion with Toyota. One thing they wanted to do is the following. So they want to understand EV usage and EV charger usage. And they want to know in what type of city environments where they should place the EVs, that is not EVs, chargers, so that they can increase the usage of these chargers. And we had this toy example where maybe there's a burger joint that's very popular in the city. Maybe there's a charging station and you are trying to figure out where you put this charging station. And once you put it in different places, you observe different type of behaviors. And you try to understand these behaviors so that you can find an optimal location for placing your charging station. Again, here we are learning from populations, and when you are learning from populations, you have lots of data, and you have lots of stochasticity. And our earlier approach using KKT and optimality, assuming everything is deterministic and optimal, it doesn't work anymore. And these like non-horizon complex multi-stage tests are common from manufacturing to home robotics. If you are possibly preparing a meal, it's all multi-stage. So the question is like, what type of reward, if this is a inverse reinforcement question, what type of reward captures this? You cannot use your state-wise rewards if you have these multi-stage. So one thing you can do is you can have a trajectory-wise reward where your reward at time t depends on everything that happened so far. But this is such a complex structure that it's impossible to learn, brings in so much impulsiveness into problem, and there's no structure in it. So the question is, what is the right structure that we can represent these multi-stage tests? And the specific structure that we are using is reward machines. These are automata type structures that are very related to temporal logics. If your environment has some high-level atomic propositions, for example, maybe the rooms are your propositions and ABC are the rooms here. And if you have a patrol task that requires some order, you can write this automaton structure to represent your reward, how your reward evolves in time and the memory in your reward. And in the end, you can write down a new forward problem that combines your environment with this reward structure. And we are assuming the demonstrators are solving these type of forward problems. And there's a memory structure in what they are doing. And we are trying to learn this memory structure to understand their behaviors and intents. So the question is, how do we come up with this reward structure? Especially given partially observed policies. We are not even observing policies, we are observing some demonstrations. Okay, so here is what we did in this context. So we don't observe the policy, but we observe the different atomic propositions or different rooms the person or all the people in the population visit throughout their demonstrations. For example, this robot starts here. This is one of the demonstrations. It's walking around, and I am just capturing this high-level landmarks they are visiting throughout their demonstration. And we capture these type of demonstration, high-level demonstrations from a population of users. And we want to learn this reward structure from these type of demonstrations. So here is the key insight. This demonstration is, I said, this is a multi-stage test. There's an underlying memory structure. And we will represent that memory structure with a graph. The question is, we know nothing about this graph. So it's an empty graph. But one thing we can do is that if we can detect changes in the policy, if we can figure out if a person visits this A and B, and if they only visit B, they are doing something totally different, then in this graph, there should be two paths, one corresponding to AB, another corresponding to B, that don't go into the same memory cell, because the person's behavior changed after doing AB versus just B. And this gives us a negative example. So in this case, this A and BA, AB and B should not go to the same memory cell of my reward machine because people are behaving totally differently in their policies when they observe these things. So the question is this sufficient information? Getting this negative examples, sufficient information for learning? And it turns out that if you observe trajectories up to a certain length, these negative examples is sufficient to learn your reward machine exactly. Again, we applied this to some tasks. This is a sequential power block stacking task. We have some demonstrations. We learn the reward machine, then you can go and plan with that reward machine in new environments. For learning, you can also do it in more continuous environments. Also, this is a fun example if you are really trying to understand intent. This is some real mice data set. The mice was deprived of water for a while. So there's a population of mice that's not deprived of water. There's another population that's deprived of water. They are left in a maze, and there's a water fountain in the maze. And we can just learn for the water deprived mice, you get this reward machine where it prioritizes to go to the water. And hopefully you can use these ideas to maybe learn the intents and goals of people to design better environments for people and robots. And this is the final question that I want to answer. Can we do safe personalization with incomplete specification? And most of our systems are very close to humans. And I think this is kind of the next frontier, as I said, in safe learning and control. Can we learn and personalize for individuals? Again, we won't have too much data if I am trying to personalize it to a specific individual. I don't want to bother that person too much. I want to get a few amount of data from them. And I have this safe set of behaviors, and I want to refine my safe set of behaviors into something that's going to please the human. And typically, the specifications that we have are also incomplete, and learning from humans are also useful in this incomplete specification set. This is related to what Andrea was saying. So if I write my specification, there's a state space that I have in mind, and there are certain propositions or safety specs that appear in my specification. But if my state space doesn't capture everything the human cares about, that specification won't be able to capture everything that the human cares about. So here is the setting that we will be working on. Here we will start with a specification. Someone gives me a formula or specification that captures safety broadly. And we know there are many methods for getting this specification and generating safe behaviors. What we want to do is within these safe behaviors, find the one that best describes the preferences of the person that I am trying to personalize. Again, preference learning is the common alternative here. The setting is that human has some unconstrained optimization problem in mind. We give them some pairwise comparison questions, and they tell us in their unconstrained optimization problem, which demonstration has better costs. But the problem here is that this does not take into account safety at all. We want to do the same thing with safety in mind, where we want to constrain preference learning with safety so that we can both personalize and guarantee safety. Okay, so here is the problem that we will try to solve. Now we are given a temporal logic formula. This is a very simple specification. For example, if you are driving, this is something like, don't run the red light, don't hit the pedestrian, or something like that. It doesn't capture all the intricacies of driving, but it captures the rule that you always want to satisfy. We are also given some preference data that human tells you, I like this versus this. And we are trying to learn a ranking function, very similar to preference learning, such that this ranking function, we want it to be as expressive as possible. It captures most of the preferences or all of the preferences of the human. But we have this additional safety rule. We want to make sure this ranking function never ranks a rule violating behavior above a rule satisfying one. So it's kind of a constrained preference learning problem. It turns out that you can use weighted temporal logics. Instead of your specification, you can now consider a weighted version of this specification. And if you pick your weights in a certain way, you always guarantee safety, and you convert this preference learning problem to a problem of learning weights of a temporal logic formula. And essentially, if you are familiar with logics, this quantitative semantics of your logic formula, weighted logic formula, is essentially this ranking function that satisfies the properties that you want to satisfy. As a bonus, since this is a logic expression, you can take this and use it in control synthesis directly as well. So it's also like easy to incorporate in downstream tasks. Again, we run some experiments by comparing this thing with standard preference learning type approaches. We showed that using this logic-based preference learning, you capture the preferences almost at the same level as other standard methods, but you guarantee safety all the time. And the other thing is that you can even learn only with demonstrations that are safe. For other methods to learn, you really need to show them demonstrations that are both safe and unsafe. Otherwise, they end up being super unsafe. And again, in a traffic scenario, you don't have too many demonstrations for unsafe behavior. And there's an advantage to be able to learn only using safe behavior. We also put people into this 6 degrees of freedom driving simulator at Toyota, where our synthesized trajectories are running in the simulator and the person is sitting in there. And we have an active version of asking right questions to the person, this yes/no questions. And within 10 questions or so, we can capture their preferences pretty well. Okay, so finally, as I said, since we are learning these preferences in terms of logic, we can synthesize new behaviors using them as well. But when we started synthesizing these new behaviors, one thing we noticed that our state space is not complete. Our preferences, our logic formula doesn't capture everything. And just learning with this formula without a complete state space is sometimes problematic. So let me try to see. And to fix that, what we did is we start adding demonstrations to regularize the behavior that we are seeing. And I will show some behaviors. I think the video is not playing here. I think the one behavior, for example, these two behaviors that go to the edges are behaviors if I only use my preference learning, because I didn't specify anything about lateral dynamics in my preference learning. And it learned that, oh, the people are trying to be away from the pedestrian as much as possible. How can I be away from the pedestrian crossing the street? I will just go to the edge of the road, which gives you not so nice behavior. So this is the pedestrian crossing. But if you have some demonstration to regularize, you can start capturing this part of the driving behavior that's not necessarily captured with your state space where you are defining your specification. Okay, so maybe this is the end of the talk. Let me summarize. So I think we are spending too much time on modeling systems, or learning models, but less time on writing specifications and learning specifications. And I think specifications should be there in the same equivalence class as models if you are doing design. The key messages is optimality is a strong prior if you want to learn from a small number of demonstrations. If you want to learn multi-stage tasks, for stochastic systems with lots of data, you need to understand the memory structure, and there are efficient ways of learning this memory structure that gives you this multi-stage task. And combining human feedback with logic both increases expressivity without sacrificing correctness and safety. And I think there are many interesting questions there. How do we incorporate more human feedback into safety specifications, learning for safety and safe control? I think with that I will stop. Over time.
So we'll take one more question while the next speaker sets up. Yes, go ahead.
I'll just speak here.
Yeah.
I'm curious for the learning the temporal logic specifications. You were assuming that the APs are given, but in many cases you can have demonstrations where they don't know the APs, so you're making copy. It's going to give you a trajectory and not going to tell you what the stages are.
So in the first part, we don't need APs to be given. We can use the statics. We just need a featurization of the reward function, featurization of the constraint, and we just need to know the features. So we have examples, we have exactly the copy example where we are learning how much you can tilt. So as long as you have a featurized version of your APs, you can learn those features. It just comes from the first part of the talk where I was trying to learn the ellipsoid. That same thing combined meshes very well with temporal logic, and you can learn the APs as well.
Okay, let's thank the speaker again. So, well, for the next part of the workshop, we have been talking about how to capture specification, how to learn all this safety specification, but now we're going to shift towards how to look at uncertainty that comes with that, or uncertainty in general, with like stochastic system. And who's the better person to talk about this than Luca? Luca is a professor at he cannot come in person today, unfortunately. He's a professor at TU Delft and also a co-director of the AI Institute there. Oh, use this one. And he works on formal methods and data-driven stochastic CBF, or these sort of things. Let me check if we can hear him. Can you speak a bit?
Can you hear me?
Yes, we can hear you very well.
Perfect.
Yes. So, yeah, take it away.
Oh, so thank you very much for the introduction, and sorry for not being there. Unfortunately, I had a wedding yesterday in UK, so that's why I'm not there essentially. But thanks again for the invitation. And indeed, I'm going to talk you about one research direction which is pretty recent for us. It's about safety guarantees for uncertain dynamical systems, which I think that intersects very well, hopefully complements very well with the other talks. So let me just let me start by giving some motivation behind my work. Essentially, in my work, I'm interested in dynamical systems, and in particularly on how data-driven techniques can be used and can be used safely for learning and controlling dynamical systems. In fact, as well, you are all well aware, considering all the talks, right now in dynamical systems like autonomous cars, the use of machine learning, such as neural networks, is becoming pervasive. And this introduces several challenges. And one of the main challenges that I'm interested in it is the uncertainty that comes with it, because nowadays autonomous systems are inherently uncertain, but the uncertainty, as I say, does not come just directly from the interaction with an uncertain environment with stochastic dynamics, but also comes from the fact that while we use data-driven techniques, data are finite, and so we have some uncertainty behind some of the components of the system, also because maybe we don't know those models very well. And this leads to the fact that, well, as the title of my talk says, I'm also particularly interested in applications which are safety critical, meaning that, well, if there is a failure, this can have very fatal or costly consequences. And this is the main motivation of on my talk, which is how can we actually give safety guarantees for systems which are stochastic and uncertain. As well, I'm going to show you uncertain, meaning that not only the system is stochastic, but we don't even know those distributions. And I'm going to show you that actually we can actually do something about it. We can actually compute guarantees for this kind of system. We can kind of propagate the uncertainty over time for these systems. And this is going to be the first part of my talk, where I'm going to focus on uncertainty propagation in Wasserstein distance. I'm also going to introduce why Wasserstein distance, hopefully give you a bit of background on what Wasserstein distance and its properties. And then I'm going to show you how these techniques can be applied for doing safe control of dynamical system with uncertainty. And then I will conclude with some, well, open questions and challenges. But first, I want to start by defining the general class of models that I'm going to consider in this talk, which I think leads to so many open problems, which I thought was nice to start directly from introducing the models that I'm going to consider. So in this talk, I'm going to focus on dynamical systems, discrete times dynamical systems, where we have xk plus 1, state of the system on time k plus 1 is given by some nonlinear function f of some state x. We have a controller u, and there is some noise w. And f we assume to be known, but I'm going to show you later that this could also be a neural network, for example. And when I say that the system is uncertain, there is some epistemic uncertainty. I mean that the initial distribution of the system and the distribution of the noise are themselves not known, but we just know that they are close to certain target distributions. I'm going to be more precise later when we introduce specific problems. But this is the general settings. And before moving further, I want to motivate you why in my group or with my collaborators, we started to study this class of systems. And this leads, and this is motivated by essentially, there are many motivations, but I want to give you 3 ones. Okay, the first 2 are pretty standards, which are given by the fact that, of course, this distribution, noise and input distribution may be learned from data using statistical techniques. So there is uncertainty, and then we need to have planning methods that are robust against this uncertainty. And also there may be distributional shift, because of course the distribution of your system can change, can be different from when you collect data, when you deploy the system, you may have different distribution, and so you need to have to be robust against changes in distributions. But there is also another settings which I'm particularly interested in, and I'm going to show you that some of the techniques that actually we develop in, well, robotics and control theory can also be applied in learning on neural networks. And this is the fact that if we see this F as a neural network, you can see this W as the parameter of a neural network, which in a Bayesian setting, these are all distributed. These are all distribution. This is what's called in the literature of Bayesian neural networks. But the problem also there is that if I try to do learning on this model, then I cannot really compute the exact posterior distribution, which is the distribution of the parameters given the data. But generally what happens, what people does is approximate it to some Gaussian with some error, right? And then the problem is, okay, but as I'm learning the system, I need to be robust against this uncertainty. And this is also another motivation why we are considering this class of models, because the models can be neural network driven, but then if we learn neural network in a Bayesian setting, because we need uncertainty quantification, we need uncertainty, then we need to account also for this error, or at least being robust. And before moving further, let me discuss a bit what is the problem, where I'm focusing on this setting, and I'm mentioning that it's very interesting, but it has quite a lot. It's quite difficult, and all the difficulty comes from the problems that if I know the distribution of the system at time, for example, 0, and I know the distribution of the noise, even though these are Gaussian, the moment then you propagate it through a nonlinear function, then the distribution becomes intractable. And this is the root of all the problems, because this is an example. If I start from a Gaussian distribution, then the moment I pass it through, well, this to this nonlinear function, then you see you get something which is multimodal and clearly not Gaussian. And by the way, this is the problem also for, and here I'm assuming that all the distributions are known. The moment in which you make them uncertain, of course, the problem becomes harder, but I will actually show you that in theory, that in practice, it's not much harder. So if you can solve this problem, you can also solve the uncertain version. And I'm going to give you some techniques to do that. And, sorry?
No worries. Yeah.
Okay, go.
It's just a mic meeting.
Oh, so I can just go. Okay, thanks. So, and then let me just start by considering the first problems that actually that I want to discuss you more in details. To be fair, this is chronologically, this is the last paper that we had on these topics, but I think that it includes so many results of the other paper that I want to present it first. So the idea is that in this paper, we consider the setting that I described up to now. I'm assuming an additive noise. This just makes all the calculation easier, but all the results can be extended relatively easy to the case where the noise is not linear. So the setting that I want to consider is the following, right? That I know that, as I mentioned, I have an input distribution, which is unknown, and is represented in this case by this blue ball of distribution, which are centered on bar px0. And this blue ball of distribution contains all distributions that are closer than theta x0 in the Wasserstein distance to this center, to this reference distribution bar p x0. And what we want to study is how this set evolves over time. Essentially, if I propagate this blue set inside the dynamics of the system, how the shape of this set changes? Is it bigger? Is it becoming smaller? Is it contracting? Are there some fixed points that hopefully we can use to study infinite horizons properties? That will be the case in some cases. I'll show you that actually will be the case for many properties of interest. And as I mentioned, the other component of the setting is that also this noise is additive, but it's uncertain. Again, we know that it's close to some reference distribution in the Wasserstein distance, closer to theta p, right? So the idea is we have two distribution. We have an initial distribution, which is uncertain. We just know that it's close to some target distribution in the Wasserstein distance, and we want to propagate this set over time. Of course, this is a set of distributions, so how can we propagate it? This is the question, and this is I think an important problem because this set of distribution contains the true distribution of the system. So if we can propagate it over time, immediately we also know we can also propagate the true distribution of the system. We simply know that is theta close from the center of the set. So we can plan using the center of the set and then simply account for this error in our planning algorithm, which I'm going to show you later. But before of that, I want to give you some intuition of what is the Wasserstein distance. Maybe not everyone is familiar with that, and I want to mention why are we using this distance. Essentially, the Wasserstein distance is a distance between distributions. As I mentioned before, well, I'm considering an uncertain distribution, so I need to quantify a distance between distributions. And the Wasserstein distance is particularly favorable because it's described, as I'm going to tell you now, as an optimization problem. As we're going to show you, this actually makes calculation much easier for these particular settings. The idea of the Wasserstein distance, the way at least that I find more intuitive to present it, is that the Wasserstein distance is simply the cost to transform one distribution to another. if you consider, for example, the example on the left, we have that we want to transform this blue discrete distribution beta to another discrete distribution alpha. And the vastest and distance is the smallest possible cost that I can possibly have by transforming these two distributions. And another property is that any cost, any transport plan will be an upper bound on the vastest and distance. The idea, for example, is that if I take the first row, you can see that the third point in the support of beta, all the probability mass from there is transported in the first point in the support of alpha. While for the second point of alpha, in the support of alpha, we know that we take some distribution from the first point in the support of beta and some for the fourth one. Same for the third. And this is, you can already see that this is a kind of, this is essentially moving mass from one location to another. The cool thing is that this is a linear program. This is what generally makes calculation easier. And it's a linear problem if you have discrete to discrete distributions. But another important properties of the vastest and distance is that, which is one of the main reasons why I'm considering, is that is because it's well defined both for discrete to discrete distributions, but also for distribution of different support. So you can define it between a discrete and a continuous distributions, or between continuous and continuous. And this is particularly good for the setting that I described now, because it gives us so many good properties, which are very important the moment we want to provide safety guarantees. Because first of all, the vastest and distance, even though I defined it as a solution of an optimization problem, it satisfies it's a distance, right? So it satisfies all the distance properties. But the important thing is that if you have a bound in the vastest and distance, automatically you have a bound on the first moments of the distance of the two distributions. We actually proved that, this is well known for the expectation, but we proved also for Eiger moments, that if you have a bound on the vastest and distance, depending on the cost, the exact bounds translate to bounds on the first few moments of your distributions. And even more, if you have a bound on the vastest and distance, by solving an optimization problem, you can bound probability of an event, right? So you already see that if in that ball of distribution I know the vastest and distance, automatically I know properties that I can use to provide safety guarantees for the true system under study. And also another important property is that, well, I can learn a distribution from data with bounds in the vastest and distance, right? So these are very prone to data-driven algorithms. The bounds can actually require a lot of data. That's a problem, but I know people are working on that. And so now that I described you, hopefully give you some intuition of why we consider this distance of distributions, I'm going to describe the approach that we use to solve this problem. So the idea is simply that, well, it's not that, the idea is that, okay, we have this ball of distributions, and we transform it through f, which is a non-convex function, right? So in general, the true set Sx1 will be a non-convex set. So what we simply do in our approach is to find the tightest possible of convex over approximation. The tightest possible ball in the vastest and distance containing this blue set Sx1. And how do we do it? In order to explain how we do it, I'm going to show you how to do it in the case that the distribution are not uncertain. And then I'm going to describe and explain you that at least give you some intuition of how these things can generalize for when the distribution are uncertain. But note this, that here essentially what I want to focus is that I have an initial distribution P, and distribution Px0, I pass it through a nonlinear function f, and I want to compute this distribution Px1, which if we look at an example to explain what the transition kernel it is, what the transition probability it is simply this Px1x is simply the distribution of the system after one-time step. In this case, where the additive noise is Gaussian, this is simply a Gaussian centered in X. That's why actually I consider this additive noise case, because it makes all the calculations much easier. But then the problem is that when I integrate, I take the expectation with respect to the possible initial points. As I mentioned before, this expectation is intractable. So how do we solve this problem? Well, we solve it by doing mixture approximations. The idea is actually, I think, intuitive. The idea is that here we have an expectation. Let's approximate it with a sum, right? That's all it's going on. And the idea is that as we know the distribution Px0 in this case, this is known. I can simply take some points in the support, C1, C2, C3, and C4, and take some, in this case was the Voronoi partitions, but any partition based on these points, compute the probability that the system is in each of these regions, and then I simply approximate this expectation with a weighted sum. Essentially, I have a Gaussian, in the case before, centered in Ci, for any point, for any Ci points, in this case 4, and then I multiply by the probability of being in that region, right? So what I'm doing in here, I'm approximating this initial distribution, which is continuous, with a discrete one. And now you see why it's important that the vast certain distance can work between continuous and discrete distributions. And then now I can take the expectation and then obtain a mixture Gaussian approximation. This is what's going on. But the cool thing is that, I promise this is the last, after this the math will decrease, is that what I can do is that the moment I do that, the moment I do this propagation, I introduce an error. But what is really cool, I think, was probably the main result that we had in this paper, is that we can actually bound the vast certain distance between Px1 and bar Px1, this mixture of Gaussian approximation. And how can I bound it? The idea is that this formulation seems complex, but I'll try to explain you and give you some intuitions. But also what's important to know is that we can bound the distance between this distribution, we can bound the error that we are making by approximating an intractable distributions or an intractable expectation, as in this case, with something that we can actually compute and for which we can do planning, safety guarantees, all that we want. And how do we do it? We do it by, first, the bound is given by a sum over all the regions, R1, R2, R3, R4. And for each of these regions, what we do is that we have this nonlinear function f, which tells us the dynamics of the system. We linearize it around each of these regions, and you obtain, these are the alpha I and beta I are the linearization coefficient of the regions. And then essentially we compute how much the probability mass of Px0 in this case changes compared to C1 or Ci, right? We do that for all the regions, and then we account for the bias by multiplying by the probabilities. And this is a valid upper bound, which is actually tight in many cases for this to a certain distance. And what's important to know is that these are converging error bounds, in the sense that if we have a lot of samples, the bounds goes to 0. How fast depends on the system, depends on f. So depends a bit on the Lipschitz constant on f, how fast it goes to 0, but these bounds work for well, any continuous function. Actually, can have also finite number of discontinuities and things still work. And here I show you that things work for additive noise. You can extend it for non-additive noise as well. Will be harder to, there will be a correction term in here, appearing in here, which will make computing this integral harder, but you can still do it. And what's important is that I can do the same, I can use the same exact reasoning that we use, that I show you in the bounds, to the case where the initial distribution and the noise are uncertain. How do you do it? You use the fact that the solution of the vastness and distance is an optimization problem. So you simply kind of take the worst possible bounds for all combination, for all possible initial distributions in the ball and distribution of the noise. I'm not going to give you the mathematical forms, that's on the paper. But what is interesting is that actually these bounds are actually surprisingly good. I mean, sometimes are surprisingly tight, and they scale quite well. And for example, if you start to think, one question could be, okay, this bound is for one-time step, but what happens when I propagate my distribution over time, over infinite time steps, right? For example, because as you remember, when I show you my problem formulation was that I'm propagating this ball of distributions over not just one time step, but over multiple time steps. And what we found is that if your dynamics are actually have Lipschitz constant smaller than one, so they have some kind of contractiveness, well, your ball, the size of that ball will actually not grow, will reach a fixed point. And this fixed point is actually, you can approximate it with this actually, I think, pretty nice, pretty cool equation, which of course, this depends on the Lipschitz constant of the system, because if the system is unstable, growing, well, then there is not, also the ball will grow. There is not much you can do. And this depends on the approximation, this epsilon, which is essentially the solution of this of the approximation error on the centers of the balls, of the true distributions that you know at every time step. And this is something we can control by increasing n, as I mentioned before. Depends on the uncertainty of the noise, because at every time step I'm adding noise linearly. So of course there will be some uncertainty, which is mitigated depending again on the Lipschitz constant of the system. But this was particularly cool for us because we actually managed to show that we could do uncertainty propagation of general arbitrary nonlinear systems by relying on discrete or mixture approximation depending on the distribution in the systems. But let me show you some examples. In these examples, we started with some. I want to show you just two examples, to the representative ones. The first one was a neural network, this is the vector field of a neural network, which we use to learn some pendulum dynamics. And what we did in here, and what I show you on the center and right column, is the true propagation of the system. This is the true distribution of the system that I propagate. And this ball, these circles that you see are the bounds, the translation of the bounds in the Wasserstein distance to bounds in, I think it was 99% probability that we obtained with our methods, was this Wasserstein distance ball translated in probability. And as you can see, what we saw is that this ball, for this system, even though that was a neural network, I think it was one, I don't remember if it was 2 in the layer 128 neurons, or 1 in the layer, I don't remember exactly. But what you can see is that these balls actually, when they reach 0, they actually reach a fixed point. So they will actually stay here forever. So that's what, so in the center, I mean, you can run it for as many time steps as you want. This circle has reached a fixed point and will not move from there. And what we plot on the right is the approximation, meaning the samples from the centers of the distribution that we obtained with our approximations. As you can see in this case, the samples are basically almost identical to the true distributions as we expected it. And instead, on the bottom row, we had a planning example. So we took some switch systems. Essentially, it was a linear system that was controlled to solve reach avoid problems. The problem was I want to reach the target regions while avoiding obstacles from every possible state. And we took a policy from one of our algorithms, and then we wanted to verify that for particular initial distributions, well, the system starting from that distribution, the system was safe with that probability. And this is what we can do again, because as you can see, these balls again represent I think it was 95 or 99%, I think 99 again, because it's supposed to be the same parameters. The certified 99% that comes from the probability of the system, that comes from our bounds in the Wasserstein distance of reaching the target from different initial conditions. And again, approximation is what we obtain with by approximating the center of that blue ball that I show you, by simply doing propagation with the center. And this was cool. So as I mentioned, these techniques with this set of this method that I show you allow us to do uncertainty propagation for nonlinear systems. Of course, there were some limitations. It depends that for certain class of systems, computing the bound is easy, like if you have added Gaussian noise. And of course, if you don't have non-Gaussian noise or noise is non-additive, you need some correction, which can be challenging to compute. That's something we are working on. But something that I want to stress that I don't have time to mention you in here is that this approach can actually scale quite a lot because we actually used it to approximate the distribution of neural networks as Gaussian mixture models. It was ReLU neural networks that we approximated as Gaussian mixture models. And on images, so input size smaller than 100, that we actually managed to get a non-trivial non-trivial bounds in busters and distance also for that setting, which was, I think, was very, very cool to see. Also because there were no other techniques for that. And now I want to move forward to show you how these techniques that described you how to do in a general way uncertain propagation of uncertain systems, sorry for the repetition, can be used for planning. And in order to do that, I'm going to consider this paper. I want to show you the result from one of our papers, where in the paper we actually we had temporal logic specifications, but just to simplify the presentation, I'm going to just focus on probabilistic reachability or reach avoid. The idea is that what we want to do is that, again, we have our same classical model, discrete time nonlinear systems, and we want to compute the probability. We want to compute a controller that maximizes the probability that starting from any point, well, in this case, the robot will reach the goal region XR while being safe, while remaining in XS. If you have if you know the distributions, so if you know the noise and the input and the X, the initial point is known, then you know that solving this problem is equivalent to solving the following dynamic program. The idea of the dynamic program is that you start from the goal regions, and then iteratively you propagate and you find a controller U that maximize the probability that you reach state that are likely to go to the goal regions. And those boils down to compute this expectation, again, this expectation over the noise of the value function at the previous time step. And as you can see, again, you can already notice, but this is an expectation which is quite similar to the one that I showed you before. Indeed, we will see that similar techniques applies also to robustify this setting. And if you run these dynamic programs, it's well known that at time n, you have that the solution of this dynamic program at time n is the reachability probability for horizon 0n starting from state x. And what happened in our setting? In our setting, in this case, we have that, as mentioned, that the noise, what happens if the noise is uncertain, again, is within this ball of distributions. Well, in that case, we show that you still have the same dynamic program. The only thing that changes is that now you find a controller against the worst possible distribution in the set. That's what this minimization is about. The idea is that, okay, I want to maximize a controller that maximizes my reachability probability, but as I don't know the distributions, the only thing, well, it's not the only thing, but one of the most, if I want to be robust, what I can do is plan against my the worst possible distribution from the set. And this is what's going on in this dynamic program. What I'm going to show you is that techniques right now that are commonly used to solve this stochastic dynamic program for stochastic systems can actually be easily, well, not easy, but can actually be modified by accounting to the robustness, for the distributional robustness, without increasing the complexity of the system, the complexity of the resulting algorithms, or at least the class of complexity. So, and again, in this paper, we consider the abstractions. Reason is that because this is probably the state of the art to solve these problems for stochastic systems. The idea of an abstraction is that as f is nonlinear, I cannot, as mentioned before, I cannot really propagate a distribution of the system over time, especially if I want to find a controller, a feedback controller for every possible initial state. So what I do, one option is to simply approximate my continuous system X with a finite one, with a finite machine, a Markov chain, which is called the abstractions. The idea of the abstraction is actually, I think, pretty intuitive. The idea is that you discretize the state space of the system. This is all well-known techniques. You discretize the state space, and then from every pair of regions in the partition, you compute what is the probability of going from one partition to another. Of course, here there is the problem that depending on which point in Q0, in this case, you start, the probability of reaching Q prime, Q1, will be different because starting in from different points, you have different probabilities. So what do you do in practice? What you do in practice is computing both the mean and the max of the probability of transition to region Q prime, Q1. So essentially what you do, you compute an interval, essentially starting from Q0 to Q1, you say that the probability of reaching that from Q0 reach Q1 will be within a minimum probability and a maximum probability. And this leads to what are called in the literature are uncertain MDP abstractions. In this case, it's an IM interval Markov decision process abstractions. It's an interval because, well, this is as you can see, it's a Markov chain with a finite number of states, in this case 10, Q0, Q1, well, up to 9, because there is also a state for everything that is outside this set. But from every two states, I don't know the probability that transition from one state to another, but I know that it is within some certain intervals. And these intervals are independent from every state, at least in the most classical formulation. And this is why are called uncertain MDP abstractions. Uncertain because, well, we are uncertain. We don't know the probability of transitioning from one state to the other. But the cool thing is that planning for this kind of uncertainty can be done still in polynomial time in the number of states in the system. And gamma represent all the possible probabilities that satisfy these constraints, because it's clear that if I have intervals from every pair of states, there will be infinitely many probabilities that satisfy these constraints. We call this gamma. And what happened when I have an uncertain distribution is that you say, okay, I take all possible admissible distribution that satisfy these constraints, and then from each of them, I consider I have this ball, and then I consider the worst possible modification of this distribution from the ball, using the techniques that I showed you before. And so essentially you end up with this max-min problem. This seems complicated, but in practice, it's not bad, because what we proved is that this problem can actually reduces to a linear program from every reduced to a linear program, which is the same complexity that you had to plan for interval Markov decision processes. Essentially, you have a linear program from every pair of action and state. And this was cool because we showed that actually adding the uncertainty, we could use the technique that I showed you before, and everything still reduces to a linear program. There is a caveat that you get a linear problem just if one of the distribution is discrete. And this was cool. So we still kind of maintain the same complexity. And then let me show you then an example for that. So to show you an example, we consider again this nonlinear system, again, where f is this piecewise this nonlinear function where we have 4 discrete controllers. So this is a switch systems. The goal of our goal is to synthesize a sequence of controller, a feedback controller, actually a time-varying feedback controller that for every state and time select which actions I want to play. And this distribution W again was uncertain, was centered at a discrete distribution, which was learned from data. And then we had an uncertainty, which actually was quite large in this case, 0.05. And then we use our algorithms to plan to synthesize a robust controller. And this is what we got, right? As you can see, what we got is that on the left, you see the vector field of the system after with the strategy. And on the center and right, you see the lower and upper bound probabilities as computed with our approach. Notice that these are valid. These probabilities. These comes with no confidence. These are the true lower bounds and upper bounds of the probabilities. And as you can see here, you see quite a lot of black, in the sense quite a lot of zero, because in this case, well, the system was not flexible enough to synthesize a strategy, to have a satisfying strategies for states starting close behind the obstacles. And this is what I want to conclude in terms of the experiments, was to see that, to emphasize that actually considering uncertain could be very important and could lead to drastic changes in your probabilities. This was, again, from similar settings. As you can see, that when I had no uncertainty in my system, so standard stochastic, solving the dynamic programming for a non-stochastic system, I could get a lower bound probability of 1 from every state in the system. The moment then I started to introduce uncertainty, well, then this lower bound was decreasing. This again shows actually that if your system is uncertain, considering uncertainty can be actually important. And let me conclude this last couple of minutes with some remark and maybe some what are challenges and what are the challenges. So what I show you is that I show you some algorithms to approximate and compute the distribution of a nonlinear systems, uncertain system over time. I show you that we had bounds for that. And I didn't mention that the way that we find this, we had also optimization algorithm to optimize for these partitions, to discretize the distributions. But of course, this comes with challenges. One challenge is that solving these optimization problems can be expensive, and for certain class of systems can be done pretty smartly. For others, it may still require some investigations. But something that I want to stress is that how these techniques that allow us to approximate a distribution with a mixture of Gaussians over time can actually be very suitable to be combined with approaches some MPC or with the planning, like research plannings, because this propagation requires essentially no discretization of the full space, which is what I'm very happy about. And then what I want to stress is that, and this is an open question that we are working on, is how these techniques can be used in a Bayesian learning settings. Because as I mentioned before, one of the problem or one of the features of neural networks, if trained in a stochastic setting, is that the conditional distribution of the various parameters over the data cannot be computed exactly. You need approximation. So one of the questions that we are trying to solve, or at least to investigate, is these techniques can actually be used to bound the uncertainty and the error that you are making by approximating the distribution of a neural network with a Gaussian, for example. And actually, we showed in many cases, actually, all the techniques that I show you can actually be very useful also on this setting. And this has probably a motivation for also considering that settings, which I think is orthogonal to what we are doing essentially, but for which uncertainty propagation is very, very essential. And thank you very much. And I'm happy to take any questions that you may have.
So we have time for one question. If you have a question, can you come up and speak to the mic? You want to speak to the mic? Yeah.
Thank you for the great talk. So the problem formulation, you had expectation over the over the probability distribution. What if we want to bound the tail probabilities? How can we modify, say, Wasserstein distance or something like that to account for tail probabilities instead of like average distance between the distribution?
Yeah, the idea is that, well, the answer is probably on this paper number 2. Is actually, it shows you how to translate bounds in Wasserstein distance to bound probability of a specific event. For example, if you want to bound tail some specific events, I mean, or you can actually, I would do it by solving an optimization problem. So, well, the answer to your question is probably on this paper, essentially. There is an optimization that you need to solve, essentially. And the bounds may become maybe hard, maybe conservative or not, depending on the specific sets or on the specific cost that you are using. But in theory, you can do it.
Okay. Looks like there's no more time for questions. So let's thank the speaker again and
so thank you very much. Well,
and we're going lunch break and we'll meet back at 1:45.
Thank you. See you later. See you later. Bye.
Bye. Do I end the meeting or do I end the meeting? Or is it
Maybe
recording?
just pause the recording, right? Just pause the recording.
Just yes, you can. And yes. You press record? Yeah.
Yes. Won't make slide.
Sorry to make the file.
Is there? No. Yeah, okay. Okay.
Oh, so he didn't want to connect directly?
No, he's connecting directly.
No, I mean like through the screen. Maybe just gonna do it through the screen. Like,
Oh, yeah, I think
Yeah,
it's
I don't know if you
better.
want
It's
to do that.
better. It's better because we'll have a lag,
But,
right?
I think he needs the adapter.
Schumann has it. Schumann, do you can
Adapter.
adapt?
Oh, yeah, yeah.
USB-C, right?
Yeah. I'm connecting directly from your computer so that it's.
Yeah. Is it still on Zoom?
Yeah.
Okay.
Yeah. You've been everything good?
Yeah. How about you?
Everything strong.
Thanks again for the invitation.
No, thank you for speaking. Yeah.
Bye. It's probably now after lunch, it's going to be a little more empty.
Yeah, people would like take longer lunch.
Yeah, when I saw that it's only 1 hour, 15 minutes break.
So I'm sorry.
No, I mean, that's a schedule.
Yeah. You know, Shell is gonna go in China.
I heard about it. Yeah, really happy for him.
Yeah.
I didn't know that he applied actually. But he only applied to China.
Even
So-
Ames didn't know.
Doesn't he need reference letters for?
Apparently not.
Okay, well, I mean, good for him. I mean, it seems like he didn't want to stay in the US. You had interviews too, right? You had interviews too, right?
Yeah, I had interview.
How did it go?
Got one offer, but I didn't take it.
From where?
From Ohio.
But you didn't want to.
Yeah, no.
Well, I mean, maybe. Yeah, it's a difficult time.
Yeah. Well, next year.
Yeah, finger crossed. Yeah, I'll also be moving back to Europe, actually. You heard about it, right?
Yeah. KTS. You.
ETH, yeah.
ETH.
I'll move in September.
Oh,
yeah.
so you that's locked in.
Yeah. Funding is a little too complicated for me in the US right now. Other things. I'll give Europe a shot, see how it goes. See how life goes. But I mean, for you, it was a good experience, I guess, to be on the job market. And
Yeah, I learned how to start to think more about like what do I want to really want to do.
Yeah, this kind of vision and
Okay, let's just start. Yeah. So, okay, everyone. Hello. Hi. So, yeah. So, thank you for coming back after lunch. So, we're going to continue on the second topic on how to, quantify all this uncertainty that come from learning this the safety specification or uncertainty in general, I suppose. And we have Lars here. He was a PhD student at KTH and then go to UPenn for his postdoc, and he's now a professor at USC, right? And yeah, and he's an expert in conformal prediction and control, right? And formal methods and, temporal logic, all these things, which will be a very good tool for quantifying uncertainty. So, but Lars, please take it away.
thank you so much for first of all, the invitation and the introduction. Thanks for coming, even though it's after lunch. I was expecting it to be much sparser. So I'm going to tell you a bit about safe control for learning-enabled autonomy with conformal prediction. And I have 3 goals in this talk. First of all, I would just want to give you a high-level introduction, show you a bit, very high-level, what I'm working on in my lab. And then my second goal is to tell you about conformal prediction. So conformal prediction is a statistical tool for uncertainty quantification. Some of you may have heard of it already, but I'm going to give you a very detailed tutorial on it. And then in the third step, I'll show you how we can use conformal prediction for safe control problem. Okay. So first of all, I work on autonomous systems very broadly, and autonomous systems, at the end of the day, they are control systems that operate autonomously in complex and open-ended environments, right? They perceive their environment, they reason from and learn from data, they assess uncertainties and risks, and they make decisions in order to achieve a wide variety of tasks. In my lab, we're interested, especially in this space, we have applications in autonomous driving and robotics, and more recently also in wildfire prevention and disaster recovery, which you can imagine wildfire prevention in LA is a really big topic after the fires that happened in January. But there are many other applications, for instance, space exploration, warehouses, agriculture, or smart cities. And all of this certainly highlights the importance and the potential impact that autonomous systems has already had and will continue having in the future. Specifically, over the last years, the computational advances that we have experienced, along with availability of data, has accelerated progress that we have made in order to build these systems. I've shown 3 examples here. You probably have seen those: Boston Dynamics robots, Tesla cars, and drone fleets, where these systems really perform highly challenging tasks with ease. And just looking at these videos, we could say that, yes, autonomous systems are a reality. They are there, right? However, the question that I want to ask, and the questions that we look at in my lab, is, do we really have all the theories and tools in hand to build autonomous systems that are also safe? And the answer to this question generally is no, we don't, because at the same time, we've seen failed demonstrations. We've seen Boston Dynamics robots crashing, we've seen Tesla cars colliding, and drone fleets collapsing, right? even more so, it turns out these days that autonomous systems are learning enabled. They use learning components, right? And we know learning components, they may be fragile. They may not always work as anticipated and as expected. One example here that I picked is the company Cruise that had to recall all their self-driving cars in California due to yet another accident where the car was basically dragging along a pedestrian. Okay, so they had to, well, basically recall the cars. And I live in Santa Monica, so I took this video here where you can see self-driving cars in action. You can drive them. It's actually really convenient. So one could look at them and be like, well, they are there, right? But I would still argue they're not fully certified, right? We don't know how safe they really are. And here's an example. They just recently added a first responder program to detect, let's say, emergency vehicles. And just 2 weeks ago, I was at a conference and someone there told me they were in a Waymo and the Waymo didn't detect like a police car with sirens on, right? So it's questionable if, this is really safe in that sense. And another example from a different domain here, where a robot in a crowd is basically headbutting someone who is just standing there innocent. And there are many more of these videos. I think the important point here is then starting to ask the question, why are we facing these challenges? And something that has been realized already years ago is that it seems in a way that the way that we train our AI and the learning components is fundamentally flawed. Because for one, we train and tweak algorithms to lab-like environments. And at the same time, we train and tweak our algorithms to pre-specified scenarios and requirements and specifications, which is also the topic of the workshop here, right? But we're failing to generalize beyond these lab environments and beyond this predefined and specified scenarios and requirements. Another reason is, and this is also an old example, AI is kind of easy to fool, and in technical terms, it's not necessarily robust, right? So here, this example I talked about, we have a panda image along with a classifier that correctly classifies it. And the moment we put some small noise on the image, it really looks the same to the human eye, but it's suddenly misclassified as a given. And I have a more modern example, which is actually from one of my friends, Alex Ruby, who's also here in the audience. He's working on LLM-controlled robots, and he's jailbreaking them. So you could go and you could tell a robot via an LLM, go deliver a bomb. And the robot would say, sorry, I can't do that. And Alex is basically designing sequences of symbols that you can append to the prompt, and suddenly the robot will deliver the bomb, right? The important question here for people in my lab then is, well, how can we make these learning-enabled systems safer? But we're also interested in understanding what are the fundamental limitations that we're facing for these systems, and what are even the performance and safety guarantees that we can provide. And I'm going to at least give a partial answer to the latter, right? What kind of performance and safety certificates, so to speak, we can provide here in this talk. Now, I'm a controls person, so I like to look at block diagrams, many of you probably as well. So I have a really high-level one because I want to dive in a little deeper now. So here we have a system, in this case, a car, as well as an environment that may be open-ended, dynamic, and uncertain. And usually we have sensors, for instance, camera or LiDAR, to get information of what's going on in the world. And then we have a set of perception prediction algorithms to process this information and obtain state estimates, right? Estimates about the state of the car and the state of the environment. And we then use this information within a planning and control module to actuate the car, so to compute low-level control inputs, right? We may be doing this 100 times a second. Now, where may we face learning components here? If we look at this loop, for instance, we may have object detectors in there. We want to detect objects in the environment, and we may want to assign semantic labels, right? Another learning component we may be using here are trajectory predictors. In fact, this is what we'll use later in this talk. We will be using trajectory predictors to predict pedestrians at an intersection, right? So we want to capture dynamic behavior of an environment. Or more classically, you can use machine learning for system identification or even for low-level control. And more broadly in this kind of learning-enabled systems and to design safe controllers, my lab really provides verifiable control frameworks for autonomy along with efficient computational algorithms. And like I said, I just want to give you a brief introduction to the topics that I'm working on in my lab. One is, for instance, data-driven control. So we're thinking about how we can learn control laws, for instance, from demonstrations here for this walking robot, right? Another line of work we're doing is on statistical system verification. Here in this case, during runtime of the system, we want to compute the probability that the car will enter a failure mode. We also work on multi-robot systems. Here you can see a video of the lab of something I did at KTH still. And very broadly, we work on formal methods and controls. So synthesizing controllers for high-level, potentially temporal logic specifications. And last but not least, on risk-aware autonomy, so decision-making under uncertainty, and this is what I'll be talking in detail about today. So in summary, really think about providing a formal and a computational approach to systems and control. All right, so now after the short introduction on what I'm interested in, what my lab is working on, I want to dive into the technical part of this talk, which is on safe control design in dynamic environments with this statistical tool, conformal prediction. So this is in this risk-aware autonomy bucket. And if we have a little bit of time in the end, I'll also talk about a bit of formal methods. Okay. So the problem that we want to solve here is the following. We want to compute control inputs for a system, for our ego agents, so to speak, so that this system avoids dynamic agents in the environment with a probability of no less than 1 minus delta. Right? For instance, we may want to control a car to avoid other cars in the environment as well as pedestrians. Right? So why is this a challenging problem? Well, first of all, the agents in the environment, they are dynamic, they are stochastic, and they have potentially unknown intentions. Okay? So there's a lot of uncertainty already in these agents in the environment. And what one typically does is one uses complex and potentially learning-enabled predictors to predict their behavior. But as we just learned, these learning-enabled components, these predictors, they may not always work as we expect them to do, right? They may not be robust. So uncertainty quantification of both of these things is kind of difficult, especially if you want to integrate them into the controls. And just briefly, a lot of people have obviously worked on this problem, so just want to give kind of a bit of references to those. You could, of course, use vanilla kind of motion planners such as graph or sampling-based A-star or RT-star algorithms. But here in this problem, these algorithms typically ignore the dynamics of the agents in the environment. Right? There's a lot of existing work on reactive controllers, for instance, navigation functions, or in robotics, dynamic window approaches or control barrier functions. However, as these are reactive in nature, they don't use predictions of future behavior of the environment. And oftentimes they're also, if you want to have valid functions, valid control barrier functions, for instance, you have to limit yourself on specific systems. Right? And there's a whole bunch of literature on predictive, interactive, and non-interactive methods, for instance, deep reinforcement learning, Gaussian process-based modeling and control. However, usually you don't obtain safety guarantees with these methods unless you make simplifying assumptions. So that's when we started asking ourselves the question, well, how can we quantify uncertainty here for learning-enabled predictors and design safe controllers? Now, if we look back at our block diagram, I want to ask the following question. How do we even reason about safety of such high-dimensional systems? And by high-dimensional, I now mean that in these learning-enabled feedback loops, we may have neural networks that contain of thousands of neurons, right? So how can we reason about safety or of input-output properties of these? And some people have looked into this, for instance, using satisfiability module theory solver, mixed integer linear programming techniques, or also hybrid systems reachability to quantify input-output behaviors of neural networks, for instance, or neural network control systems, for instance, analyzing reachability. However, these tools, they usually have scalability issues, and they don't scale to the complexity of the problem at hand that we have, all right? And for that reason, people have focused on convex relaxations of these methods, so to speak, using semi-definite programs or linear programming relaxations or even compositional approaches. However, here it turns out that these approaches are typically overly conservative and also don't apply to really complex problems. So what we'd ideally like to do is we'd like to navigate the trade-off between scalability and conservatism. And on top of that, we'd like to reason about stochasticity that enters this loop. For instance, disturbances on the car, noise on the sensors, or what we'll focus on here, stochasticity and randomness that enters through the dynamic environment. And that's when we really started asking ourselves, well, can we use statistical tools to formally reason about safety of learning-enabled systems, right? And what I'm going to argue here is that what we need is an online monitor that takes as inputs our state estimates, and it gives you uncertainty representation via efficient statistical abstractions, okay? So we want to kind of measure the uncertainty of our state estimates, so how good are these state estimates, basically, and incorporate this into our planning and controls models. And we want to do that by using this tool that I mentioned initially, which is called conformal prediction. Just to give you a bit of, I guess, perspective, zooming out for a second again, here, what you can see here in this plot are several different methods to do control design, right?
And on the x-axis, you see the verifiability of these methods. And the more you go on the x-axis to the right, the more formal your proof or your certificate for safety of a system becomes. Well, if you look at the x-axis and you go more up, then you get a more scalable method. So it scales to more complex systems. And I've carved out here in red the area for learning-enabled autonomous systems. And what we can see here, that statistical tools and statistical verification generally is highly scalable while still giving you some form of a guarantee and proof for your system. And conformal prediction is one of these. It's a statistical tool. And I argue that it's simple because it's easy to understand. It's general because it applies to general black box kind of systems. And it's efficient if you use it the right way. But what we should keep in mind here is that the guarantees are of probabilistic nature. So we can reason about safety with 1 minus delta probability, but we will not be able to say we're always safe with probability 1. Okay, so that's important to keep in mind. And if after this talk you're interested to learn a little more and also more of the technical details, we recently wrote a survey paper that you can find online. It's a 50-page paper. It has all the details and I think interesting references, especially to the community that works more on conformal prediction. Okay, so with that, I want to tell you a bit more about conformal prediction itself, about conformal prediction in a nutshell. All right, so conformal prediction has become popular because it gives you uncertainty quantification under minimal assumptions. What I mean by that is, A, it's distribution free. So if you have a supervised learning setting where you have inputs U and outputs Z that are drawn from some distribution calligraphic D, then you don't need to make any assumptions on this distribution calligraphic D. It can be any funky distribution. It doesn't have to be Gaussian, all right? At the same time, you don't need to make any assumptions on the predictor that you're potentially using. So if you have a predictor mu that takes an input and produces or estimates an output Z hat, that could be, for instance, a neural network, or it could be something more classical like a support vector machine, a Kalman filter, or whatever you're really interested in. What you need, on the other hand, is the availability of an IID, so independent and identically distributed calibration data set of k input-output pairs that are also drawn from this distribution. Right? And the goal then is the following. You as a user, you fix a failure probability delta, and conformal prediction gives you a region C such that a new test data point Z, so the output, is contained in this region C, which may depend on the input with a probability of no less than 1 minus delta. How does this look like in practice? Well, imagine you're given these 3 images that are of varying difficulty to classify its content, along with a classifier. Then for the easiest image here, the region C may only contain 1 label, the correct one, right? While for the 2 other images that are more difficult to classify, this region C may contain 4 or even 6 labels. So it quantifies the uncertainty of the task at hand. Now, the question, or the next natural question as well, how does conformal prediction actually work? And the vanilla version, so to speak, is based on a very simple quantile. Assume that you're given k plus 1 IID random variables R0 to Rk. And in the community, these are referred to as the non-conformity score. For now, you can just think of it as a prediction error. Okay. The goal then is the following. We want to find a probabilistic upper bound of our test data point R0 in terms of our calibration data R1 to Rk. So you can think of R0 as something you experience during test time, while the calibration data is something you have collected offline. And then the following can be shown. It holds that with a probability of no less than 1 minus delta, the test data point R0 is bounded by this 1 minus delta quantile of the empirical distribution of the calibration data R1 to Rk and infinity added. So the way this looks like is you just plot the histogram of your calibration data. So on the x-axis here, you have the potential values of R. On the y-axis, the frequency by which they're hit on your calibration data. You add infinity to this, and you compute the 1 minus delta portion here. Now, the question is, how do you compute this really? Well, what you do is you compute this number, which I denote by p, which is nothing more than taking the ceiling of k plus 1 times 1 minus delta, and then you take the p smallest nonconformity score. So all that you need to do is you need to sort your calibration data and pick the p smallest one. So the complexity here is that of a sorting algorithm, which obviously is computationally really efficient. You can do this online while the system is running. Now, there's an implicit data requirement because you're picking the p smallest nonconformity score. You need that p is not greater than the number k of calibration data that you have. It's otherwise the bound is infinity, you get a trivial bound. Well, how much data do we actually need? Well, we can simply, since k is an integer, we can remove the ceil operator here, meaning that we just want that this requirement is satisfied, and simple rewriting gives us that k has a lower bound of 1 minus delta over delta. So if you pick a delta of 1%, you need roughly 100 samples. All right. Another question here is how tight is this bound? Here we have obtained a lower bound of 1 minus delta. If you make the additional assumption that the distribution of your nonconformity scores is continuous, so if you have a continuous random variable, you can actually show that you also have an upper bound of 1 minus delta plus 1 over k plus 1. So as you collect more calibration data, your probabilistic guarantees will be sandwiched by or in between 1 minus delta. Right. Now, so far we assumed that we kind of had k plus 1 IID random variables. Why I think conformal prediction has been so successful in robotics and control is because all you have to do is you have to understand the previous slide, obviously, but then you have to design the nonconformity score according to the problem that you want to solve, right? So there's some engineering of the nonconformity score by which you can solve your problem efficiently. For instance, I just want to give you a very simple, naive kind of example. If we have a one-dimensional regression problem, we could define the nonconformity score simply to be the error between the output and the predicted output over your calibration data, okay? And in this case, if you apply conformal prediction to this nonconformity score, you get immediately that for a test data point, the prediction error is bounded by the one. So again, here, this is test data, and it's bounded by the 1 minus delta quantile over the nonconformity score of your calibration data. And you can simply rewrite this, and you can see in this case that your output Z is contained in this region, which is centered at the prediction and has a width of 2 times the 1 minus delta quantile. So it's a valid, statistically valid prediction. Now, as I said before, I think conformal prediction is simple, general, and efficient if you choose the right nonconformity score. Okay, just want to give you some examples here. For instance, in this F16 simulator, we kind of picked nonconformity scores to obtain prediction regions that were convex hulls, hyperrectangles, or ellipsoids. And here you can see they all, in black, you see test data points, and these regions all cover 95% of the data. And if you look closer, you could argue that, well, the convex hull gives you the one with the smallest volume, okay? So, and that's just achieved by choosing the right nonconformities. We have another example here where we have a robot that could go left, right, or straight with equal probability. So we have 3 modes, and we want to detect these 3 modes, right? So here you see test data in green, and you see a carefully selected nonconformity score that gives you these 3 black ellipsoids, right? So it detects kind of the 3 modes, left, right, or straight, and then it's an ellipsoid fitted to it that gives you minimum volume coverage. And this is as opposed to, for instance, the red region, which is just the Euclidean norm that you would choose over your prediction. Okay, so this is the basic, the intuition. There are a lot of questions that I often get on the type of guarantee that conformal prediction gives you. And this is a little more mathy, but I think it's important to understand what you actually get at the end of it. And these kind of vanilla conformal prediction algorithm that I've just showed you gives you marginal coverage. That's what the community refers to. And what I mean by that here is that the probability measure here captures the randomness in the draw over the test and calibration data. So over all the data that is random, R0 to Rk. And it's important to realize that this is in contrast to what we would ideally like to have, which are calibration conditional coverage guarantees, right? So ideally, we would like to have a conditional probability. Here, the conditioning is on the calibration data that we have. And in this case, the probability measure here would only capture randomness in the draw over our test data point R0. That would be, if we had that, that would be awesome. Unfortunately, it's impossible to obtain unless you make very restrictive assumptions on the nonconformity score, on the distribution, and so on. However, the good news here is that, again, if the nonconformity score has a continuous distribution, that your probabilistic guarantees is kind of, or the kind of conditional probability measure here is kind of beta distributed, okay? It's beta distributed with a mean exactly at 1 minus delta and with a variance that scales with 1 over k. Meaning that as you increase your calibration data, these conditional guarantees of your conformal prediction algorithm will approximately approach your 1 minus delta coverage, okay?
On top of that, you can slightly modify the conformal prediction algorithm, and you can obtain what I call pseudo calibration conditional conformal prediction guarantees. So you get calibration conditional coverage with high confidence. And the way this looks like is, as statements you see often in statistical learning theory, you have an outer and an inner probability. And the outer probability here captures the randomness in the draw over the calibration data. And the outer probability holds with a confidence of 1 minus beta. You can pick beta again. And the inner probability now captures randomness in the draw over the test data, R0. And what you do here in order to achieve this, instead of picking the 1 minus delta quantile, you pick the 1 minus delta, you pick 1 minus delta bar, where delta bar is a tightened quantile. And you can obtain these in 2 ways. I mean, the details here are not important. You can read this up. So important to keep in mind, conformal prediction, you pick a non-conformity score, you get a probabilistic upper bound, right? And those give you marginal guarantees that can somehow be related to calibration conditional guarantees. And you can even obtain these type of guarantees. So that's kind of what you should get from. One last thing I want to mention, conformal prediction runs under this IID assumption. And there are extensions that go beyond this setting. So if you have dependent data or not identically distributed one. So obviously I cannot cover all of this. There's robust versions, adversarial, adaptive, or weighted conformal prediction versions. I might touch on these 2 if time permits. And they are also summarized in our cell. All right, so now we learned about conformal prediction, and we can go back to our problem of safe control in dynamic environments. You remember I started with that in the very beginning. Now, our motivation here to apply conformal prediction is based on 4 observations. If we look at these 3 kind of scenarios we may encounter, then we realize, well, the system dynamics here, they're well understood and we can actually model them, right? Modeling a car or mobile robot is not really a challenge for us. But modeling dynamic agents that are uncertain is in general a hard problem. However, we're now living in a data-rich world. So we may have large data sets, maybe even publicly available, Waymo data sets or so, that we can use that describe behavior of dynamic agents in the environment. And we have these previously already mentioned learning-enabled prediction algorithms that are really powerful. So we want to use all of this together with conformal prediction to design safe and computationally efficient control algorithms. And before I go into the details of this control approach, I want to give you a high-level overview. What we assume here is that we have an offline trajectory dataset, our calibration dataset, which in this case, you can think of it as a set of trajectories from pedestrians at an intersection, right? Now, during test time, we assume that we observe the state of the pedestrian at time t, and we have potentially a history of those. So y of t minus 1. And what we do is we use a trajectory predictor, for instance, a learned predictor here, a recurrent neural network, to predict the future behavior of the pedestrians, here indicated by y hat t plus 1, y hat of t plus 2, and so on. Right? And the natural question is, well, how good are these estimates? They could be accurate or they could be pretty bad. So we kind of want to quantify that. And in order to do that, we use conformal prediction. And what we will be doing is we'll be computing these prediction regions, these blue regions that are statistically valid in the sense that it will contain the trajectory of the pedestrians with a probability of no less than 1 minus delta. And we then feed these prediction regions back to our robot where we know the dynamics, and we design a probabilistically safe controller. In this case, an MPC, a model predictive controller, that makes sure that a safety constraint C that is coupled over our system X and the environment Y is non-negative. And the advantages or the contributions here of this approach is it's a computationally lightweight algorithm with statistical guarantees. And if there's time, we'll see how we can deal with distribution shifts and temporal logic specification. All right, so first thing I need to tell you a bit about is how can we represent uncertainty in dynamic environments. So I want to set up the stage. We have a discrete time random trajectory that models our environment. Y0, Y1 is drawn from some distribution over trajectories, calligraphic D, and this could be any discrete time stochastic system, for instance, an MDP. We use a trajectory predictor that maps observations into predictions of the future for a finite mission horizon time, capital T. In our case, we use the social LSTM, so every agent in the environment has an LSTM, and the weights of these LSTMs are getting pooled to model social behavior. And for those, we want to compute these blue prediction regions. I'm going to show you 2 approaches, a naive approach and an approach that works way better.
the naive approach is very intuitive. It would be the first thing you do. So for each time that you're predicting into the future, so for each time tau could be 1, 2, 3, and so on, you pick a non-conformity score as the prediction error for the tau for tau steps ahead. So you're taking the ground truth y tau over your calibration data, you compare it to the prediction that you're making for tau steps ahead, and you take the Euclidean norm of that, and you compute that for your calibration data. Then you apply conformal prediction to this non-conformity score, but not with a 1 minus delta quantile, but with a 1 minus delta over capital T minus T quantile. So you're making a minor correction, because what you want to obtain are multi-step prediction regions. So for a new test trajectory, you want that the tau step ahead prediction error is bounded by this quantile C tau for all steps that you're predicting into the future, all right? And this is statistically valid. We evaluated this in Carla, a driving simulator with pedestrians with random initial conditions, goal positions, and velocities. And what I'm plotting here is the histogram of the 2.5 second ahead prediction error. On the x-axis, the error, on the y-axis, the frequency. And importantly, it's a bit small here, but in green, you see the prediction regions for increasing mission horizon time t over here. And at the same time, you see similar behavior 4 seconds ahead. As you increase the mission horizon time, the prediction regions, they kind of increase. And yeah, so the outcome of this is the observation that the size of the regions basically becomes more conservative as you predict more into the future. And that's somehow undesired. And the question is, can we do better, right? The reason why we have this conservatism to begin with is because we're kind of looking at a modified quantile. Instead of 1 minus delta, we're kind of tightening the quantile, and we're being more conservative than we actually need to be. And the question is, can we avoid that? And the answer is obviously, if I'm asking this, yes, we can. Here we're running multiple conformal prediction instances in parallel. But what if we only defined one non-conformity score and we use one conformal prediction instance? For instance, we could take the maximum over all the prediction errors at all the future times, right? So we take the maximum at the prediction error at time step t plus 1 up until the capital time t. And if we add a carefully selected normalization constant. For now, you can just assume that the normalization constant is 1, okay? But you can choose these optimally, which I'll show you on the next slide. Now, for this non-conformity score, it follows right away that you again get multi-step prediction regions. So you know that the tau step ahead prediction error is bounded by C, which is now the 1 minus delta quantile over this max non-conformity score, and then renormalized with alpha tau. And I think the benefit of this is best illustrated in an example. Assume you're predicting 20 time steps of a pedestrian, here shown in blue. Then in red, you see the statistically valid prediction regions of this naive approach, while in green, you see the prediction regions of this max approach. Arguably, you get much tighter regions while still being statistically valid. And in fact, if we look at the 2D kind of plot of X and Y position, at, for instance, 1.25 seconds ahead, we see that, in fact, we were aiming for 95% coverage, and we cover 95% of our data with this prediction. So one thing I haven't told you about yet is how do we actually choose these normalization constants optimally, these alphas, right? And we do so by solving an optimization problem. So the outcome of this optimization problem will be the optimal normalization constant that kind of gives you minimum volume. And what we're doing here is first of all, we're enforcing the non-conformity score to be a constraint over our data. We're minimizing our 1 minus delta quantile, and we're enforcing a normalization budget. This basically avoids that you get trivial solutions such as alpha being 0. Right? And two important takes here. You can solve this problem offline, first of all. You don't need to solve it online. And if you look at it carefully, it turns out it's a mixed integer linear complementarity program. Because the quantile here can be rewritten as a linear program. Then you have a bi-level optimization problem, okay? And then you can rewrite the inner problem with the KKD conditions, and that gives you linear complementarity constraints. And at the same time, you can reformulate the max operator here also as a mixed integer linear problem. Okay, so now that we have the prediction regions, we can basically go ahead and we can do control design with them. And the simplest, maybe not smartest thing would be an open loop kind of control design. So you could say, well, I want to compute my control inputs at time 0 for all time steps to minimize a cost function subject to dynamics constraints, input and state constraints. And importantly, we're enforcing here a robust safety constraint. So we're making sure that our safety constraint
is satisfied for all states of our environment in these blue prediction regions that we have. This again is a bi-level optimization problem that you can rewrite, for instance, if the constraint function C is Lipschitz continuous. What you're doing then is you're evaluating C over your prediction and you're tightening the constraint by the Lipschitz constant of C and your prediction region, all right? And if you can solve this problem, you have found a safe controller with a probability no less than 1 minus delta, okay? Just quick example here, toy example, we have 3 agents in the environment in a mobile robot navigating around. At time 0, we're building these prediction regions and we're just planning around. Right? The obvious drawbacks, while it works in this case, is that it's potentially conservative, especially if we predict into the future for longer time horizons. And if we can't solve this optimization problem, we don't find a solution at all, right? So next natural step is we want to have a receding horizon approach, such as a model predictive controller, where at each time step we take measurements, we make predictions, we recompute our prediction regions, and we solve this optimization problem again. So here at each time step, we update this robust safety constraint. We potentially do so only over a finite mission horizon. And then under the assumption that this MPC is recursively feasible, so we can solve it at each time step, we're guaranteed to find a safe controller with a probability of at least 1 minus delta. Now, the recursive feasibility here is, of course, an issue, but I think this goes back to a much larger problem of how do we ensure recursive feasibility of optimization-based solutions when algorithms interact with uncertain environments, right? Which is exactly the case here. We have one work where for shrinking horizon MPC, we can kind of modify this constraint to retain recursive feasibility, but I would say in general, it's still an open problem. Nonetheless, I mean, we implemented this on the same example. What you can observe here is that basically these cylinders, they shrink over time, and we can plan a much better path. So here, it's a straight path that brings you directly to your goal. We also validated this on Carla, an autonomous driving simulator, like I said before, on the pedestrians here. And first of all, we empirically validated our theoretical guarantees. So here we had 99.83% coverage, what we were guaranteed in theory. In practice, we found we're slightly above that. We were also guaranteed to have at most 5 safety violations, and we only observed 1. We did a small comparison with the Gaussian process to model the pedestrians, and we found that at least in this case, they were largely undercovering. They were only giving us 70% coverage. Okay, so one thing I want to talk about that I think is important, especially from a practical perspective, is dealing with distribution shift. And I'm sure you have heard about distribution shifts. Everyone has their own kind of definition of what distribution shift is in a way, or can differ. So I want to give you a very general one. For me, a distribution shift is if the design and the deployment conditions are different, right? In what we just talked about, this may, for instance, be the case if we have calibration data collected close to a nursing home with old people walking, but we now want to deploy our algorithms close to an elementary school with small kids, right? So obviously, in that case, there's a mismatch between the data that we have collected offline and the one we will be encountering online. Another example is we may be having data from potentially photorealistic simulators where we want to deploy the systems in the real world. Well, these are arguably quite close. They're not the same, right? And in that setting, all our safety guarantees are being thrown out of the window. In fact, there's some work in conformal prediction that tells you that these guarantees degrade gracefully. So for small distribution shifts, you only violate your 1 minus delta guarantees slightly. But in general, you lose your safety guarantees. Question is, what can you really do about it? Well, there are many versions of conformal prediction, and one of those is robust conformal prediction that we use, where basically you assume that your calibration data is drawn from this distribution calligraphic R, and your test data point is drawn from R0, and you make the assumption that some distance, in this case an F divergence, there are other kind of measures between distributions, is epsilon bounded, okay? And what you can then do is you can robustify your conformal prediction guarantees to get, again, the same kind of strong guarantees, but now with a C tilde, which is not the 1 minus delta quantile, but the 1 minus delta tilde quantile. And delta tilde is a tightened quantile that depends on the distribution shift epsilon. So the more distribution shift you have, the more you need to tighten your quantile. And in fact, the delta tilde, you can simply compute it as a solution of a set of convex optimization problems. Now, there are some trade-offs One being you need more data, obviously, right, if you have a distribution shift. And another one is you may not be able to select an arbitrarily small delta. But in principle, you can use this, and then you can go ahead and you can design your controller using robust conformal prediction. Another question as well, what is the distribution shift is too much, right? For instance, here, this is unrealistic that we get any useful information from our data. And what we could then do is we could, for instance, use adaptive conformal prediction from an online data stream. I don't want to go into details, but the high-level idea here is that you're computing your empirical coverage that you have observed over your trajectory, like how good are your conformal prediction regions. You compare this to your desired coverage, the delta. You multiply this error with a learning rate, and you update your coverage level that you use to compute the prediction region. And what we then do is we design an MPC, again, using these regions, and we get slightly weaker guarantees. We get controllers that are on average safe. So here you see we average over our safety constraint over time steps. And asymptotically, as t goes to infinity, we also recover our 1 minus delta on the right-hand side. We implemented this also on a drone that was supposed to avoid flying frisbee. And here we were aiming for 97.5% coverage. And the important thing here I want to show is we achieved 99.2, while two competing methods, one of those being an extended Kalman filter, had 100%. So they were overestimating the uncertainty. And the outcome was basically that the distance from the drone to the frisbee was way too large. Okay, so it's larger than ours. Ours was much smaller, and we were able to fly the drone actually closer to its performance limits. All right, I think, do I have 1 more minute or? I have 5 more minutes. Okay, then I can do this too. One other extension I wanted to briefly talk about is so far we talked about navigation specifications, right? Going from A to B while avoiding obstacles. But you can extend this to arbitrary high-level specifications, for instance, in a temporal logic framework. And we heard about temporal logics already a little. It's, for those of you that don't know, it's Boolean logic that is equipped with temporal operators such as eventually, always, and until. And I don't want to go into syntax or semantics. I just want to show you an example that shows the expressivity of temporal logics. For instance, for this drone, you could say always avoid region E, every hour inspect regions A and B. Whenever the battery level of the drone here is low, go recharge in region C or D, and between some time, turn on some communication device, right? So fairly high level. The good thing is you can denote, or generally you denote a temporal logic formula by the symbol phi, and you can associate a performance measure rho phi with it. This performance measure is positive. It means you satisfy your logic specification. If it's negative, you violate it. And the more positive it is, the better you're doing. Okay. Now, what we're doing here is we're looking at a performance measure in temporal logic that couples, again, our system X and our environment. And we proceed as before. We take a trajectory predictor, we predict the future behavior of the agent, we compute the prediction regions. But now, since the task is more complex, we need kind of compute not a performance measure, but a robust performance measure, rho phi bar. And what this is we're basically computing the infimo over our performance measure over all the states of our environments that are in these prediction regions. And then in an outer kind of step, we maximize this robust performance measure by picking the right control. You can solve this recursively on the structure of the formula. And well, we have some case studies over here, but I think in the interest of time, I'll stop here and I'm happy to answer any questions if you have.
Yeah. Thank you for the talk. I have a question about maybe technical about the use of conformal prediction in control. So if I understand the intervals you get are over a distribution of states and controls. So once you start putting planning into it, the planner might choose control that will be completely correlated with the competence regions, right?
Yes.
You could go out of distribution.
Yes. Yeah.
So how come you have guarantees of safety? Because
so in this case, the assumption is that the environment is not affected by the control system. And this is arguably a strong assumption, right? Because it means that the pedestrians that are potentially there, they will not react to my control signal, which only holds if you're having a controller that has some conservatism, right? The moment you get closer, you will induce a distribution shift. And you will have to incorporate kind of this distribution shift. And that's also why I talked about these robust versions of conformal prediction. And there are, I think that's where really people are looking into right now, how you can do this, incorporate this, right? I think one way would be to assume a model of interaction and kind of try to bring this into the picture, right? If you know how the interaction really is. Or to do some iterative schemes, right? That would also be. But yeah, that's really, yeah, I mean, this is one of the core problems, how you deal with distribution shifts, and interaction is one of those.
Okay,
yeah.
Thank you.
Yeah, thanks for the great talk. So one thing when I think about safety generally is I like to think about what the worst thing that can happen. When you do conformal prediction, you're kind of chopping off the tails and saying, let's only look at, what happens 90% of the time. How do you think of this as a sort of a safety for control in that context?
It's almost a philosophical question in that sense, right? I like to think of or take inspiration in aerospace. Certifications of airplanes, right? I mean, you kind of, you have components and you certify that, like there's 1 in a billion kind of, right? I mean, it's a probabilistic statement that they want, right? It could go wrong, but what they do is, I mean, they are aiming for 1 in a billion, but maybe the component has 1 in 100,000, right? And what they do is they need to certify this, right? And they do this through exhaustive testing, but they have redundancy in the system. So I'm not saying, this is what you should put in a car, but it's one component among those that you should have, and in parallel with others that give you redundancy, right? If you have 2 systems, for instance, if you have a planner that gives you 1 minus delta safety, and in parallel you use a monitor that monitors safety that also has 1 minus delta, and they're independent of each other, then you multiply this failure probabilities and you get much lower, right? So that's how I think of it in general. Yeah.
Thanks.
Any more questions? I think that's right.
So what do we lose when we use conformal prediction? Is conformal prediction just better way of handling error than assuming, say, distributions over neural networks? So what is the trade-off in using conformal prediction? Is it just better in general?
What do you mean by distributions over neural networks?
Like if you are using Bayesian neural network, like ensemble.
This is a frequentist approach. I think that's the benefit that you have. You have a frequentist approach, while with Bayesian approaches, well, you have a Bayesian approach, right? If you choose the wrong prior, you're kind of completely off. And this was also in the case study where we used GPs. Arguably, we're not experts in picking the right prior, so it may be a little misleading, but I think you do this, you get statistically valid guarantees. There's no question about, well, what prior do you pick and so on and so forth. And I think it can even be complementary. So there's work that combines kind of Bayesian approaches with conformal prediction. So you use a Bayesian approach first, you conformalize on top, and you still get your frequentist guarantees. Yeah.
It's last question.
Yeah, so one of the questions I had is you mentioned you kind of gave a formula about how many data points you might require based on the probability. But is that does that not account for the size or the dimensionality of the state space and how much do you?
Yeah, since the nonconformity score is a scalar, it's independent of the underlying problem that you may be having. So let's say you do image classification or whatever, right? You're living in a very high dimensional space, but you have to find a nonconformity score that boils all of this down into a 1D kind of representation. And that's why it's not dependent, the kind of data points, the number of data points does not depend on the dimension of the problem. But if you pick not a good nonconformity score, you will get really large regions. So I think the kind of question here is more like, what is a good nonconformity score? To give you tight guarantees. But then it's independent of the kind of dimension. That being said, there are some more recent works that look at conformal prediction not in a 1D setting, but in a 2D, 3D kind of setting, whatever you're looking at. And I think there the dimensionality shows up again.
And let's thank the speakers. So for the next hour, we're gonna have a poster session outside. So feel free to talk to poster.
Please check the posters.
Please check out the
We are combining this with the coffee break, but the coffee break hasn't started yet, so we have to stop with the poster. It will be back. It will be back.
No, after that, it's, yeah. And 30 minutes after. So in hour and a half, that's what you do.
No, I'm reading that. So where? So I need to
in an hour.
So I know there is a sudden thing. It's a complex even one tell me that answer for that. I don't know. That's all the time. Any one or two a minimum time and the objective is start
Your name is Ayo?
Yeah, I am.
Ayo.
Yeah.
Ayo.
Yeah, I am.
Okay.
I after this talk, I have to run for a panel.
Okay.
So I try to finish this one like 4:10.
4:10?
Would that be okay?
Yeah. For all, right?
For 1:0.
For one.
Yeah. Okay.
15 was the original schedule.
Okay, sure.
But,
Okay.
Yeah,
No
give us
problem.
like 2-3 minutes.
Should be fast. Yeah.
So stop the question before that. Yes.
Okay, sounds good to me. So am I the next one or?
You are the next.
Okay, then I will just have
Yeah,
the
you can-
connected.
Yes.
I just need to have power so that it doesn't run out.
Oh, red, the plug is ready. You have the charger?
Oh, okay, yeah, I have the charger. So she just needs to leave the onions early, right?
5 minutes.
Is that what she said?
Yeah, 5
Yeah,
minutes.
fine, okay.
Yeah, so
Just do that.
so hopefully she finish first and then you cut the.
Right, but
the
if
question.
she finish her wrong, before 10, should I allow questions?
Maybe like you to say she needs to go, maybe look
Okay.
around. Yeah.
I see.
Right.
There's another pen, another bar.
Yeah, they say that this meeting is recorded. So okay.
Is it? Oh, yeah, that's even better. Okay, thank you very much. Nice. Solve the problem. So all ready? Okay. So when the next speaker comes, anything I should be aware? Anything I should be aware when Georgia is here next after she finishes?
No, that's fine. Okay. Just muted. This should be muted. I wonder if it's muted. Look again. Participant. Because I think she should mute. We check if this is muted. I see.
I didn't do it. Yeah. Do you want me to do it? No.
No, we want to mute it. That is really so that's nice. Maybe for slide. Oh, okay.
The mouse. Better.
Sorry.
Okay.
Yeah.
Your phone is strong. I'm very robust.
Yeah, I think that like.
Do you have any audience?
No.
Okay. This might help you. Yeah, nice. I just read this bio. Oh, yeah, sure. But like people just, easier to see. Yeah, definitely. Let's wait for a few. Okay, sure, yeah. I think people are still trying to coming back from the post. Oh, yeah. Yeah, it's
I'm not gonna do that. Maybe they have that.
because could you check whether people from the poster session want to come back?
Yeah.
It's almost time.
It's like a big,
Okay. Don't worry about too much. I can also make this talk between 20 to 40. I can observe or 20. Sounds good. Yeah. Okay. Thank you everyone for coming back. This afternoon session will be on safety in robot perception and real-world robot deployment. And I'm Yiwei, one of the co-organizer of this workshop. And we're very delighted to have our first speaker for this afternoon session, Ayoung Kim. And Ayoung is associate professor in the Department of Mechanical Engineering at Seoul National University, where she has been a faculty since September 2021. Her research focuses on perceptual robot autonomy with an emphasis on navigation and spatial representation learning. So before joining SNU, Professor Kim was a faculty member in the Department of Civil and Environmental Engineering at the Korea Advanced Institute of Science and Technology, the KAIST, from 2014 to 2021. And she holds bachelor and master degree in mechanical engineering from SNU, as well as a master in electrical engineering and a PhD in mechanical engineering from the University of Michigan, Ann Arbor. All right, so let's welcome our speaker.
Thank you very much. As introduced, my name is Ayoung, and today I want to talk about the robot safety, robot navigation, and by using some sensor beyond visible spectrum. So basically, I'm going to talk about something different from LiDAR and camera. I think our group has been working on this non-conventional sensors for years. So you might have heard my keynote at IROS 3 years ago and some of my talk. But today I want to introduce some of our recent work that will be presented in ICRA and in ICRA. So why we need thermal or radar sensor? It's quite obvious because when you have to fly a drone in a smokehouse, actually that was a project that motivated me because I was a junior faculty like 7, 8 years ago, and I had to fly a drone in a fired house, and I found that camera is not working, LiDAR is not working, and I was frustrated because there's not the camera LiDAR failed, and then I don't know what to use at the moment. And if we think about driving a car in a rainy night, it cannot work because we humans can drive a car during rainy night. We know we can do it, but we want safe and more robust. If car is going to automate it and drive for themselves, can it have some more sensor ability beyond visible spectrum? So let me start this talk. So basically, I want to talk about the radar and thermal camera capability beyond this visible spectrum because they have a longer wavelengths. They are much more robust to the particles. So we call the radar as all-weather sensor, and we call thermal camera as all-day vision. But as you see from the bottom, the radar and the thermal images are not really vivid. They have a lot of noise, and there are many things that we have to overcome. So our group has been working on this issue for many years, and today I want to introduce some of work. So today's talk will be in 2 parts. First one is the radar, and the other one is the thermal. And I'll start with the radar as all-weather deployment. Basically, if you go into the radar, there are 2 types of radars typically used in robotics. The first kind is on the left, imaging radar. That is the output measurement is the image format. And basically what it shows you is the bird's eye view of an environment. And you can think of that as a top-down view. Those are the rows, and there's a little particle moving around. That's the cars passing pedestrians, and those passing by dynamic objects are also captured. But what I want to talk more is not the imaging radar, but the tracking radar on the right. That gives us a 3D point cloud. So similar to LiDAR, so a 3D point cloud, but only a handful of points, like 20, 30, at most 50. And the question that we have is, okay, we are used to very dense, rich point cloud coming from LiDAR. Can we do something par or better, even better, with the sparse handful of the sparse radar points? And also, we call this one 4D radar, but there are some radars, alternative radars that goes for cars, but not only for that. Recently, we have a Texas Instrument system on chip radar that's very small, about my palm size, and very low power consumption that can easily go to your mobile robot or drone. That's actually also have a wide application potential. So we'll talk about the right-hand side of the radar mostly. So what we can do, we were thinking about maybe we can enhance existing odometry or SLAM with radar. So we thought about what we can do. So we thought about maybe the leg odometry from the leg robot, their state estimation, internal state estimation, combine the leg and IMU, and they can estimate their angle motion without any extrovert sensors. But if we add radar with it, could we improve this one? Was quite obvious, actually, if you know how the radar works. So this is the red one, is very small one on top of the spot. That's the TI sensor that I mentioned. That's very low power consumption, and then it gives a very handful of very sparse point cloud, but we have a strong advantage with it. What it is some of you might know, some of you are not, but for those of you not really familiar with radar, I want to give kind of radar 101 quickly here. Radar can measure velocity, not only the range, but also the velocity. And what radar measures is the radial relative velocity between target object and you, yourself, the robot. So which is in that we are the radial velocities, what we can measure from the radar sensor. And the range may be very noisy and spotty, but the velocity measurement is coming from the Doppler shift, and that's very accurate. And what we know is if we are moving in the red arrow, we are moving in one direction, all of the static object movement should be consistent with me. And what is not consistent with me should be dynamic object. So if we do that, we think about this one in a mathematical way. If we plot V versus theta, the azimuth, and if we try to fit a sinusoidal curve with it, whatever the dot that falls into the sinusoidal curve, the sine curve, will be from the static object, and what's not outside of the sine curve will be the dynamic object. So it's a very simple sine fitting will give you a dynamic object segregation from a quick math. And then what we can do from there, so we can only capture the inlier or the static object only. And if we solve for our ego motion, it's a very small optimization problem, and then we can get our ego velocity from the static object. So we can get our ego linear velocity, and what the leg odometry is doing is they have a kinematics coming out of it. They all have their own ego velocity estimation. If we compare those two, we can correct what's coming from the leg and some error coming from the radar. So that's how the SLAM does. Like if two sensors coming in, we compare those two together and then try to correct each other. Yeah. So we had an idea of correcting the leg with radar, and by combining this radar measurement with the leg measurement. And this is the result. We run that robotic system in a two-storied indoor garage environment and moving back and forth. We use LiDAR SLAM as a baseline. So the white one is the LiDAR SLAM. We know that this kind of indoor situation, LiDAR SLAM is really accurate. So we were using LiDAR SLAM as the baseline, and the green one is ours. And as you can see, ours is doing quite well. The combination of this radar and leg was quite promising, and especially in the Z direction. The bottom, what we are plotting is a Z directional error, and others are all going up, but we could manage to keep this Z directional drift very low, even if we are moving from indoor to outdoor and then moving up and down. So we saw the leg odometry can be improved with the radar. And another thing that we want to do is there's a LIO or LiDAR inertial odometry, really popular. And then there's tons of work happening in this LiDAR inertial odometry. If we use radar, can we enhance the LIO even better? So the existing LIO, how that works is they estimate the gravity, but from the IMU and the pose estimation. And so by combining a LiDAR and IMU only, and they don't have any information about linear velocity. Angular velocity and linear acceleration is measured from the IMU, but you have to double integrate to get a pose and then calculate, correct your LiDAR drift or the IMU bias. But what if we have radar together with this? So together with LIO, if we have radar, we can dramatically correct the error and then look at the gravity error in the yellow when we were using just LIO and the Z directional drift that we got from the vanilla LIO. But if we add up the radar measurement, and then if you estimate your gravity direction from it, you can actually reduce that gravity error a lot significantly using the radar. And as you see from the bottom plot, our Z directional drift is a lot significantly reduced. So this is quite nice. But the reasoning behind it is very simple, isn't it? Like if the radar gives you velocity, estimating your ego acceleration from pose couldn't beat when you have a linear velocity estimation, right? So we can leverage that linear velocity measurement from the radar to enhance this one. And also at the same time, we can just apply the same technique that we did to the dynamic removal, apply that fitting, and then we'll know directly by reprojecting the point to the LiDAR or camera images, we know oh, this part is the dynamic object, this part is a static object right away from the radar information. So we enhance the LiDAR odometry as it is, and we enhance this entire pipeline with the pointwise radar velocity residual. But lastly, we refine the entire pipeline with this refinement with the gravity residual. So the main thing here is we try to estimate our gravity direction. And then once you know the gravity direction, the other error could be reduced significantly. So others are the top left corner is ours. And the others are from Leo existing method. And yeah, we could improve one, but maybe some people think, yeah, the more sensor, the better. That's quite obvious. But what we want to say here is, okay, there's a limitation of the LiDAR. Can we improve even better? If we have to overcome the Z directional drift, what should we use? What sensor modality we need to improve that part? And then on the right, what that white and red arrow is indicating is the gravity estimation on fly. So what another thing that we can achieve from here is what people have been doing to estimate gravity. Another way to do the gravity estimation is you go and stop, and then your acceleration is 0. The only acceleration measured is gravity. So you correct your gravity. Move a little bit, stop. But we wanted to do this one on fly without stopping. And then this one, this graph, this flash shows you the gravity estimation on flight. So I know it's not super accurate. You see it's kind of moving a little bit, but still that's even actually a lot improved, and that really improves the Z direction drift, and you can do many other things. And then we thought about this, like this one is gravity enhanced radar. Leo will be presented on Wednesday. If you are interested more about the technical stuff, you can visit us and talk more about this. And then after combining with these two, what we think about is what if we just do it on radar only without lag or LiDAR? What we can do with a radar only if we just only to combine radar with the IMU. This is the best paper award finalist, and luckily, and I'm very thankful, tomorrow at the award session. So you can come and discuss with us and then what we could learn from it. But the basic idea is much more difficult if you were to do this one with a radar, without radar or without lag, or we try to do it radar only. So the question we have is, can radar replace LiDAR? I know it's a kind of radical question. I'm not really trying to get rid of all the LiDAR, but I mean, I wanted to see how far we can go. LiDAR SLAM, as you can see from that, from that's captured from one of the benchmark results, is really super accurate. Like you see less than a meter, and sometimes almost a centimeter level accuracy from the LiDAR odometry we achieve by the time now. And there has been a lot of work done in an imaging radar field, and they try to achieve LiDAR level localization accuracy using an imaging radar. And they actually was very successful. They were very successful achieving their goal. And this is called the CPR, and this method, they achieved almost 1 point error at one of the Oxford benchmark data set, but they were using that imaging radar, that is high resolution imaging radar in a 2-dimensional. What we wanted to do is we go from there and we wanted to achieve LiDAR level accuracy with 4D radar. Now, not the imaging radar, but with a handful of point cloud or the sparse point cloud and noisy range measurement, can we achieve the LiDAR level? It's kind of a radical question, but this is something that we've done. We are not saying that we achieved the LiDAR level, but this is made a lot of improvement, like toward that direction. So something that you can probably learn if you come and visit us tomorrow in our session. But here I want to give you a brief introduction of what it is. So first thing is LiDAR odometry, they've been heavily using ground, and having the ground detection running really helps when you want to do a range SLAM, range sensor SLAM. But the problem is the range measurement is very noisy in the radar. And how could we incorporate the radar specific noise characteristic and then reliably detect ground and then incorporate that into the ground optimization? So we had to look at the radar, and the radar is, as you can see, it's very noisy and there's up and down. We incorporated some of the zoning method and the uncertainty associated and made it work with the ground optimization. And secondly, this is real. So IMU is there. And there's an amazing work by the Teresa a couple of years ago. They enabled the GP for Gaussian process for the IMU pre-integration. And knowing the ground, using the Gaussian process is really helpful, because if you were to tightly couple and make a radar IMU pre-integration vector, for example, the IMU frequency and the radar frequencies are different, but the Gaussian process is implicit kind of function level. So you will have there's no motion model assumption. You don't have to linearly interpolate anything. If you fit a Gaussian process to it, you can have very tight integration, and you can overcome the time synchronization issue between two different sensors and then enable the very tightly coupled radar IMU pre-integration vector. So these two are the key contribution that we made toward this direction. And first, for the ground detection, we look into the zones because it's very coarse and noisy data set. And for each zone, we look at the point-wise uncertainty, and we can fit the plane, but considering the radar uncertainty per port. And then if we do it compared to the naive ground filtering that fails, like ground and the radar noise are mixed on the right. In the middle, you see a lot, sorry about the video encoding, but believe me, this is actually, it's much more cleaner, filtered radar point after this. Yeah, if you go to the YouTube, actually, you have a much more cleaner, but I think, believe me, it's just working here nicely in the computer running. Right, so you can make it filtered nicely for the ground detection. Now you can incorporate this one in the ground optimization for the radar. And also for the radar IMU pre-integration factor, there's not only the IMU, this one is for the IMU pre-integration in the Gaussian process, but we don't need that because now we have a radar and we enhance the IMU pre-integration, not the IMU integration, but the radar IMU pre-integration. The good thing about it, you can have the double integrated value from the Gaussian process from these equations, and where you don't need direct, you can just do the direct inference of your integration at any time. This is continuous function. No motion model assumption needed. So it has really strong advantage. So those two really help us to make this is radar inertia odometry, no LiDAR, no lag, no other sensors. And then we achieved here, on the right, there's a Z directional drift. This is 0.63% G direction elevational drift. That's quite significant improvement over the existing radar inertia odometry. That is like 18-meter drift over 2.5 kilometers. So we made this one work, I think, and then the next one is we try to ship this, combine all these pieces together and make a nice final radar, ultimate radar slam. All right. We test this one with many different scenario benchmarked, and then we could achieve a substantially improved result. All right. So next goal for us is to combining those pieces together to complete the radar, ultimate radar slam. And on the other hand, the next topic is about the thermal infrared camera. So thermal camera is quite interesting. It has very interesting characteristic. It's kind of interesting, ironic to tell you that we actually started working on thermal camera 6 years ago. And this paper is at the RA letter 19, so 2019. And at the time, we completed the thermal LiDAR SLAM system first. And then we realized there are so many problems that we have to solve to make it really work better. So our research started from like backward. We started from the entire pipeline, entire SLAM system first, and then we comes back to improve each module one by one. So this SLAM system is direct SLAM. So direct SLAM, individual direct SLAM, what you calculate is photometric error between sequential images, but instead of the photometric error, you can calculate the temperature distribution and run the visual direct SLAM. So that's what we did. And combining with a LiDAR, you're gonna get a really direct measurement of the depths. That really helps. On the left is a daytime SLAM result. On the right is nighttime SLAM result. And for thermal camera point of view, there's no difference. They don't care if it is night or day, it's the same. The point cloud here, though, is not a colored point cloud as we think. This is temperature. The color here indicates the temperature. The blue is 0 degree. The red is 30 degrees Celsius. So you can actually, from this map, you can see how the temperature distribution look like. So it has many advantages, but only after we complete this one and we think about many other issues. Thermal images are not very vivid. They are 14-bit. And compared to the 8-bit images that we are using for the RGB, they have more bits, they have more resolution, but they are not vivid. And then, which means we need some signal processing or image enhancement. For that, we were using direct SLAM, so we were just comparing the 14-bit value to the other to get the SLAM working. But if we were to use maybe object detection, or if we were to use a feature-based one, we would need to convert that into the 8-bit images to apply many deep learning leveraging techniques or something like that. So that was the first topic. And then we realized if we wanted to go for the deep learning for the thermal data, thermal images, there's not enough well-labeled data set available to pursue researches toward the deep learning for the thermal. And the last thing is the conventional calibration works very poorly, and we introduced new sensor calibration methods. So during the last 6 years, we've been working one by one, tackling one issue and one by one. And this is a RA letter paper we'll introduce in this Wednesday. Why the thermal images are not vivid? Because if you look at the histogram, the RGB has very widely spread. The diversity is much more. In the histogram, you see much more diverse distribution of the pixels intensity. But the thermal infrared, even if that's 14-bit, they're really spiky in a very narrow range that only intensity exists. The distribution is very limited. And then when we see them on thermal image, that they're not vivid. So the quick answer for that is getting the minimum value and maximum value and stretch that out to do a histogram equalization and make it more diverse and vivid. That's one possible. And then to do so, we need the mean value and the max value. Our finding is getting a mean and max for globally over the image. Instead of that, what if we have a mean field and max field of locally changing value and extend that within that range? We can exaggerate the changes within the thermal image and make it more vivid. The rightmost result is coming from ours, and then it's non-deep learning is a very lightweight algorithm that can run in your computer easily, real time. And you can see this enhanced image is much more vivid, and now you can run a typical object detection or a semantic segmentation algorithm to it and make it work. And then once that's enhanced, we still need to overcome some challenges and then how to calibrate. So when we were doing the LiDAR camera SLAM, this is how we did. So we had a PCB board with a metal and a plastic pattern, and we heated this checkerboard with a heat gun and let it cool down a little bit, and there will be a temperature distribution, a difference between the metal part and the plastic part that looks just like a checkerboard in a thermal imaging. And then we can do calibration and then calculate find out the lens distortion, something like that. But this is what it looks like from the checkerboard. And if you were to calibrate the thermal image, you have to closely look into this image and then click on each corner and make it work, right? And this is super hard because it's very blurry. And we thought there are circular patterns exist in the world, and if we use a circular pattern, even if the edges are blurry, it's still okay if you can detect blob. You can maybe calculate or detect the center point, and that should be much more reliable than point-wise clicking for the thermal image. So yeah, let's go with a circular pattern. Yeah, right. Because if I ask you to click on the point, and you have to really carefully look into this image and then try to click right on corner, but it's not easy. Whereas detecting a circle is much more easier. But there's a big problem for that. Point is okay, because if you go from a point project to another point, if that goes through a distortion model, which is nonlinear, point goes to another point. So you can trace this point with set of equation, and then this point is also detectable from an image. But point detection is straightforward. But this point, the center point of the 3D circle, if you project this point to another point, and if it goes through a distortion, it will be mapped to here, but this point is not measurable. You might think it's a little bit confusing, but think about it this way. There's a circle in 3D space. If you project, after projection, circle will be ellipsoid. If you look at it from the side view, it'll be ellipsoid, right? Without distortion. Circle and ellipsoids are totally describable with equation, okay? And if distortion happens, radial distortion, how that affects to an image is that look at the distance from the center pixel to the radial pixel, and that is nonlinear mapping. So the ellipsoid distorted into a shape, and that shape is not describable with any equation. So conic is not a conic anymore after this distortion. So the problem of this conic base, or the limitation of this conic base calibration, is you can't really, you lose everything. So under distortion, this is not working. So even if there's a huge advantage of the detection part, people couldn't use this very well. So what we did is we changed this one a little bit. Instead of tracking this point, what if we go from the center point to another centroid? So can we write an equation and find an analytic form to track the center point, and then just solve this one in an optimization? And that will allow us to do many things. So let's find an analytic solution. And luckily, there is this kind of moment representation which allow us to do so, because even if there's nonlinear mapping, y equals to dx, and d is the nonlinear function, the moments of y are represented as a linear combination of moments in x. So finding the analytic solution is equivalent to finding our coefficient Cij. If we can find the Cij in an analytic form, we are done. So we actually, if you go to this paper, there's tons of math just finding out this coefficient. You don't really have to look into the detailed proof, but we can calculate this coefficient analytic form, closed form solution. Once done, now you don't have to worry about it. You can just run it for the calibrating your thermal camera. Let me show you some example here. So it's hard to find where the image pops up. Yep. And the code is available from the GitHub. You can download and follow the Python script and then run this one. Oh yeah, there you go. So you can run the script to detect, and you see the points are the circles or ellipses are detected, or actually the blob. It you see if it is the the circle is at the corner is totally distorted. But still, our moment tracking can find the centroid point of that. So, okay, I can't see what you're saying, but how good is it? How good? So look at this. For the server calibration, I told you the checkerboard pattern is 4. That gives us 16 millimeter error. The calibration, for calibration, having more than a centimeter error is not acceptable quite. But whereas if you use ours, which is a conic-based calibration, we can actually reduce this error further down to a millimeter level. That's almost equivalent to the RGB calibration accuracy. So it's there. If you are interested in, yeah, go for it. And one thing is, it actually even good for the RGB. It's actually par and even better slightly for the RGB because we have a better detection model for the circles. Circles are much more robust in detection and measurement point of view. So go for it. And it's available. All right, so once the calibration done, what we have now is we wanted to go for secure the data set and wanted to go for the deep learning for the thermal camera. So first, naively, we try to collect data as much as possible, publishing this data set. Stereo data set is a stereo RGB stereo thermal data set from day to dawn to night, so 3 different times of the day. But we realized right after working on it, this data is not maybe good for the odometry or SLAM benchmark, but it's not enough for the deep learning training. So what we thought about is maybe, yeah, we have to switch our strategy. That plan is not really working. And the next plan that we did is to train the thermal and to train the thermal for a very hard task like optical flow estimation or object detection. Instead of training and getting a new data for the thermal, what if we just steal labels from the RGB? So make a small network that converts this image to image translation network that convert RGB image to the thermal-like image, and we can always go back to the RGB image with labels. So we can just steal all the label, reuse it, and only use the synthetic thermal images for training with labels from the RGB. Can we achieve some performance in the test? So we give it a try. We at the time, it was like 3 years ago, so 3 years ago, we used a multi-domain style selection. Some people ask me, can you do the diffusion for that? Yes, of course. And then diffusion, I know that's powerful, so you can do something similar with more powerful tools these days. If we do that, we can train with a synthetic data set and apply with something challenging. So we give it a try with the optical flow estimation because securing label ground truth for the thermal image for optical flow estimation will be really challenging. So this is a result. So we trained from the synthetic thermal images with the image-to-image translator, and we gave the input thermal image, that's a real thermal image, and see if ours can estimate the optical flow. Unfortunately for this, we don't have the ground truth label, but we can only see the consistency happening in this result. But we found out that the result coming from here has less fluctuation, better consistency. So we think this kind of is in the right direction. And after this, we can train a network specific to each task. If our task is object detection, we can just train a network to convert from 14-bit to 8-bit. Or if our task is the depth estimation, we can train this one in an end-to-end manner. So that's another RA letter paper, which we'll present tomorrow. So we call that as a thermal chameleon, and a TCNet is the title of the paper. And we tried to train this one in an end-to-end manner. And then that was quite nice. With the TCNet, we can improve the object detection and depth estimation. But look at the difference. On the right two, their translated image looks different depending on the target task. So if the downstream task is object detection, the end-to-end manner, this network learn to distinguish something for the object detection. If it is for the depth estimation, the object learns during the end-to-end learning. Yeah, that should be something for the depth estimation. So this image translation, let's just learn task-specific way in an end-to-end manner. That really helped. So that's another paper on Tuesday. With that, I think I want to conclude this talk. There's a lot of things I try to kind of pack everything into one keynote speaker. Some recent work from the radar and some recent work from the thermal. There are 4 or 5 papers tomorrow about the thermal and the radar. So please visit us during our session, poster session, and I hope we can talk more about it. With that, I want to thank my funding and collaboration groups, and that's it. Thank you very much.
We have time for one quick question.
Yeah.
We have time for one quick question.
Thanks for the talk. So I'm interested in the calibration work. So how do you combine the metal checkerboard with plastic checkerboard?
So my conclusion is not to use that way, but this one, we printed.
Okay.
We printed. You can ask the manufacturer to make a one that printing the metal in that.
And you mentioned that you have to click the corner points. Can't you detect edges directly and then find the corner
Edges are very blurry. This is like from the actual summary image. The edges are quite blurry. These are plus minus 5 pixels or so.
Thank you.
All right. Let's thank our speaker again.
Thank you. Thank you very much.
Giving focus. So when he on the Zoom, you need to give him co-host.
Sounds good.
Yeah.
Sure.
Okay, so our next speaker is Dr. Georgios Fenekos. Dr. Georgios Fenekos is a senior principal scientist at Toyota Motor North America, focusing on cyber-physical systems and robotics, particularly in automated driving systems. So he earned his PhD in computer and information science from the University of Pennsylvania in 2008, affiliated with the GrassFab and holds a diploma in mechanical engineering from the National Technical University of Essex. And before joining Toyota, Dr. Fenekos was a tenured associate professor at Arizona State University School of Computing and Augmented Intelligence, where he led projects funded by NSF, DARPA, AFRL, and industrial partners, including Intel, Toyota, and Bosch. His expertise spans formal methods, applied logic, control theory, AI, and optimization. So he is a recipient of the NSF Career Award and multiple research and teaching allocates, including Best Paper Awards and Top Educator recognitions. He's previously held roles at NEC Labs and also serves as a program co-chair for ACM HSCC 2016. Now let's welcome our speaker.
All right, thank you for the introduction.
Maybe make sure you mute yourself. No. Oh, okay.
Should I turn on the camera?
No.
Oh,
I think like you can. Yes. That's good.
All right. Welcome, everybody. My talk is not necessarily about perception systems, but rather about the title of the workshop that I liked, intangible specifications. And I'm going to say a few words about that, on how we view these specifications and in the context of our work. But before I do that, I would like to say just a few words about where I am currently working at, because many of our peers here in the conference are not familiar with, even though everybody's familiar with Toyota, I hope so, they're not necessarily familiar with the research division of North America. So I am in a research institute within Toyota Motor North America that we do future challenges research. We look at problems that may be 20 to 30 years down the road. Within that institute, we have a small group that does what is called future research or future mobility, several cool projects there. And within that, we are even a smaller group called the Cyber Physical Systems Group, dealing primarily with issues of safety in cyber physical systems. Cyber physical systems is a bigger umbrella that captures everything from robots, medical devices, whatever you like falls under that. As long as you have computation, sensing, and some intelligence there. All right, so the focus of our research group is on fundamental research on risk-aware autonomous systems, and our goal is to provide mathematical guarantees on functionality and performance under uncertainty. We have 3 topics: requirements, verification, validation, multi-agent systems, and these days we are working on what is called neurosymbolic systems, systems that combine some form of neuro process with some symbolic process as well. Now, our problems are motivated generally from the organization. For example, Woven City is a prime example of a smart city where you have a lot of mobility concepts coming in. And even though we don't work directly on these problems, this is the domain where we draw inspiration to actually do fundamental research. I'm not going to play the video. This is a very interesting video by the CEO of Woven. I'll just show some pictures, they envision a big city, not big, a smaller city, but it's going to be fully instrumented. It is almost open or already open in Japan. There are going to be mobile systems, autonomous transportation for humans, autonomous package delivery, adaptable pods that you can change and depending on the scenario that you would like to do, robots inside the house helping humans, and interestingly, below the city, you're going to have a logistics infrastructure where robots will be running around delivering products to the apartments. So this is kind of a landscape. We draw a lot of inspiration for problems that people may not necessarily think Toyota as part of these problems, right? When you say Toyota, you think potentially cars, you think autonomous navigation potentially, ADAS. These are a new class of problems that we are also being inspired from. And of course, there are plenty of robots in factories, plenty of robots in logistics, and our colleagues that are around here in the conference working in Japan on the hospital delivery robots for logistics there. So a lot of inspiration for problems. Within that, we, as a small group, we work on all kind of edge niche projects in the autonomy stack, from global planning, learning workflows, local planners, for example, communication-aware planning. Communication here, I mean human-robot communication, and all kinds of aspects that have to do with deploying robots. But today, and of course, we work a lot with universities, and typically I'm out here to also potentially look for further collaborations. Because again, we are a small group and we enjoy working with universities on various cutting-edge problems. And today, I'm going to talk about testing such systems. I'm not going to talk about control, perception, neural networks, but rather testing. And I would like to kind of focus on driving videos as a form of intangible specifications for our testing. While I was a faculty at ASU, we had a nice project with Heni Ben-Amor, my good friend and colleague. We were taking dashcam videos, and we were through multiple pipelines of neural networks. Back in the day, we're translating the trajectories from the vehicles to something that you can replay in simulation. And it was an exciting project because you have to think, you don't really have a reference. This is just a YouTube video uploaded somewhere. You don't know the velocity of the ego car. You don't really know, you don't have optical flow that is accurate. You don't know about the environment. So a lot of interesting challenges, but it gave us nice results back then. The interesting thing here is that when you would like to now move to testing, you have a fixed scenario. You have the trajectories that you are replaying, and potentially you can randomize the ego vehicle initial conditions, and you can test the system. So for example, translating the dashcam video to simulation, then you can take the extra step and do search-based testing, but with a fixed scenario, because what you care about is really that bad scenario, the accident that happened in the environment. Last year, we said, okay, this is not enough. Like if you want to have a video being an intangible requirement, you want to be able to generalize that video in some form, right? And we had a very nice intern, Yan Miao from University of Illinois, spent the summer with us, and we threw transformers as everybody else on the problem to see what might give us in terms of approximate thinking about these problems. So he came up with this nice framework where he gave the dashcam video to some language model, that multi-modal language model that process images and text. And from that, we were generating, we were formulating what the model perceived in the environment as a probabilistic program in the scenic language, testing language, from which we could then randomize the environment and generate tests. Of course, when you take the first attempt with a language model, will give you some potential garbage, but it's kind of syntactically structured and meaningful, at least as a program itself, right? So you would like to close the loop in order to get the scripts generated by the scenic model checking, which is a programming testing language developed by Berkeley, Sanjit Sesia's group, over several years now. So you would like to close this loop. And what we do, we have another language model that extracts what we call interesting features about the video itself. And of course, you have then a similarity check, and you close the loop doing some form of reinforcement learning to make the generated simulated scenario close in some sense to what you had initially as a video. And here I'm saying in some sense because at the current stage, we kind of engineer the features we are looking for, but you can imagine a true general framework would like to actually have a way to extract this automatically. And who knows what is really what makes a video interesting, right? So that's the main question here. If I give you a video, we all know what makes it interesting by taking a look at it, but still we cannot make our models figure out what is really the interesting part. So I find this to be a cool research project here. This is just one more slide to show you how we close the loop. So for example, we had extract as a feature that you have an opposite vehicle cutting in at 10% in terms of overlap. And then through the feedback mechanism, for example, at the end, you have it at 90%. This was for a video, you are having a head-on collision. Just purely in terms of assistance for test engineers, you can reduce 1 hour of human coding where the human is trying to create such a scenario to a 2-minute automatic process. Out of 50 videos Jan downloaded online, 32 were fully automatically generated into test scenarios. 17 out of 32 videos were improved using iterative refinement. And 9 out of 17 had good results through full automation. Of course, you have plenty of challenges. When you have bad weather, snow, and so on, you cannot really use that yet, but you can imagine if you keep working on this problem, it's only going to get better and better. All right, so again, the main challenge here is what makes a video interesting. Then you can start building the scenario around this. On a kind of orthogonal direction, you may want to have a way to abstractly search for interesting scenarios. And we had that vision of, can we really search for scenarios as simply as writing regular expressions? Most of the people who are in computer science or anybody who uses computer and you would like to search for a string, you're familiar with regular expressions. So we said, can we do the same for videos? Can you have your data set somewhere, write what you're looking for as some form of regular query, regular expression, and then search your data set to find related videos. So for example, you may want to write something like, next to, you have a car that is black and a bicycle for 5 to 10 frames. Here we maintain the regular expression syntax as close as possible. And then you would like to give this to your system, maybe translate it to something related to distances, right? Maybe. And then return to you that segment in your data set that satisfies that query. So here's, and we did it. So here's an example of integration with Foxglove. This is, I don't remember what the data set is right now, but the Foxglove is an open source, maybe from a startup, framework to replay and visualize your data sets. And so we interfaced our framework here, and you select the channel that you would like to have. You can write your search query in natural language. In this particular case, it is find all frames where a pedestrian is excuse me, is occluded by a car from the perspective of the ego vehicle. And as the algorithm runs, you select the channel. And what you see here in blue is the highlighted regions where we have found a match for the query. So let's see an example here. So here is the ego car, here is a vehicle, and pedestrian is there. So you have this occlusion, for example. So what are special regular expressions? And I'm going to show here some details for those who are familiar with formal methods and enjoy formality. So we have special terms, which is a form of spatial logic that reasons over sets. The easy connection here is that most bounding boxes or bounding rectangles in space are sets, and you would like to be able to reason about occlusions, intersections, intersection over union, and so on and so on. So all this can be encoded using the S4+ logic. This can be extended to talk about emptiness and subset relations, so that you can say that something is fully occluded, for instance. And then you can combine that with the standard regular expressions, right? And you can write regular expressions where every atomic element is a topological formula. And what changes really is when you try to give an interpretation to this language, is that now you don't have a match of one string as you have with regular expressions, but really you can have multiple ones, right? Think the simplest possible scenario. I would like to find 2 frames where I observe a car, right? You can have multiple cars in a frame, which means a proper matching framework needs to collect all of them and say, okay, here's a bunch of matches for you. Okay. And therefore, we don't talk anymore about a single match, but multiple matches within your dataset. Here is just the general architecture. You give as an input the spatial regular expression. you process it, parse it, and you build DFAs, and that's what makes our framework quick. We have these DFAs that do the matching, but now the transitions over the DFAs are symbols that correspond to topological formulas, so that we can do topological reasoning. Then there is this matcher, and the evaluator is the topological reasoner, and then we return matches. Again, we don't care about whether a given stream satisfies an expression or not, but rather where it starts and where it ends when you match it, because we would like to have this data. This is integrated with rows. So you can write something very simple here just for visualization. Non-empty means, of course, you don't have, you have a non-empty intersection here of a pedestrian, which means the bounding box of a pedestrian, and a bicycle. And I put a star there to say that I would like to have the longest possible match in my perception stream. The tools are all available online. You can download and play with them. And in terms of current pipeline that you can find online is you can have, of course, in a proper perception stream, you can have multiple channels for multiple sensors. What we have online focuses only on camera, and you can have a DNN doing your classifications. So you can reason about objects, or you can reason after your sensor fusion on a map about such a map, right? If you want to talk about relations between different vehicles. So here's an example just to show that this running real time. We integrated with Carla. The integration is publicly available online. So you can run ROS, you can run Carla, write your query for the example I gave you before, and then live, it gives you the matches in terms of frames as they occur. Okay. My point here is that this runs real time. And this is an example of different queries, how they scale with the length, because our goal is to be able to do queries that have very long time horizon. And I'll make a comment later on why we really need to be able to handle very long time horizons. So you can see here we're talking about milliseconds, so all good. I'll skip that. Okay. The running times, of course, matter whether you have a match or not, right? If you don't have a match, you may be running for longer time. So how fast you run also depends on whether you have matches or not. Here's an example of how you can extend the framework to handle, let's say, depth data. You're giving images. You add to that one of these image to depth models. And now you can do not only images, but also reason about the depth in that image. Because again, our goal is to be able to work even with YouTube videos where we don't have really any depth estimation data for that, right? We don't have all the perception data. So here's an example of that. You call Strem, which is our online, our monitoring tool for spatiotemporal expressions, regular expressions. You write your query, and you can pipeline it with your camera, which is going to run also the depth estimation part. And here the query is the distance between the car and the track has to be less than 100, and the distance between the track and the car, okay. And the x distance, the x coordinate between the track and the car has to be ordered there. And Jacob, the person who has been developing this primarily, got his little toy cars, and now you can see online the matches as you move around the track and the car. Again, main point, this is happening in real time, and you can write arbitrary queries for what you search for that have spatiotemporal components. All right. Now, let me take you back to Foxglove to give you open challenges here. Let's say you have a map view of the environment, and you would like to say something like find all frames where a bus is near the back left of a truck. Because we are writing formal specifications, we need to define really what near and back left mean. But ideally, you would like to have a model giving you these as general information. What near and back left means for the specific context that you are working with, right? So these are kind of interesting questions when you try to connect the actual language model with the underlying formalism to return your queries. In this particular example, you can see the system gives you matches, but we have given an interpretation already of what that means. All right, so some remarks and limitations. Our goal is, again, to keep these queries as close as possible to regular expressions. That is our main motivation, be as close as possible to regular expressions. There is an interesting consequence because of that closeness. You can use language models now to write your natural language queries and automatically translate them with very high success into these regular expressions because the training corpus is humongous, right, for this type of relations. So this is all great. So you may ask, can't language model do this directly from images, right? And this is an excellent question. And of course, with 4.1, these days, the answer is mostly yes. There are two limitations. One is, of course, it doesn't run real time. And the second, it doesn't do well in very long temporal contexts, right? So if you want to say something happened now and something else happened half a day later, then you'll not be able to get good matches using language models. So still we need these formal tools as underlying foundation to even potentially help our language models. Now, interestingly, this is an extremely hot topic. This spatiotemporal reasoning is an extremely hot topic last year and this year. In terms of smaller models, you don't want to be running GPT size model for this type of queries real time. You would like to have a small model. If you see in the literature, small models, unfortunately or fortunately for us, don't do at all well in spatial or temporal reasoning. So we need to have these training assistive tools to improve performance. Another interesting limitation for both the current version of the spatial regular expressions I presented and language models is uniqueness of objects in a scene. If you want to say, track this specific car across time, becomes extremely challenging. So this is another open or semi-open research challenge, given that we are working on that problem. Okay, so future work, and future here is a little bit in quotes because we have already ongoing work potentially under review. Robustness of queries with respect to classification noise. If your classifiers, for example, are extremely noisy, you have to decide what does it mean to have a query matched. Okay, so this is an interesting problem. It will give you some form of quantitative or qualitative query matching. The second is, of course, training smaller models. This is an open challenge these days. Uniqueness of objects in queries, as I have already mentioned. And my biggest challenge here, what makes a scenario interesting? Current language models, unfortunately, cannot tell us what makes the scenario interesting. Maybe it's a training data issue, but just cannot really figure out what is the interesting part. You can have them describe a scene, and that's what we have based on right now in all these translations. You can get information of what is in the scene and how it moves, but not really what was the important features within that scene. Okay, so that makes it an interesting problem. How much time do you have? 10 more minutes. Okay, great. All right, then, excellent. I'm going to have a bonus item here of another class of intangible specifications, and this is with respect to neural networks fine-tuning. This is work that we started when I was at ASU, and I think this fits nicely here in the context of what is these intangible specifications. And I'll motivate this from the classical problem of verification of neural networks. typically we have an input domain. It doesn't matter really what the problem is. We have an input domain. We have a neural network. The neural network will give you some reachable set for, let's say, your classifications in terms of ranges, your reachable states, if you're doing some kind of control computation with the neural network, and so on and so on. Now, you may have a safety property there, and all is good if that safety property completely encompasses the reachable values. And here, there's a lot of research happening on how to develop algorithms to capture any neural network behavior given, again, a set of possible inputs. But interestingly, another topic that I find really exciting is if you have some violation, if your system doesn't satisfy the property, what can you do to go back to the neural network and fix something there, right? Repair, or potentially even better, have guaranteed repair given the counterexamples you have encountered. So here's a concrete example. This was a project that Henny Ben-Amour was working with his students. I think maybe they're still working on prosthetic and neural networks. The question is, can we bound the control rate that is computed by the neural network to be within a safe boundary? Okay. What you see in red is the original that we have learned from the real data, a human walking, right? So this is the real data. You would like to replicate that behavior on the prosthetic device, but on top of that, add a safety feature. Okay. So even though you can replicate fully the natural behavior, after you have learned the natural behavior, you want to come in and add bounds and keep that resulting behavior as close as possible to the original data, but still satisfy your safety properties. So this is a data-driven problem where we want to change, not just replicate the data we have, but also modify the resulting behavior. And the way we did that was getting our counterexamples and formulating a mixed integer quadratic program for a specific layer of the neural network. And at the end of the process, you get a guaranteed result. Now, for this setup, we don't have intangible specifications. The specifications are very concrete. These are the bounds. Make sure your behavior fits in there, right? So we said later on, what if actually we have a predictor, right? That predictor can be viewed as the specification. So you get the state of the system as input to the predictive model. You get the action that is given to you by your policy. And this predictor model reduces that into a lower dimensional, let's say, space, which could be either some predicted values for your system performance or your safety requirement at the end of the day. So why you may want to do that is because you reduce the size of your repair problem and your training problem potentially. And now your training, even though we cannot have the nice mixed integer quadratic program formulation as before, at least now we have a natural way to give as constraints or as requirements any arbitrary neural network there that takes as input state and actions for the system. And this computes your requirement, and you can repair now the policy using classical fine-tuning techniques. All right, and you can do that, and you can see here from the results. In this particular example, we would like to have the pressure to be bounded within some safe region. And of course, I'm showing you here that we achieved that result. You can read the paper. This was in last year at IROS 2024. All right, great. So some closing remarks, and I'm hopefully finishing a little bit earlier. Okay, so closing remarks with respect to our research group. What we are working on is performance verification. How do you specify correctness for a lot of the data-driven learning problems that we are dealing with? It's very hard to define what correct behavior is. So potentially these type of intangible requirements are the way to move forward, at least for some level of certainty. How do we develop a testing theory? How is it even possible to prove correctness for all problems of data-driven systems? Trustworthiness, how do we steer responses toward a goal? User alignment, and how do we integrate symbolic human-like reasoning? So these are kind of the primary, the priorities for our group right now. Just embodiment in general is, of course, another direction. I'll skip that now. And I would like to, since I mentioned that our second direction is on user aligned systems, we have a workshop at ICRA 2025 on user aligned assessment of adaptive AI systems. Please submit your extended abstract. We want to have the discussion going on what does it mean to verify systems, especially after deployment. The question is, you have a learning system that adapts to the environment, so the original specifications by the manufacturer may not become relevant anymore as the system evolves. So what do you do? And we'd like to open this discussion, so please submit. This is a follow-up to a last year workshop at the spring, I think, series of AAAI. We have a DAX tool workshop coming up. So we'd like the discussion to roll and going on, and I'll stop here. Thank you.
Any questions?
Only softballs, please.
Thank you for a very nice talk. You mentioned that, so I noticed that defining the atomic propositions for the logic to discuss actually requires a lot of properties from the either video or map of the environment.
Mm-hmm.
So I'm curious if you have thoughts on this. Do we need to reconstruct maps as opposed to using video? You also mentioned kind of the length of the temporal context starts to become a problem. So do you think there's some reconstruction of the environment needed before we search using regex, or
Right.
we use video images?
This is an excellent point. And thanks for the question, because it will help me clarify a little bit. It really depends on what you would like to search for. You could operate directly on the point cloud. We don't have it directly supported right now for the public version, but you could do that. If you want to just reason directly on grouping of points, distances between points, you can do that. But potentially it is not very useful. Maybe there are some applications that's useful and that can be done. Depending on what you would like to reason about, you can go in and plug in at this respective level. You can just, for example, reason about images directly. So you can run a classifier, reason about images. You can reason after you have done the 3D fusion. You can reason after you have done you have run other models that give you side channel information, right? It really depends what you would like to get out of that. So, yeah.
Thanks.
Thanks.
Thanks for the very informative talk. So I wanted to ask, like, what type of backends in terms of like database query systems that we are using underlying this? Are there like good APIs and like interfacing with those are easy, or are there challenges there as well?
In terms of storing the data, the perception data, or
storing the perception data, doing the search. So you are not writing the search engine yourself, I suppose.
we wrote the search engine. What we haven't done yet is the integration with the databases.
Like Databricks type load, you don't use those sorts of data.
Databricks.
It's just like a database query system.
Well, it really depends on the type of the database. What is the underlying way to record the data, right?
How big are these data sets? Because like they are long videos of lots of long videos, right?
Okay, so that's a separate problem integrating. So think of it SQL, for example, SQL, right? in SQL, you can throw in your regular expressions and search over your data. That's our goal here is the same. You can write your spatiotemporal null query and search over existing data. But that's kind of a little bit separate problem. How do you retrieve the data to sequentialize it and do your search there, right? Because right now we just want to develop the tools to enable you to do that. Then the other setup is to enable retrieval of the data from the database so that you have the appropriate temporal relation across all your data that have to be aligned. And this is not trivial because everybody's using different way to represent their data. And Jacob here had done a lot of work to make sure that there are these type of serializing or sequentialization of existing data sets that are openly available. I think like the new scenes format, or I don't remember exactly the details, so don't quote me on that, but we already have a couple of interfaces where you take these data sets where everybody has innovated on how they store them, and then we create a stream where we can actually search over that. Yeah, thanks for the question.
Any more questions? If not, let's thank our speaker for the nice talk.
Yeah.
And finally, Nikolai will give an introduction to our last speaker.
So, everyone, thank you for sticking around until almost the end. We have one more talk, which I'm excited about, and we're slightly ahead of schedule, but I think it's okay. We can move forward. This will give a little more time for the last talk. So I'm excited to introduce Professor Vadim Indelman. Vadim is an associate professor in the Department of Aerospace Engineering at the Technion. And there he leads the Autonomous Navigation and Perception Lab. His research focuses on autonomous perception, navigation, and planning under uncertainty for both single and multi-road systems. And some of his interests include planning under uncertainty, probabilistic inference, semantic perception, simultaneous localization, and mapping. So we're very excited to hear from Vadim, and I guess as part of his goal is to give some closing remarks also from the workshop. But don't worry, I'm gonna also say a few words at the very end. Please welcome Vadim.
Right. Thank you, Nikolai, for a nice introduction. And thank you for the organizers for this opportunity to present some thoughts of mine. And I'm very excited to be here today. And thank you for attending this late talk. So I'm going to present a perspective of robot safety under partial observability. And I'll try to kind of highlight some of the challenges that are out there. For sure, it is not an exclusive list, but let's start. So to set up the scene, let's do some quick intro. So for advanced autonomy, we typically require a few key capabilities. The first of which is the ability to probabilistically infer the state of the environment, so perception and probabilistic inference. This probabilistic inference can be over different levels. Basically, can be on geometric level, can be on semantic level, and so on. And on top of that, we typically require advanced AI and the decision-making capabilities, basically deciding the agent has to decide what to do next to realize tasks. And so in this talk, I'm going to consider this autonomy loop for an online setting, meaning we have some cycle here that is operated at some frequency, where we update the distribution over the state. The state is application dependent, so we have this belief. We do planning under uncertainty, while caring about safety aspects, of course. We perform the action or the policy that was calculated, get from the environment a new observation, update the distribution, belief, and continue this at some frequency, right? So a bit more in depth for now for the info part. So we maintain this posterior distribution over the state, given all the data that we have access to. We do not specify here explicitly, but this is conditioned on the prior and also on the models that we assume to be available here. So just for example, we could consider some manipulator that reasons about location of different objects to point to pick. We could consider autonomous driving, where we map the environment and the reason about the different lemma objects, classes, and so on. On top of that, we now would like to formalize the decision-making problem, and we will formalize this within this framework of HOMDPs. So for that, we'll have the state, observation, and action spaces. We have the corresponding models, meaning transition and observation models, a general belief-dependent reward function, and some prior belief from the inference part, BK. Okay. So with that, we can now consider the value function, which is looking here for some policy, a time k. Okay, so this is basically the expectation over cumulative sum of rewards. And in the context of this workshop, we would like really to maximize this value function subject to some safety constraint to be satisfied with sufficient probability, 1/7. This is what we'd like to do. So consider this toy example just to set up the scene again. We have this toy agent that has to be located. It's somewhere in this grid region. It does not know where it is located, so we have some distribution, the belief MK, that denotes the probability to be in each of the cells. And now when we consider planning, we reason really how the distribution evolves in the future for different actions and for different observations. Now, generally, this distribution will evolve differently for each such realization. So we should have considered all the possible realizations. Obviously, it is not tractable for sure as we extend our planning horizon. And when we are talking about high-dimensional settings, SLAM, for instance, then the computational burden becomes even more complicated. Nevertheless, what we like to do is we like to develop autonomous agents that operate safely in the environment, right? This is what we like to do. So with this, what I want to do in this very short talk, I would like to present some perspectives of research that we are doing, and maybe this will bring you some ideas for your own research down the road. And I'll start with POMDP planning with beliefs over continuous and discrete random variables, so hybrid beliefs. And I will highlight two reasons why would we have such a setting. The first one has to do with semantic perception. So consider this movie. So I will not say from what Thomas Card is taken, I guess you can guess, okay? But what you see in the monitor here is a complete mess, right? So let me play it again. So we have this, the classifier tells us this is a truck, this is a car, it rotates it for some reason, right? And then all of a sudden it becomes a person. What's going on, right? And this is, this is bad news for safety, obviously, right? And one of the reasons for this unwanted, undesired behavior is that semantics and geometry typically are treated separately, independently. And again, this could lead to very undesirable results and safe behavior and so on. So what we really care about in this part of the talk is to reason about the coupling between semantics and geometry. So conceptually for now, if you're looking at this object from different viewpoints, from each viewpoint, the appearance of the object changes conceptually. And so we have this coupling between the classifier and the viewpoint, which is by itself a random variable, it is uncertain. And so if you want to capture this coupling, we can introduce this, what we call a viewpoint-dependent semantic observation model, where the S here is the output of some classifier, it's a semantic observation, and is conditioned on object class and on the relative viewpoint of the agent to the object, okay? And so with this model, basically, we have to consider a distribution over all the random variables, which are in this case xk, the continuous variables, the agent poses, the object poses, and so on. And all the discrete variables, which are in this case, the classes of all the objects that have been observed until the current time. So generally, we have this huge coupled system where each variable is dependent on any other variable. There's specific structure, as you can see here in the factor graph. But nevertheless, we can no longer assume that classes and objects are independent. We can no longer assume that classes of different objects are independent. And this is in stark contrast to many, many works these days that make simplified assumptions, such as they perform per frame classification or modeling the semantic observations as viewpoint independent. Right? Now, why is it of interest? What's going on then? So if you now consider planning, so we like to, we like to evaluate this value function and optimize for the best policy or immediate action, then BK here is this higher belief over many, many discrete variables, right? So it can be written as using chain rule into two forms, and we'll see why is it problematic actually. Now, in the concept of safety now, we can specify the notion of semantically aware safety or semantic risk awareness, in other words, where the unsafe region is actually class dependent, right? It really depends what is the object that I'm looking at to reason about safety, right? If it is a human, then there's some unsafe region. If it is, an elephant, there will be some other safe region and so on. But the class is unknown, right? It is part of belief. And moreover, we have many, many objects in the environment. And so to actually somehow evaluate this or estimate those guys, we need the ability to sample from the distribution, this distribution at time k, even just time k, the current time. How do we sample from this? And the complication stems from the fact that without any assumptions, we have an exponential number of classification hypotheses here. Right? M here is number of classes, N is a number of objects. So one question is, how do we sample from this BK to estimate the probability to be safe? And what kind of guarantees can we provide on the corresponding estimator? And importantly, how can we sample without first pruning some of the classes? Because if we prune, then maybe we have pruned the correct class, and this may lead to bad things. So we have a work that addresses these challenges, so do not have time to actually go over it, but you can read it later if you want. But I just want to mention that this work succeeds in maintaining very accurate estimation without pruning any of the classes I mentioned before, and it scales linearly and not exponentially in the number of hypotheses. So the details are in the paper. All right, so this was the first reason why to consider higher beliefs. The second reason is ambiguous settings. Also here we have hypotheses. So imagine now that the agent is located in some environment that has some repetitive structure, perception aliasing, for instance. So imagine that we have this observation, here it is, and this observation could be explained by these two elements, okay? And so the agent has to basically reason about, in this case, two hypotheses, right? Either it is coming from this guy or for that guy. Now, if it considers the correct hypothesis, let's say this guy, then it would update its prior belief to the posterior belief and understand, okay, so to reach the star, it should go to the right and so on. But if it chooses an incorrect hypothesis, the posterior will be here, while the agent actually be located here. So it will think that it's something over here, and it will be guided upwards to the goal, and instead it will enter an unsafe region. Right? So bad things can happen then. And so the question we would like to ask here, how should we identify, how should the agent autonomously act in such a case? Maybe it should gather data to disambiguate between those hypotheses before actually committing to some specific case, right? So these are the two cases that I explained so far for where we have hybrid beliefs, either classification hypothesis or data association hypothesis. More cases exist, obviously. And in both cases, the number of hypotheses grows exponentially, either with time or with the number of objects. And the question is, we cannot do exact calculations with after some time, because there's exponential growth. What is the impact on safe decision making if we are trying now to approximate things because there's no other choice, actually, right? So, for instance, in the context of data association hypothesis, if you consider this belief tree that I described before, where each node here corresponds to a plausible possible posterior distribution in some time in the future, there's another tree that is hidden inside, which we call a hypothesis tree. Let's see why. So imagine that now we have a single hypothesis here. So here this is a single hypothesis. And we consider the possibility to get this observation. So this observation may give us, let's say, two hypotheses. Let's say we have only two possibilities here. Now, if we go down this sequence, each time we have this branching factor of 2. So very quickly, the number of hypotheses grows beyond, exponentially. So to go beyond our capability to actually calculate explicitly. And so one idea is, okay, we can sample promising hypotheses. That's fine. That's doable. But again, what is the impact on decision making? We just consider a subset of this exponential number of hypotheses. So in some work, we can prove that the simplified value function that considers only a subset of hypotheses can be the difference between this one and the value function that considers the full tree can be bounded. And what is important in this bound is that we can evaluate it online, meaning this bound is only a function, kind of difficult to see here, but it is only a function of the quantities that we open in this subset of the tree. So it can be evaluated online, which is very important for safety, actually. And this notion of taking some problem and simplifying, we call this in the lab simplification of decision-making problems. Again, the concept is to identify and solve a simplified problem and provide performance guarantees. And if needed, we can adapt these guarantees on the fly. And we have different flavors of this kind. Now I touched one of those flavors as utilizing a subset of hypotheses, and many other flavors exist. All right, moving on. We'd like to say a few words about any time constraint competitive planning. So in this context, we consider an anytime POMDP solver that constructs this belief tree using MCTS Monte Carlo tree search type of techniques for POMDPs. And in this case, we would like to, again, maximize the value function subject to some probabilistic constraint here that can assume at least two forms. So C here is a binary Bernoulli variable. It can assume two forms. It can be either a cumulative form where there's some summation over some function of a function of a pair of beliefs. The motivation for this form is information gain like scenarios. We would like the agent to explore the environment, but we'd like the exploration to be meaningful, meaning there's no sense to explore if the information gain is not significant. And so we'd like to explore only when it is sufficient novelty. But in the context of this workshop, what is more appropriate is this form, where this constraint here takes a multiplicative form, where each indicator here corresponds to basically to a safety aspect, meaning what is the probability of the agent to be safe given the belief at future time L. And we require this to hold for each of the future time instances given a belief sequence. Right? And the question is, okay, given that we have such a definition, how do we construct a belief tree? How do we do anytime planning in such a setting? Okay. So we have some works that do these things. For instance, we can approximate the constraint by empirical expectation by drawing samples. So this is the empirical approximation of that constraint. We can do adaptive pruning for if we set epsilon equals to 0, only then. In that case, if we have some portion of the tree that we constructed, in the case one of the nodes violates constraint, this constraint it is violated less than what we wanted, then the entire branch can be pruned because of this violation. This works only when epsilon is equal to 0, actually. And much more things can be said here. I refer you to the papers. A lot of things can always be going on in this area. How much time do I have?
5 minutes.
Okay, perfect. Another thing that I would like to mention briefly really is concerned with multi-agent setting when we consider limited data sharing capabilities. So let us discuss that for a moment. So imagine 2 agents or more, but let's do 2 agents. So each one has its own sensor. Now, if they can share data with each other, so they share data with each other, then they can each plan, perform basically decentralized planning, and each reason about its own and the other robot actions, and identify the best joint action to reach the star and avoid the unsafe region here. But that requires communication, data sharing.